Good morning, everyone, and welcome to Comic-Con version 3. Please feel free to get seated. We're going to get started with the presentations here in a second. You know, Comma's been around for basically 10 years now. Every year we have better products, we make better software, we're growing, we sell more, and we have more Comic-Cons, and there's more of you every time. This is Comic-Con version 3, and I think you guys are really going to enjoy the stuff we're going to talk about and some of the cool new things that we're going to be able to show. There's also some cool booths around that you guys can explore in the free moments. To get started, we're going to start with a presentation from the OpenPilot team about OpenPilot development, and they're going to come up right now. Shane and Maxime from the OpenPilot team will start with their presentation on solving simplicity for OpenPilot development. Enjoy.
All right, so today I want to talk to you about two core principles that we use to develop OpenPilot. The first one is testing or requirements, and the second one is simplicity. And then I will show you how those two things actually go full circle at some point, which is very cool. So let's start with the first one, testing and requirements. You need them. And in order, nice clicker. So we believe that your test should be as quick as possible in order to iterate as fast as possible without fearing regression from the past. And in order to do this, we did a project called the 1 minute CI, which, as the name states, your whole CI must complete in 1 minute, otherwise it fails. And this is very important because we consider that the time it takes to test your code should be part of the test itself. Your code should be fast and quick to test. And we use GitHub Actions for most of our CI on OpenPilot. And I took the screenshot from our GitHub page this morning, and as you can see, everything runs in 1 minute. And this is all the tests that we run every time you push a single commit to OpenPilot. And we do a bunch of stuff. We build a release, we build a Derks, we test the simulator, we run unit tests, we run static analysis. We do a bunch of stuff. And if you want to do stuff like this, if you want fast CI, which I'm sure you want, if you don't think you want it, start making your CI faster and you will learn that you don't want to go back to your garbage CI. So if you want to do this, I have a few tips for you. The first one is you should probably delete or at least reevaluate most of your tests, because most of your tests were probably written at a time where you didn't even understood your software. And now, if you reread them, you probably understand that most of them are useless. The second thing you should do is you should dream a little bit. As Harald said, this is the comma 10th anniversary, and about 9 years ago, there's a very famous commit that was made to OpenPilot. And if I can click, nope, not this one, yes, this one. From 9 years ago, that says one day we will have CI, one day we will have testing. And these days we have testing, and we have very good testing. But in the spirit of this commit, about a year ago, I did a reply to an issue on GitHub if I can click, thank you, that says one day OpenPilot will install in 10 seconds. You know? And what I mean by what OpenPilot will install in 10 seconds, I mean that before you start testing your code, you have to install Python, all your packages, maybe Valgrind or something like that, and this is a recurring cost, and you want to shrink that recurring cost as much as possible. So testing is very fast. And these days, you can install OpenPilot in around 11 seconds, so off by one, but we're getting there. It used to be in the minutes, and this is insane. Now it's very fast. Another thing you should do is you should chase every second, because you only have 60 seconds to test your code, so every second matters. And if your CI takes 17 minutes to run, you probably don't care about 10 seconds. But I'm going to show you one very specific example where we save 10 seconds with our unit test. We use PyTest to run our unit test because most of our code base is written in Python. And this is how we run PyTest. We run PyTest very simply, but just before that, we also run PyTest with -- collects only. And those two lines are 10 seconds faster to run than only running PyTest. because it does a bunch of stuff, because we use multiprocessing to run our test. And many people didn't believe me when I pushed this commit, and they tried to revert this line because they didn't understood why it saves 10 seconds. And every time they did this, they actually had to revert with a realization like this, that it actually saves 10 seconds. I don't know if you can see this, but yeah, Shane made this commit about a year ago. So very fun. But having quick and fast CI is not enough, right? Because I could write something like time.sleep5, it would run instantly, but it will be garbage. It wouldn't catch anything. So you actually want to be able to trust your test. And one way to do this is you should never have flaky tests. If a test fails, it should always be because the code it's testing is bad, not because the test itself is bad. And in order to do this, we did a very, very simple thing that you should actually do right now after this talk. In GitHub, Action, and even Jenkins that we use for our hardware in the loop test, they have a feature where if a test fails, you can just press a button to replay it for some reason. And if you have a flaky test, maybe you have a test with a threshold, and sometimes it goes a little bit over or down the threshold, and most people just play the replay button and they go on with their day. And the flaky test stays in CI forever, and they never fix it. We actually disable this feature. And on top is GitHub Actions, the bottom is Jenkins. It will yell at you, don't do this, fix the test, fix them instead. This is very powerful, and this way you can eliminate, flaky tests, and this is very nice. Otherwise, the flaky test will just hid in your code base. The second thing to gain trust in your test, and this is the most important part because this is not enough. This is good when you have flaky tests, but if you want to actually gain trust in your test, most people will use stuff like line coverage, or if you're fancy, like branch coverage. But those metrics are not enough, right? Because I could, again, write time.sleep5 and run your whole code inside a try-catch block, never fail. I would probably get 100% line coverage, but I wouldn't catch anything. Because line coverage only checks how many lines you actually run with your test. But this idea of line coverage is very nice, because this is exactly what I want. I want to make sure that all my lines are covered by my test, right? They check if the line won't change. But more specifically, I want to make sure that all the semantic, the logic of the line are covered. So what I really want is something like semantic line coverage, right? And this thing exists, and it's very nice, and it's called mutation testing. And I will explain to you what mutation testing is. Very simple. Let's say that in 5 years, comma pivots to a liquor store company or something, so we need a function called isAdult. But don't worry, we're still open source, so someone submits a PR, or someone submits a PR. And since you are the developer, you add a feature, you add a unit test, right? And this code is correct. It checks if you're an adult, if you're above 18. But this test is garbage. It clearly doesn't understand this line. It knows that something around 18 happens, so it checks above and below, but it doesn't understand this line. But we merge it. And 5 months later, I do a refactor, and I push this commit, where I change this sign to this sign. And I merge this, because I see a big old green check mark, that's my test, and I trust it, and it was very fast, so I trust it. But now, I just changed the meaning of this code. It doesn't mean anymore if you're an adult above 18, like just 18, and that's it. You're an adult at 18, and that's it. This whole thing, this whole experience of testing your test is what mutation testing does for you on every commit. It will take all your lines, right? All your line, it will try to mutate them, so it will take the operators, flip them, make them bitwise, take all the numbers, make them big, small, nan, null, whatever, and then it will run all your unit tests, right? PyTest, unit tests, whatever you have. And if your tests don't fail after those mutations, this whole thing will fail, and it will say, hey, I changed this line, and your test didn't pick up on this. So either this line is like dead code, remove it, or your test don't understand this line, and you could push stuff like this. So this is very nice, because this gives you trust in the things that should give you trust in your code. Because how do you gain trust in your test? You can do it with stuff like this. And we did this for the Panda safety that now lives in OpenDBC. And mutation testing is not perfect, because when you think about it, what if the mutation you did is like computationally equivalent to the previous thing? Well, if you have the answer to this, you just won $1 million and a Turing Award, but it works for our purpose, and it's very nice. Okay? So now you have great tests, because they are quick, and you can trust them. That's nice. let's talk about simplicity. I'm going to take one example, very simple, that we did very recently, actually, and that you probably use every day. It's the openpilot UI. We rewrote the entire openpilot UI from scratch. We went from an UI written in Qt with C++ to a UI written in Raylib in Python. Raylib is a simple, thin wrapper around OpenGL. And Shane will talk to you more about Raylib in itself. I want to talk to you more about the graphics stack that we used to use and our new graphics stack that we use now. So, well, it's crop, I guess, but it says openpilot UI. And as I said, openpilot UI was written in Qt, right? And since we're on Linux, we need a windowing system. So we use Wayland. But the problem with Wayland is that it's more of a standard protocol, so we need an implementation. And we use Western. But again, in the real world, Western doesn't really know how to speak to Qt, so we use something called WL shell to communicate. Remember that name, it will come up later. And we need the rendering client, right? So we use OpenGL ES2. And OpenGL doesn't really know how to speak to your system, so we use something called EGL. And I know the order is not exactly right. This is just so it's nice and flow down. But at some point, we need a buffer, right, to render frame into buffers. So we use libgbm to get buffers. And to actually drive the screen, we use something called the libdrm. Yeah. And since we are on a Qualcomm chip, we use the MSM backend and the MDP5. This goes on. I could go all day. I could do the full slide. I wouldn't be done with the graphics stack, right? This stack is pretty insane, and I call it the 3 letters acronym stack, because everywhere you look, there's more 3 letters library that just pops up. GBM, generic buffer management, DRM, direct rendering management, MDP5, mobile display processor 5, it goes on. And by the way, EGL, it doesn't mean anything. If you go on the Chronos website, which are the guys that are developing the standard, they will tell you EGL stands for ta-ta-ta, but ta-ta-ta is not EGL, so who knows what it means, right? Yeah, so this used to be our stack. And when we first tried to move to Raylib, I went on their GitHub page because they have a very nice GitHub, and I looked at the requirements section, right? What do we need to switch to Raylib? And they said, we support Linux. Great. And we even support Wayland. And I was like, I have Wayland. Can I have Raylib? No, you can't. Okay? Because again, remember, you have Wayland, Western, WL shell. And of course, it broke at the WL shell because nobody knows about this weird 2000, the thing that was deprecated in 2015, that nobody used. So it was broken. But this whole experience gave us the opportunity to actually learn about the graphics stack and move to something simpler. And I will show you our new stack that we call the magic stack. We tried to choose a very simple word, not an acronym. It's very simple, just magic. And it's much simpler. And this is our new stack. It basically replaced Qt with Raylib and Wayland with magic, which is a special piece of code that we wrote. And when I say this is simpler, I'm not saying like the idea is simpler. No. Like Wayland, so Western, is more than 250,000 lines of code, right? Magic is 200 lines of C and 60 lines of Python, which is 1,000 times smaller. And I'm sure most people would say that sometime 1,000 times smaller is kind of 1,000 times simpler, right? So this is much simpler stack. And I know some people will look at this, right, and say stuff like, well, why did you change? It was working. What's the point? You just chase simplicity for the sake of simplicity, right? What the expression is like, don't kill your horse if it's still alive, or whatever it is. But we change for a reason like this, okay? This is the model execution time, so the actual time it takes for the model to run on your GPU, on your device. And as you can see, this is our new stack. And this is, on green, it's the old stack. And the further on the left, the better. It means it runs faster, because the UI and the driving model has to fight for the resource of the GPU. So you want the model to have all the time, so it doesn't conflict with OpenGL shaders or whatever. And we did this. And when I first plotted this, I was expecting the inverse. I was trying to see how bad of a job I did with this rewrite. But turns out, if you choose simplicity, you get stuff like this. And I love this plot so much, because it's such a representation of what comma is. Raylib is written in Python by one guy in Spain, right? Qt is like a 900 people company. You cannot git clone Qt. If you go on the subreddit of Qt, it's all people bitching about like licensing fee, etc. So it's very complicated. And did you know that Python is 500 times slower than C++? I didn't know that either, but turns out if you choose simplicity, you win. And this is the part of this talk where it's super cool because it will go full circle. With this new simplicity, we can actually get new requirements, new tests. And I will finish on this. There's 2 new requirements we want to do with this new simplicity. The first one is we want to move the UI off from the GPU. We want to do software rendering. So the driving model has all the time for, do its stuff, drive for you guys. So this plot will look even better. And to do this, you kind of want to use the software rendering implementation. So if you want to do the Mesa LVM pipe thingy to do that, well, you need to change what you use. And with the old stack, it's pretty hard because who even knows where the OpenGL context is created, So now we can do stuff like this, and we will do this very, very soon for you. The second thing we want to do, we want to add a streak mode to the UI, where if you start the UI with streak equals 1, and the UI drops a single frame, the UI gets killed instantly. And this is very nice because it would lead to a perfect UI, which never lags, essentially. And to do this in the old stack, again, what does it even mean to drop a frame? Where does it drop a frame? Is it in libgbm? Is it in raylib? Is it in Western? Spoiler, it's always in Western. That's why I put a big box around Western, so all the Western stuff stays in there. Never open that box, please. But yeah, now we can do stuff like this. We can know when you drop a frame, because every time we render, we get the v-blank ID of the screen itself. And if the v-blank, the diff is not 1 when you render, you technically drop a frame because you missed the opportunity to render a frame. The screen was ready, but you were not. And now, I will leave Shane to go on stage and talk to you more about simple stuff again.
How's it going, guys? That was a great talk by Maxime about the low-level graphic stack and how we simplified that. And I'm going to expand on that more on the raylib part, how we turned, yeah. So let's just start. So solving simplicity again. It's my idea that if you have simple code, and this goes both ways. If you have simple code, you can have a nice, simple life. So yeah. Nice, beautiful servers here. You can go surfing after this. Great. So, sorry to jump scare everybody so early in the morning. I know if you get this in your email, pull request closed by Adeeb, that can be scary. But yeah, before I started working at Comma, I was just a college student, and whenever I wanted to work on a project, a coding project, I didn't have any idea of making things simple. I just hacked together the first solution that worked, and I moved on. And maybe I came back months later, and it was totally impossible to reason about this code. It's just way too big. You can't keep it all in your head at once, and that's why you need to try to keep things simple. So how do we recognize whenever we're adding complexity where we don't need to? And that's recognition. You need to be self-aware enough to realize in the moment when you're doing this stuff. One case is, let's say you're adding something to the UI and you want to add an edge case. You want to support, maybe a user gets into a weird, we want to show an error message for this specific one case, and that adds 30 lines. Well, 20 lines. Or maybe you're adding a feature that you don't really need. Maybe you're making something abstract. You just want to add one feature, but you're oh, maybe in the future we want to do this other thing. So we make it generic, and that's just extra complexity that you don't need yet. And well, that looks good. That looks good, right? We're removing 1,000 lines. However, this is a tricky case because you're using a library, and while that can be good sometimes, I'm going to explore why that might not be. So we're going back, I think 8 years or so, back to 2016. Oh, whoops. We were basically running a souped-up Android phone. It was the comma.ai at the time, and we had a few APKs that we ran. One was, it was just black. It just drew a black frame for some reason. I think that was to hide the boot splash whenever we switched between the different UIs. One was the frame, so when you're on road, if it's green or not, if you're engaged or not. One was the off-road UI, so you could swipe, see your driving stats, whatnot, pair your device. I didn't know this, but apparently we had Spotify and Waze, which if you have CarPlay, I don't know why you need that. Maybe this is before CarPlay, but I guess you could just pair it. to your Bluetooth. And then on top of that, to draw the lane lines of the model, we had a different graphics stack called NanoVG, which is written in C. It's actually quite simple. So that was probably the best part of this stack. But you can see this is a lot of like working parts together, right? So a few years ago, we switched to a new stack, which is, whoa, I think there's some lag up here. It's Qt. And Qt is a nice graphics library at the time to switch off of, or to switch to, because it supports widgets. You know, if you want to like put some text, or if you want to like enter your password for your Wi-Fi, it's just all there. It's all coded for you. It has nice multi-language support, and if we go back to the graph there, if you saw, there was just way too much to reason about. You need a graph. Let's see if this works here. But anyway, you need a graph to like see the whole state of Qt. You can see you have like a tree widget. I don't even know what the hell half of this stuff is, but it's there, and this is probably just like a small subset of Qt. So this is the problem with using libraries sometimes. They do remove code. They do put the complexity out of your project. However, the problem is that you have to trust that this other developer, they didn't write bugs writing all this complex code. So if we can switch here, there it is. So complexity is a black box. And I'm going to briefly explain like a few cases we ran into while writing the new UI in Qt. So basically, the driving model for experimental mode, it like draws a path, and just like it's green if it wants to accelerate, red if it wants to brake, right? So we have this nice hue, which is a float, but for some reason, I found that if you don't round the float from another float to a slightly different float, it would take 2 times longer to draw the path, and I just never figured it out. I just ended up rounding it, which somehow worked, which is great, but it's just complexity. And complexity is a black box, right? And so black boxes require care. Another issue I ran into, so just one day, the Jenkins test, the hardware in the loop test, just started failing out of nowhere for high UI timings. And if you can see over there, it might be a little faint, but just some frames will take up to 300 milliseconds to render, where they should normally be under like 10 or 20. And while I was debugging this issue live, the lights in the openpilot office turned off, and the timings that I was seeing just like spiked. So what was actually happening was the model was just, on the comma.3x, was pointed against the wall, and it's basically either seeing light or dark. So when the light turned off, it was just outputting lane line geometries that were just totally, not totally wrong, but it just, the polygon renderer just couldn't convert it into like a nice triangle strip that the GPU could run. And it was just using this entirely different code path that it just doesn't tell you that it's doing in the moment. So that took a while to figure out. So how do we fix this? Well, as Maxime talked about earlier, we switched off Qt to Raylib, which is just like a simple OpenGL wrapper. It gives you a few functions, like you can just draw shapes and text. The entirety of Qt, I think I looked it up last night, it's like several million lines of code. And we just have a widget function ourselves, which is 200 lines of code. So that's a huge improvement. If you want to draw a nice icon, it just takes 4 lines right there. There's no dependencies, there's no build time. So what used to take a minute if you want to change a UI component is now instant. It's infinitely faster. And yeah, just who wants to fix other people's bugs, right? That's cringe. So how did we fix the original problem where the model was just outputting like lane line geometry that the Qt didn't know how to handle? You can just simply do less. So you can see Qt has this huge 3,000 line function just to triangulate polygons. And they might be like inverted or convex or whatever. And we don't need to support any of that. We just need a simple 4-line for loop. That's all you need. And it's way simpler. It's consistent. So yeah, that's one of the practical applications of switching to a smaller library where you can control the complexity yourself and you can remove the bugs yourself, which is very nice. So switching gears to the car interfacing, I think it's really cool how we support over 300 cars now, and that's growing every single day, right? And a lot of the car support comes from contributors like you guys, which is also really cool. But there's there could be a lot of complexity in that, right? You have to support all the different Hyundais support different harness, physical harness types, and as well as the software, the DVCs can be different per car. So how do we handle that? That seems like an impossible problem. Well, to give you guys some context, last year we had a daemon, controls D, and it pretty much does what you expect. It takes in CAN data from the car, runs it through the car interface suite, which is basically where's the steering angle and the gas and brakes. Runs it through some controllers. So based on the model, should it turn left or right now or accelerate? And then it outputs it back to the car. And however, Controls D also did a bunch of other stuff. It ran the state machine. If you're pressing the brake, should it disengage right now? Or if the model is uncertain, or if you're doing a lane change. So it's just doing a lot of stuff. This is pretty complex. To keep the whole file in your head is just also impossible. So what we did, and this seems pretty simple now, but this is how it was for 8+ years or so. We just took the car stuff out of openpilot, where it was all together. We moved it to a new project called OpenDVC, where the the DVC messages already existed, so it's just all in one place, which is really nice. And OpenDVC, what I just discussed, is a self-contained package that you can pip install right now. You can run all the tests. You can import all the cars. This wasn't possible before with OpenPilot. We're trying to make that nice and pip installable, but soon. So what OpenDVC does is it provides a very small API that OpenPilot can take, and it can read data from the car. It can send actuation messages to the car. But again, what this allowed us to do is look at this API and see, what is this message that we're reverse engineering for every single car? All we need to know is if the user is pressing the gas, but we're also reverse engineering how much they're pressing the gas, which you don't really need in terms of the state management. You just need to stop applying the brakes. So remove that field, and that's just one less thing that people have to reverse engineer now. And then also the 1-minute CI, as Maxime talked about, that was a requirement, and it was pretty easy. There was 8 different tests for OpenPilot, and just adding these onto it, it's just it's nice to have that separated. So one of the improvements that the smaller API allowed us to make was add a new tool called the longitudinal maneuver report. And that's a toggle built into OpenPilot. You can go into your settings, turn that on, and basically, before this, if you wanted to test longitudinal tuning improvements, you had to especially late at night, you have to find a lead car, maybe at a stoplight. You have to engage behind them, hope that they don't leave or run the red light, so you can get a nice stopping profile, and then you feel did that feel good? Did it overshoot on the brakes? Whatever. But now we can recreate real scenarios. Let's see. Ooh, laser pointer. So gas brake. You can see the Camry is overshooting on the brakes a little bit, undershooting and then overshooting on the gas. Corolla looks like it overshoots a whole lot. The EV6 is pretty good. So this just allows us to quantify the actual performance of the different cars that we support. And what that allows us to do is we can make very targeted changes to the tuning. So if we want to improve the gas response on Toyota, help that not overshoot as much, we can make those changes and rerun that part of the report and see that if it improves it, if it makes no change, or not. And it's really cool because you can see some of these are user reports. So you want to run this tool again, it's just in your settings. And you can upload the data to this website right here, and maybe somebody will tune your car if you can't. And one improvement from that, so this is the simplicity thing, like Maxime said, it all goes full circle. So you have this API that you make smaller because you're reasoning about it now. You're trying to make it simpler. Then you build this tool to use that new API, and now you can actually merge improvements based on that. So a contributor in 2020 found this bit in the reverse engineered DVC for Toyota that improves the gas response. However, it also disables braking, and it makes it overshoot sometimes. So we didn't merge it until just this year. Yeah, I think just this year. And that was because of the report that we had. So on the Corolla, starting from a stop, it took up to, looks like, more than 4 seconds to move. And now, after we tested the bit, we can actually see that it follows the acceleration request much better. So yeah, if anything, if you found any of this interesting, you can port your new car. You can help us make the API simpler. You can also get paid if you go to the Bounties website, which is really nice. So my final message is if you too can simplify your code, maybe one day you can merge your PR and Adeeb will approve it. Thank you.
Hi, thank you so much, Maxime and Shane. Amazing talk from the openpilot team. Next, I'm very excited to welcome Yassine, our head of machine learning. He will be here momentarily when he gets mic'd up, so I'll just give a few housekeeping notes before we get started with our next talk. There is still coffee in the back, so feel free to grab a coffee. And then we will have lunch served at about 12:45, which will be served in the entrance where everyone came in.
Hello everyone, hi. Let me see. Let's check the clicker. Clicker is almost AGI level technology, so we should. Alright, works. Reach AGI. Hi, my name is Yassine from the autonomy team at Comma. And today we're going to talk about machine learning. I'm here to talk to you about not any kind of machine learning, a very exciting style of machine learning that we call end-to-end. We're all familiar with it right now. Everybody's talking about end-to-end. It's all what the craze about. All the cool kids are doing end-to-end machine learning. So I'm here to spill the tea and tell you all what it is. What's end-to-end machine learning? So if you're here, you probably already know what openpilot is. We ship openpilot, open source L2 ADAS system that runs on the comma.ai. It has tons of users, many of whom are here, I think. A lot of supported cars, more than 300 supported cars. And recently, Linus Tech Tips said that it was amazing. So I guess if you guys trust Linus Tech Tips, I think it's amazing. As a famous person said while looking at a car, they said that it was all computers. What I like to say is, well, it's more than that. What we ship, it's all machine learning. So we ship this device to you called the comma.ai. It has cameras all around, and it runs on a car that has some sensors and it has some actuators. And then everything gets blended into this crazy linear algebra that we call machine learning, and then drives your car. That's magical, right? It's amazing. I think it's cool. Well, it's especially cool because we are doing it end-to-end. And I'm here to explain to you what end-to-end means to us and why it's important. So in general, what we call end-to-end is what the general literature called general purpose methods. So these methods, what you want them to scale with is compute and data. You don't want them to scale with lines of code, and you don't want them to scale with numbers of engineers. So you don't want to be in the situation where you need to ship a new feature or you need to improve your system, And the only solution is, well, I need to write more code. Or, oh, wait, I need to hire a labeler. Or I need to hire an engineer. That's not what you want to be in. You want to be in a state where, well, I need to make this model better. I need to improve performance. The best way to do it is, well, I need to make this model bigger. Or I need to train it for longer. I need to train it on more data. So that's what we call general purpose methods. And this little guy over there, his name's Rich Sutton. And that's a photo of our data center, built by our friends, Tiny. And they have a booth right over there if you guys want to visit it, with some cool exposition hardware. So that's our data center, and we want to scale with data. We want to scale with compute, not with people and lines of code. As I said, all the cool kids are doing end-to-end, right? Even people that were not doing end-to-end a few years ago now are talking about it as if it was, you know, the only way to do it, and as if they always did it, which is fine. It's good to for people to get you know, convinced and change their opinions, but it's great. So yeah, the cool kids are doing end-to-end. Tesla is doing end-to-end. Even Waymo is doing end-to-end. Robotics companies are doing end-to-end as well. You know, everybody's doing end-to-end. But you see this. Oh, sorry. These kind of job postings. A data labeler job posting. Oh. Well, that's odd. It's not really end-to-end, is it? Or even outside of the robotics, even outside of the self-driving you know, space, you see these kind of jobs like evaluator experts, prompt specialists, optimizer. There's a lot of hand coding still, but these models are end-to-end, right? Well, how you train them is very important. They can be end-to-end, but the way you train these models might not be end-to-end. You might still need effort, you might still need people, you might still need intermediary steps to train these models, which kind of defeats the idea of end-to-end. But sometimes you see things like this, which are great. Sometimes you see these in the news. AI achieves silver medal in the Olympiads. That's great. And these are the things, these are the methods that I'd like to call end-to-end, because these not really rely on human data, human labelers, or prompt specialists, or prompt engineers, or evaluators. These models were trained using reinforcement learning. These models were trained using experience, not using data labeled by people. Why is this important? A few years ago, we were doing prediction. 2016, 2018 was all about ImageNet, it was all about predicting class labels, predicting lane lines, predicting this and that. Well, now it's the grown-up stuff. Now you need to take action. Now you need to act on your predictions, and this is what makes it hard. It's not just about saying things about the world. It's about interacting with the world, making actions, and then observing what happens and being robust to that. Welcome to the era of experience. This is where we're at, and this is what we are doing right now as a company. We are building agents, driving agents, that act in the world, that act in a car, and we want them to learn how to drive from experience too, because that's how people learn, and that's how you reach superhuman capabilities. Again, the case for end-to-end is comma. This is a photo of last Comic-Con 2 years ago. As you can see, not a lot of people in this photo. This is the entire company, and you get to meet us all today. This I think is the entire company at Comma today, yes. So yeah, not a lot of people. End-to-end and general methods and the bitter lesson in general is the reason why a company like Comma exists, is the reason why we get to exist in a world where other people are throwing money from the window at labelers and things like that, while we are trying to solve it in a principled way, in a way that scales with compute and data and experience. So, thanks to the bitter lesson. So, enough general and philosophical talk. I'm going to dive into some concrete problems and concrete examples of how these general methods and these end-to-end methods were used and are used by Comma to solve some concrete problems. So I want to start with driver monitoring. DM, as we like to call it, is how we make sure that the driver in the car is alert and not sleeping, not using their phone, while the comma.3x is driving, while the ADAS system is driving, because it's an L2 system. So we need the driver, the user, to be alert and ready to take over at all time. I'm sorry to bring this up this early. Bad memories, but I want to start with this and get this over with, so that we get the bad memories out of the picture. Do you all remember 2020? No. Tough year, right? Well, we had this thing called surgical masks and face masks, and suddenly people started wearing masks all the time, even in their cars. We have Uber drivers and things like that. So, but that wasn't that common, right? People weren't wearing masks in the past in their cars, so face masks. So it was out of the distribution of the training data of the DM models, the DM driving model, the DM machine learning models. So we had to fix that fast. Everybody was locked down. We couldn't, bring labelers or take photos of people and do this, how people do it usually. So we had to be a little creative. This is Wishing, is over there. So, an easy way to do it is to create synthetic data procedurally, not using, not using an artist, not calling someone to paste a mask on a face, or not using Photoshop. We're not hiring models to wear a mask and then take pictures of them. No, we use our existing data, and we use some general methods, some easy to implement general methods to estimate the pose. This, again, was done using a machine learning model that's trained. We're not using a labeler to give us the face pose. Same thing with the landmark detection. We kind of delineate where the face is. And then using these two information and these two sources of information, plus a mask that you can download from Google Images, and then you just add the two images, and here you go. You have a new data set of someone wearing a mask and driving. That's great. So again, this example, I like to bring this one up because you could solve it in a completely different way if you didn't want to use a general method. You would solve it probably by hiring an artist, a Photoshop artist, or by hiring some models, or by trying to wait for people to start wearing a mask and then collect more data. But we had to act fast. So we went the general way, and that worked out great. Another example I'd like to bring up, this looks a little creepy here, but we used to call this the eye shutter. The eye shutter is, well, the models didn't really detect when people were closing their eyes that well. So, and we didn't have a lot of data of eyes that were shut, because when you shut your eye, it's pretty fast, and then the data doesn't really have that class balance we used to call. So again, you get the eye landmarks using a neural network. There's plenty of them online that you can download, or you can train your own. and then using some simple morphological operations, you can just close the eye, and there you go. You have a photo of an eye that's closed from a photo of an eye that's open. And again, this is really a simple method, general, and that scales with data, and it's you just inflate your data set very easily without trying to call artists, without Photoshop artists, for example. More recently, there's these things called VLMs, or vision language models, that you can give them a prompt and an image, and then they can interact with you, right? So with some very little prompt engineering, you can put a photo of someone driving and using their phone, and then ask the VLM, say yes if the person is distracted from driving because they're using their phone, and the VLM knows Adeeb's using his phone. So yes, this is a more recent way to deal with this, and we're experimenting with how to use like larger and more subsequent models that are trained on tons and tons of data to automatically label some of our training set, which is what I like to call vibe labeling. That's a live photo of Wishing over there. So something more interesting about DM is that we also know the future, and that's the case also with our driving data, is that you know the future. You know if someone is going to take over or not in the future. You know if they're going to override the steering wheel, we call it override, or you take over. So if the person took over in the future, that means they were ready to take control, right? Because they did take control in the future. Or let's say if they're just sitting around in traffic, usually you're not really aware of what's happening around you when you're in traffic. You can look at your phone, you can look down, you can be distracted. So the probability of you being distracted or not ready to take control when you're sitting stand still is generally higher. And then the rest, we say we mask it out. So it's obviously not just these two cases that exist. There's tons and tons of other cases, but we can label a small amount of our data using these heuristic data that comes from the future or that comes from other sensors around the car, and then the other stuff we just don't care about it. So even with a really, really small percentage of what this covers, we can find some interesting examples, like the one that I'm going to send you here. I don't know if you can see, but this is a photo of me driving, and am I ready to take control? That's an interesting question. I mean, I'm looking at the road. Looks normal. And yes, I'm ready to take control because in the future I did take control. So that's I did override. So that's a good example. In here, am I ready to take control or not? Obviously not. I'm looking down on my phone. I don't look that interested in what's happening around me. Well, yes, because I'm at a gas station waiting for someone to come back to the car. So in this case, yes, I'm not ready to take control, and the reason why is because I'm in standstill. So we call these end-to-end labels, and they cover a really, really small percentage of our data, but it's enough to get some really good signals and to get some interesting examples as well from our data set. And yeah, all this shipped up by Wishing and maintained by Wishing, which is over here. So the idea is that you can ship and create really good systems and really reliable machine learning models using a very, very small team if you go the route of general methods, and if you don't get trapped into this trap of needing more features or improving the system using labelers and using stuff that doesn't really scale. So yes, shipped and maintained by Wishing. Next example is what we call lateral control simulation. I forgot to ask, who's here is an openpilot user? Right, hands. Whoa, nice. Who's heard about tuning? Oh, okay, cool. Yeah. So what's the deal with lateral control? With lateral control in general? This is from a really nice forum from our friends at SunnyPilot, which are here and have a booth. So you guys are welcome to go visit them. This model has been fantastic on my Hyundai, Kia, Genesis Angle steering car. Finally drove this model and lat long, both perform really good, smooth turns, but some hugging, nothing too crazy. I can't use this model because it hugs left too much. To me, this model is okay, but it kind of turns too much and too quickly. I don't like it. With my Toyota, lateral is not good. I actually thought this was a step up. Yeah, so the thing is, we support a lot of cars. We support more than 300 car models. And every car and every model has its own quirk and feature. And these quirks and features materialize in lateral control. The idea is that we control the car, some of our cars, using torque. So you put in torque on the steering wheel, and then you observe a lateral acceleration. And the difficulty is the predictability of this function. How does this translate to that? And that depends on so many things. That depends on your car, your model, how much your tires are inflated, how the road is rolled, and is the road wet? Is it not wet? Is your steering rack old? How old is it? So it's really complex, and it's a really difficult thing to model, and that's why you hear about things like tuning, hugging, turn cutting, things like, oh, this performed well on my car, and then someone else says, well, this didn't perform well on my car. Well, it's because of this, partly because of this. So how do we solve this? We could do this for every car. We could have a Python file for every car, and then kind of try to like hard code this using some Python code, using some C++ code maybe. Or we could just write this as a big problem, big machine learning problem. So you have your input observations, and then your input states. And then we're gonna come back to a style of slides that are like this a lot in this presentation. So you have inputs that are observations in time, and states in time, and actions in time, in the past, in your context. And then what you want to output is the next state. What, given these observations, and given what you observed, and given some actions you took, what are you going to observe next? And we all know the only way to solve machine learning problems is using the transformer architecture. Right? That's how we do it. That's how all the cool kids do it. What's a transformer? Not gonna talk about it that much today, but it's a stack of layers that we just repeat a number of times, and then you get to repeat them a lot. And the more you repeat them, the bigger these layers become, the more parameters or weights you end up with, and the bigger the model you end up with. And that's how you hear like, oh, this model is 3 billion parameters, this model is 5 billion parameters. Well, it's essentially how many of these layers do you have. And the transformer, not this one, the machine learning architecture, is trained to predict a set of numbers shifted by 1. So the transformer takes a set of context number and then shift them by 1, and essentially tries to predict the future, which is really cool because that's what we want to do, right? We have a set of observations, a set of states, and you want to predict the next state. It's great. and it magically works. The red line follows the green line, or the cyan line. That's great. So yeah, we train these big models using our data sets, and they do predict whatever we're interested in, and that is wonderful. Now, how do we use this? In the autonomy team, we have this rule called no testing in cars. It's inefficient. You have to go downstairs. You have to start the car. Sometimes the car is off. Sometimes you need to pull the branch. Oh wait, didn't have the right key. Someone took the key. Oh, someone took the car. The car is in the car wash. So yeah, it's inefficient. You don't want to do that. So what this enables us to do is, well, you can start with the segment that, let's say, with the driving data that's on a Toyota, and then simulate as if it was coming from a Hyundai, or simulate as if it was coming from another car. And then you can see how the model behaves using different cars, using different, what we call noise models, that come from different platforms, which is really cool. So you can see, like, this is one segment that's replayed. I think it was originally from a Kia EV6, and then we changed the noise model so that it will match a Bolt, or it will match a Corolla, which is really cool. So you can just like swap the car without going downstairs. And this is shipped and maintained by Casper and David. And over there, they have a booth where you can actually drive with a noise model from which car? Oh, you can pick the car. Yeah. So you can actually drive using a joystick and observe what the model is living every day, or is observing every day. And it's a really fun booth over there with the steering wheel and the TV. So you can get to experience what the model experiences in real life. All right, now to driving models. So this is the model that drives the car. This is the model that outputs a desired curvature and desired acceleration, given the camera views. And recently we wrote a paper called "Learning to Drive from a World Model," and it really shows how we want to solve, or how we are currently solving, the problem of training driving agents end to end from experience. This is from a screenshot from our blog post, where we describe in large details how we do this, and I encourage you to go check it out. It's in our blog, and you can also read the paper. You can look at the slides. Even the talk is published, and we have a really nice interactive blog post where you can click and play and kind of interact with the word model that we train. What's a word model? Word model is something that something of a buzzword right now. Everybody's talking about it. Like, people are talking about end-to-end. People are talking about word models. Again, a word model is something that is a model that takes in previous states, previous observations, and previous actions, and predicts what is the next state, what's going to happen to the world that you're observing, given what happened in the past and given an action. And it's really important because some really smart people are saying that it's important. That's it. No, it's important because it really allows us to interact with the world and generate these experiences, and give the opportunity to the model to interact with the world without actually interacting with the real world, because that would be expensive. You don't want to put a model that's not trained, put it in a car, and then go to, just go and try things and come back with some data, and then do some gradient descent on that data, and then send the model back. You don't want that. You want some kind of simulator. You want some kind of world model that enables you to do this in the data center instead of the real world. So our world model is essentially two models. One of them is a model that takes in the observations and compresses them in what we call a latent space or latent vector. And this compression here is important because we use that compressed feature set as a set of observations, and then the world model, which is a diffusion model, is trained to predict the next state, trained to predict the next latent vectors. And there's some details about how these models are trained using the latest tricks and the latest cool stuff in machine learning, which I'm not going to go into much details today. So if you're interested, just go in the paper and then you can read how all these models are trained in large detail. Again, inputs, outputs, action. So input is the state. It's the camera, essentially, the camera feed, Fcam and the Ecam. The action is what we call the pose, or the position update, which is a vector of translation and rotation, a 6 degrees of freedom input. And then the output of this model is also what is the next frame. So what's the world going to look like given the past, the action that I took? What's the world going to look like after that? So things move around you move around. So it should predict that accurately. But also, we want this world model to tell us something about driving, not just the world, because this is a very special type of model. This is what we call an action world model. We are asking the world model to also tell us how to drive in this world, how to drive in this future world that I'm going to imaginate. What is the best path? What is the best curvature? And what is the best acceleration to take, given what you did in the past and given what the future is going to look like? So this is a special type of model. It's future anchored to kind of give it some more recovery pressure. And again, all the details of why we do this and how we do this are in the paper. So I encourage you to go check that out. So we use these world models as a simulator. Again, same. I've said this before. You get past frames, and you get an action in the past. You get an action, and then the driving simulator, the world model predicts what is the next frame, and also what is the next action. You can use this next action as you want. You can use it as ground truth to train a different model, which is what we do, or you can just use it, feed it back into itself, and do it auto-regressively to kind of like do a rollout of a simulation. And these models are great. They scale with data, as you can see. LPIPS is a metric of how good the image looks like. So the lower the LPIPS, the better. So yes, more layers, a better model, or a bigger data set, better model, which is what we want. Great. Rich Sutton's happy. Also, this model is this is a very important thing to us. And when you train a model that wants to drive a car, you want it to be physically accurate. You want it to, if you ask it to move 0.5 meters to the right, you need it to actually move 0.5 meters to the right, not 0.25. You don't want to wing this, right? This is driving, this is serious stuff. When you're doing a video game and you move it, you ask the player to move a little bit to the right, you don't really care how much you move to the right? But in driving, you really need to be physically accurate. So we have this benchmark tests that starts in the lane center and then ask the model to move to the right, and then you know exactly how much how much the model moved using a different model. So you can check whether the model is physically accurate, and with a lot of care about how you train and use these models, you can make them physically accurate. Also, they generalize out of distribution, which is pretty cool. Look at this crazy swerve. Wow. I hope no one did this in our data set. I think no one did this. You all are very responsible. So yeah, as you can see, we really ask it to go very, very far off the road on the shoulder, and it responds to that pretty accurately. So we say that it generalizes our distribution. And if this plays, yes, this is a very long video, so I'm not gonna make you watch 8 minutes of rollouts, what we call rollouts, but this is essentially how the word model, how the simulated videos look like. Yeah, as you can see, all these videos are simulated, they're not real. The top one is the frame that comes from the narrow view camera, we call it the F-cam, and the bottom frame is one that's generated, it's also simulated, and it comes from the wide angle camera. So you can also see how consistent the views are and how the movement looks consistent between these two frames. They're generated by the same model. It's one model that generates both frames in one shot. So you can see how consistent they are, and there's a little installation over there in the TV where you can see this loop around with some fun captions that we all wrote before every video. So I'm not gonna make you watch all this now. If you wanna see some examples, they're in the TV back there near the coffee stand. Yeah. And we use this model. We use this word model that generates simulated worlds and simulated environments to train on policy and to generate experiences. And we describe this in our paper, and essentially that's what I said earlier. We start with past frames with an action. The driving simulator, the word model, gives us a next frame and the next action. We use the next frame to feed it back in, and we use this action that the word model tells us, hey, this is what I recommend you to do. We use this as ground truth for a different model that we call the policy, and that is our ground truth. We use it to train the policy, and then we do this over and over again. The policy gets better and better at driving, and that's how we ship the models right now in openpilot. No secrets. This is a very just a little fancier way to describe what I just said. And shipped and maintained by Harald, Armand, and myself, and generally other people from the autonomy team. So yeah, that was the driving model. Now this translates really easily to other types of robotics problems. So driving is a robotic problem. It's a very simple robotics problem where you just actuate using two numbers, curvature or torque and acceleration. But things can get a little messy for general autonomy. Do you all know Billy? Who knows Billy here? Oh, cool. A few fans. Billy's our friend. A comma body. A comma body is looks like this. It's a comma 3x on a stick on a hoverboard, and it's a robot. So we use the same approach that I just described for driving. We used it for general indoor navigation types of problems. So the goal is, well, you need to make Billy roam around the office, avoid objects, and if it hits an object, or if it gets stuck, it needs to recover autonomously and avoid collisions, obviously. So we open sourced a data set of indoor navigation using the comma body, using Billy in our office. So it's a few gigabytes of driving around, of roaming around the office. And it's open source. And the problem here, simple. You have inputs, observations of camera inputs, and then you can also look at the wheel speeds. That's also nice to have. And the actions are the WASD, the WASD inputs, for the gamers right here. And then the output is, again, what's the next frame going to look like? What's the world going to look like given this past observations and action? And also, what's the next action that you should take? So, as you can see, this kind of works. It recovers. This is our kitchen. This is the openpilot lounge. So you can see it kind of moves around, bumps into people, tries to recover. Here you go, it backs up. So this is all end-to-end. This is the model that is trained to predict the future and to predict the next action and recovers. So this is a short way to show you how these kind of approaches that don't really hard code things, I don't know if I said this, but I probably said this in a previous presentation, is that there in no way, in no place in our code, you will find traffic lights or cone, only in our tests. Some of our tests kind of like tries to find segments with or data with cones and sees interesting ways to evaluate the model, but in our training code, we don't really hard code anything about driving. Everything is learned by this model, so all the behavior, all the driving is done implicitly. We don't hard code anything. We don't hard code lane lines, we don't hard code any of that. So if we just put that, to just swap the data set, swap it with the data set of indoor navigation and a robot, it just magically works. So again, general methods work and generalize to different kinds of problems, which is great. And also we open source this model. Yeah, this model is open source. So if you have a comma body, you could just try it out at home and see if it avoids your coffee machine, or see if it avoids your fancy couch. Now, can you do this for input for manipulation? So this is an SO ARM 100. It's an open source kind of 3D printed ARM, and yeah, same thing. We tried to do this. We open source a data set of something that I like to call the coffee test, which is just grabbing a coffee pod, a Keurig pod, and then put it in this little tray. And you can train a model. I didn't do this, but you can train a model using this data set and to do this autonomously using the ARM. Okay. And this was shipped and maintained by Armand, which is also here, Casper, and myself. And while I'm here, I would like to advertise something that we haven't published yet, but we will do very, very soon. And I know you guys are like compression a lot. I don't know why people love compression. So we're doing a new compression challenge. We've done one in the past that we called the comma VQ challenge. This is called the comma 2K19 compression challenge, and it's essentially a new style of compression problem. So stay tuned for that. It's going to be a very fun challenge for everyone who likes to do some coding, likes to do some challenges. So the idea is to compress videos, make the video size small, but with a very different goal of not making the image look good, but actually preserving semantic content and temporal dynamics. That's it. You can make the image look as bad as you want, but as long as when you put that image into a segnet or into a posenet, it predicts the right stuff. So you could do whatever you want to that image, as long as the segmentation model and the pose model is fooled by your compression, you're good to go. And the cool thing with this challenge is that we open source the segnet that we use, so it's going to be open sourced, and we also open source a posenet. So it's going to come very soon. Stay tuned. So yeah, we're open sourcing all this for the challenge, and you get to play a little bit with the compression and plot things like rate distortion curves and do sciencey stuff if you want. So yeah, stay tuned for the comma 2K compression challenge. And also stick around for more talks about autonomy and research and machine learning. Harald's going to talk later about how we bootstrap very useful robots today. And Mitchell is going to talk about building a 1,000,000-mile data set. Any questions?
Thank you, Yassine. All right, amazing. We're going to take some questions from the audience. Do I have any questions? Hands raised.
How do you evaluate your world model? I mean, you must be getting better every day. Like, how do you evaluate what you're getting better on?
Yes, so we have tests for the world model. We described that a lot in the paper, but in general, what you care about is image quality, how well the image looks like as output for the world model, how good the video is, not just the image, because we do this auto-regressively. So you want the world model to generate good videos, not just good images. So that's the two first things. And then you also want the world model to be physically accurate. So we have this other part of you control the world model using some fake actions, and then you see how well the world model responds to those fake actions. So we have these dual kind of world model evaluation.
All right, more questions?
Hi, so I assume that your world model is stereo aware and temporally consistent, because I think it has to be useful, but you guys use two mismatched sensors and lenses. So I guess my question would be, how much of that is, I guess, generalizable if you wanted to change the sensor or lens in a future comma device? How much of your model could be reused, and how much of it would you just have to remake from scratch?
Yeah, that's a very good question. So, yeah, most of the models will need to be retrained if you add a new sensor. But we also do some kind of pre-training of the world model that is independent on the number of sensors, for example, things like that. So, or the temporal context, or how big the temporal context is. So there are things that we can change in our architecture today that don't require retraining everything. But yeah, adding a new sensor, adding a new observation vector to the state will need retraining, which is fine.
Another question?
Hey, did you have a version of experiment where the world model is just predicting the actions and not necessarily the visual cues? And does it really help to have both the visual cues and the actions predicted together?
The short answer is yes. It does help. Yeah. So you can train a model that doesn't even input the images, right? And it only outputs the future actions. But yes, outputting the images and the actions makes the model more accurate, and it generally makes it more intelligent, basically. Yes.
We can take a few more questions. Any more questions for Yassine?
So is the next frame prediction also happening during inference on device, or is that just to train a world model for pre-training, I guess?
Yes, so the next frame prediction is not done on device. It's not in the back end, and we use it just to train the policy model, which is a much smaller model. And you can see this as a little model, a small model that plays inside the dreams of this bigger model, the world model, and gets distilled, learns a little bit from the big model, and then that's the policy model is what we shipped.
Okay, very cool.
And that one does not predict the next frame, yeah. Only predicts the next action.
Thank you.
Any more questions?
When you were using visual language model to determine if a person has a phone or not, how accurate was it? For example, a person had a hat or didn't have anything.
Yes, so we used it in a very specific case where it was very easy to label, because it was just asking about a phone, whether a phone was in the frame or not. And it was pretty accurate from what I recall. because you can see the phone in the frame. It's pretty easy to see. Some people do have some very creative ways to hide their phones, but as long as you can see it, the VRM usually sees it pretty easily. But yeah, you have to be careful with the prompt, with the question that you ask. Like the question that we asked in this case was very simple. It was about, was there a phone usage or not? But if you ask it, for example, is the person looking at the road? Well, I don't know. Is it the road that they're looking at, or is it the dash, or is it the steering wheel? You don't really know. So the VRMs doesn't know these kind of things. But for phone usage, or I think sleeping detection as well, these visual language models would do very well.
Okay, thank you.
We'll take one more question.
Thank you. You mentioned you have this world model that is predicting the action, but then you're kind of doing some like pseudo distillation with this on-policy smaller model. So I assume the bigger model would benefit from data of all cars, but then you can distill according to each separate car that you want to deploy on. So the smaller model would only see data from that specific car model. Is that the case?
We could do that. We don't do that.
Then what's the benefit of like retraining an on-policy model? Is it just for inference speed reasons?
Well, the first reason is that the word model is not causal. By not causal, it means that it needs the future. That's what I wrote in my slide called the future anchoring. So the word model cannot be shipped on device for this first reason. This very fundamental reason is that you don't know the future when you drive. So you need to distill it into a causal model, which doesn't know the future and can act. So that's the first reason. The second reason is, it's too big. So even if we had a causal model, we would not be able to ship it on a device. So we still need to distill it in a smaller model. And why we don't do this for every car? Well, it doesn't really make sense. You want a policy model to know how to drive in general. This is not a car-specific problem. This is a driving understanding of the scene problem. So the policy should be really independent and should be robust to these different types of cars and makes and models. And then the controls is what deals with the differences. So yeah. There was one last question.
One more question.
Yeah.
Would having more real-world data as opposed to synthetic data improve model quality? And is there a way to assess that? Did you do that?
Yeah, so the word model benefits from real-world data, yes. The more real-world data that you train it with, the better the word model is. And then you use that word model to generate synthetic data for the policy. Yes, so real-world data is still very, very useful because we use it to train these word models that are very, very big and very data hungry. So yeah, definitely.
Thank you so much, Yassine.
Thanks.
We'll be able to take more questions after all the talks. We'll have a Q&A with all of the teams, so you'll have the whole autonomy team on the stage. So if you have burning questions, you can keep those for later. This is Adeeb, our Chief Product Officer. Welcome to the stage, and you're good to go.
Okay, that wasn't supposed to start like that. Clearly, this company's got work to do on live streams and presentations. Now that the cat's out of the bag, though, we'll get through it quickly. I want to talk to you guys about the product. I want this to be a little more interactive. I know you guys want lunch. Julie, do you know how to go back? All right, we figured it out. All right, good morning, everybody. Thanks for coming here. We know most of you aren't native to San Diego, so we really appreciate you guys coming out. As you can see, Comic-Con has a slightly different vibe this year. We had 2 previous Comic-Cons, and this one's a bit different. Comma's 10 years old, like Harald was saying. And I hope you get the vibe from both the event and everything you see here today. Things are about to start looking a little different. Things are starting to work. And I just walked in today, and I just got that feeling. I saw the renders of this space, and I came in, and it just felt right. So I want to give a big shout out to our ops team, Julie and Carly, who put together this event. If you guys give them a round of applause. And another shout out for Nick, our new arts and crafts guy. You'll see a lot of his work today. This event was one of them. You'll see, we saw it. All right, so obviously a funny title. My talk will start with a short little clip from 4 months ago. We'll watch that together, we'll discuss it, and then we'll get into it. It's supposed to autoplay. Do you guys have like any way to control this? Right here. All right. George, if you want to reenact this clip real quick. I know it's putting you on the spot here. Thanks, George. We got creative workarounds for technical difficulties. So 4 months ago, we had a nice sale, $7.99. Many of you who were here with us for our first Comic-Con and the previous Comic-Con know that's an incredible deal. This is the same Comma 3 we launched in 2021, 4 years ago at the first Comic-Con. Just refined. Refined many, many times. This is the first time we got a 7 in front of the product number since before I was at Comma. And the sale did really well. We started a bit before 4th of July, and then the Linus Tech Tips video came out. 10x the views. There's good news and bad news with this. The good news, Linus liked it. They found the product on their own. We didn't ship it to them. They briefly reached out, I think, once about like doing a review, and we're like, you can buy it if you want. And that was about it. We found out they were doing the review from the WAN show like everybody else. We're like, cool. We had not expected to drop during our big sale. We had already sold hundreds and hundreds of devices. I think close to 1,000 at that point. We were running out of stock. The bad news, we weren't ready. We were running out of stock. If we got 10x the sales, we're just not ready for it. We'll talk about why. So I'm sure everybody here knows the phrase, works on my machine. Everybody's done something that works on their machine. This is a bit what Shane was talking about before he joined Comma. You know, everybody's good at making something work on my machine. That's the easy part. And everything starts this way. This is Comma in 2016. There's one accurate ILX. There's many demos on YouTube. You can see Bloomberg drive with it. I think George drove with it on the highways. It worked like pretty well. And then there's the ideal, like what works? What are we working towards? Once you've built something that's valuable and you have to productionize it, what's the ideal? Something like a rock. It's a little dark here, but this is a rock. It's a nice looking rock. And rocks just work. Sometimes my team asks me, when they're working on a project, I'm like, all right, does it work yet? And they're like, well, what do you mean does it work? Okay, if we like sent it to Linus or we sent it to somebody, or if I just go and try it and you're not sitting here, does it work? The rock always works. And that's kind of what we're working towards with everything at Comma. Like robustness is the whole problem, it's all the value. So many of you know, Consumer Reports is one of our big claims to fame as far as third parties reviewing OpenPilot. They reviewed OpenPilot in 2020 on the Comma 2, and I believe they reviewed it with a Corolla, and they gave it their highest score. Super Cruise was number 2. Super Cruise was a good system at the time. It still is a pretty decent system. As far as I know, it hasn't changed much. Gave Autopilot number 3. We would say OpenPilot was the best system at the time, and we still refer to this one today. What many don't know is there's a 2022 version of Consumer Reports. And I think many people in the company don't know this. Maybe weren't around then, or they just weren't in the loop. Do you know why nobody saw the 2022 version of Consumer Reports? Does anybody have any guesses? They bought the device. They got a car. They bought a car for the device. They plugged it in. It had CanFD. And they needed a red panda. And they plugged it in wrong. You guys remember the iPhone 4 and that you're not holding it wrong? They tried. They put a genuine effort into, they bought a car. They put it in their lab. They bought the device. They figured out they needed a red panda. They bought all these extra wires. They plugged it in. And there's a bug in the red panda. If you plug it in wrong, then we fixed the bug. But in early red pandas, there was a bug. That's it. That's your red panda. When they reached out, we didn't know they were doing this. They reached out after they broke the red panda. And remember we said with Linus, we didn't interact with him. They figured it all out on their own. When they reached out, we rush shipped them a new red panda. We had just merged support for their car, so it's totally new. We found their fingerprint in the logs. We added it to openpilot. We retuned their lateral control in their car. This was in the early days of Torque D, for those of you familiar with that. The stuff Yassine was mentioning with lateral control simulation, that's a very advanced version of it. And then we also added alpha longitudinal support for their car. And then I remember the next email we got. It says, do we want to run the devel or devel staging branch? I was like, okay. And so Alex was the one communicating with them. She was our CEO. And she didn't know the answer to this question. I would suspect like maybe 3 people in the company knew the answer to this question. Like, why? Works on my machine. That's why you didn't see the 2022 version of Consumer Reports. So I love shipping things. I learned this at Comma, and I just want to share some cool lessons with you guys about shipping things. I'm a real junkie for that green check. Anytime I can get that green check, click merge, and I see it on master, I just love it. Shipping devices, shipping commits. Well, there's just like deleting a few lines, fixing a typo. You ship something, and it's in master, and it's there forever. It's version controlled, it's open source. Like you pushed it forward. This is one of the coolest lessons I've learned here. Quality is basically free. A few months ago, we're talking to our display manufacturer, and I'm like, it'd be really cool. I'm really annoyed my iPhone. The oleophobic coating kind of wears. You can really see it on your comma in the sunlight. Can we just pay like $5 more for like a really awesome oleophobic coating? For those of you who don't know, the oleophobic coating is what prevents the smudges on your comma. And these coatings wear on all products. Anything with a touchscreen, it lasts for a little bit and then it wears. I was like, can we just pay more dollars? Does it scale like that? Turns out it doesn't. Here's an example of this. This is our brand new OBDC cable. It's a very nice drawing. You can see nice comma logo. We put OBDC, it's a custom mold. And this is an OBDC cable. So OBDC is based on USB 3.1 Gen 2, which means you need most of the wires, basically. And if you've ever used a USB 3, like a Thunderbolt cable, it's not very flexible, right? But you ever use your phone charger, very flexible, because it has 4 wires. It's USB 2. We managed to make this USB 2 levels of flexibility just to tune up the install a bit, and it's cheaper than the old OBDC cable. All we have to do is look at it, and we're like, oh, okay, we don't need these wires. We don't need the shielding on this. That's just for USB. OBDC does not need this. We changed the mold. We changed the whole overmold on the wire portion. It's a lot more flexible now. It's just a nice wire. And it costs less money. The old cable was $4, and it's just like a standard off-the-shelf OBDC, USB-C. This is an OBDC. It costs $306, and it's just so much better. It's the right thing for a comma. I just think this is one of the coolest lessons. Quality is basically free. You just gotta care a little bit. You gotta look at it. Here's another one of the cool lessons. So I started when we were shipping the Comma 2. I had a 27% failure rate. And when we shipped the Comma 3, we wanted to do a lot better than this. It's not a good time for anybody. Nobody likes this. Nobody likes dealing with the warranty. And one of my ways for dealing with this was, okay, I'll get every device back from support, and it'll pile up on my desk, and it's kind of annoying. You have some physical constraint, right? I come into work, and then there's all these devices on my desk. And to get any work done, I gotta look through them and look at them, right? The cool thing about failures and reliability is, as long as you don't regress things and you're very careful, it's finite. It's not some super complicated bug or anything. It's just a finite list, which is really cool. And it works out to be 12-ish things. And they're not equally distributed, of course, but it's like a finite list. You like look at them, you fix the problem, and then it's like good. You just don't regress it. So I'm going to show you guys the highest leverage thing we've ever done to address our failure rate. It might surprise you. It's one line of code. Assert, this is the literal code from fulfillment. Assert device pass all tests, serial number. That's it. So it turned out we had this really fancy provisioning software. You guys know about our stress tests. We have something cool coming up too about this. We had really fancy provisioning software, catch all sorts of crazy stuff. We really stress these chips. We run them at max power. We check that the GPS signal integrity is all good. We make sure every device passes this insanely high bar. And then what would happen is, we later found out that 40% of devices that failed in the field, on the comma 2s, we just knew they failed. We knew they failed here, and we just put them in the wrong bin. Which is, you're not going to be 100% at that. So assert device pass all tests, serial number. This is the highest leverage thing we've ever done. Now you have 11 things. You go down the list, and then your thing is reliable. This is a fun one too. I remember a few years ago, like marble floors were a thing, and you see these companies raise billions of dollars. And George used to say this thing like, where are our marble floors? Are we doing something wrong? This is a figure robot. They're a relatively new company. They make humanoids. They look incredible. They look really nice. They look probably nicer than like a Tesla Optimus. And they have this insane polishing head for them. Like, this is more insane than anything in the comma factory. And this thing hasn't shipped. And this product, they've already moved on. It's a figure 3. And how much do you think they spent on this machine? This is our stress test rack. We shipped 18,000 comma 3Xs on here. That's $20 million in revenue. The figure has shipped 0 things to people. Yeah, when I was an intern in 2019, I remember, I was like, okay, when I finished my internship, I was working on something called a testing clause. It was very similar to this. It's like the openpilot CI version of this. And I was like, okay, I want to make a nice rack. And I was like, I didn't know what nice meant. I just knew it wasn't wood. It didn't look like this. It didn't have like electrical tape wrapped around it. This has been stable since 2019. This is it. Really. Almost probably all the comma devices you've bought are mounted here, here, here. This rack fits 120 devices, so this is the top of it. But no, it turns out I shouldn't have been spending the time making this metal, I had this idea that the devices would like float and it would look sick. No, I should have wrote assert device passes all tests. That was the thing to do there. All right, so we're 8 years into comma. We released a not a dev kit. Every product until the comma 3x, we'd call it the comma 2 dev kit, the comma 3 dev kit, the Eon Gold dev kit. The comma 3x was not a dev kit. Many of you have driven with one. Fortunately, you can't see the outline, but it looks like that. So 2 years later, after we launched the comma 3x, it's done $20 million in revenue. We sold 18,000 of them. It works out to exactly 3x comma 3. Yeah, I don't know. That's how it works, I guess. It's kind of fun like that. 40% sold are daily actives. That's incredibly competitive with all sorts of consumer electronics. People use their phones more than that. But you probably use your laptop a bit less than this. Most of the consumer electronics I bought a Vision Pro, got a Rabbit, I got all those things, and a lot of daily active. And it was good enough for clickbait thumbnails. Like the YouTube videos started popping up again. The comma 3 had none of this like organic content. We didn't send a device to Snazzy Labs. Either he reached out and we just told him the vibe. It was like, I don't know, just buy it. If you don't like it, return it. And tell people that. Tell people whatever you want. We're not going to tell you what to tell people. We offer it for $9.99, and that's the narrative. And he liked it. Both of these YouTubers really got it. I invited him to Comma Hack because we did a car hacking hackathon, and that's when we got the Rivian supported. They really got the vibe. it just goes to show you don't need to control the narrative. You're not holding it wrong. It's just the product was just kind of ready for them, even though we might not be quite ready. All right, so what's after not a dev kit? Does anybody have any answers? Like, what do you want in a comma? What's after not a dev kit? Are we happy with the dev kits? The not a dev kits. I know, Eric, I know you always got some feedback on this stuff.
Well, one thing I know everyone wants is quality, but in particular, I'm curious about a 2-year warranty.
We'll get to that. We'll get to that. Okay. There's a few things. Is there anything else? Anybody? If you're a user, can you just raise your hand? I'm curious how many people use the product. Ever used it? Okay, cool. About half. Go ahead.
I want easier installation so I can give it to an uncle or another friend.
Cool. Is like IKEA good enough? There's some fundamental parts of the install. Just improvement. Okay. Yeah, that's one of the things that we're not going to make the product worse, and we're going to try to make it better. Anybody else? Go ahead. Okay, cool. Not overheat. Anything else? Price. Okay. Those are 4 great ones. Okay. Cool. So we got 2-year warranty. We don't want it to overheat. We want a simpler install, and we want it to just kind of fit on any windshield. It's just meant for it. Cool. And the price. We can't forget about the price. We learned our lesson with the comma 3. We really learned our lesson with the comma 3. All right. So windshield. Meet the comma 4. Maybe let's take a step back. So it's designed to live on your windshield right here. We talked about windshield. It fits right there. And it's got a little bit. It's got a little bit for you to look at, but everything else, just hide it. Hide it on your windshield. It's more openpilot sized. Let's watch it drive for a second. Or we learned videos don't work, never mind. All right. So we had a not a dev kit, so we built a real product. That's the next step. And a real product needs a new interface. So your comma 4 has a brand new UI. We still communicate. Driver monitoring is still watching you. It's the same openpilot that you know. We've got a torque bar now. We really want to be able to communicate openpilot's driving policy to you better. We've got the confidence ball. So when openpilot knows that you're likely to disengage, this ball will go up and down. So you know what openpilot's thinking. Is openpilot low confidence? You can really notice this right now in experimental mode. It's a lot of fun watching it, and you're like, okay, cool. That's exactly my experience with experimental mode. It's good that the model thinks this too. The torque bar is super cool too. You can see subtle control bugs. It surfaces all these subtle things about the driving policy that you have these suspicions about, but you're just not quite sure. And it's just communicating these to you all the time. All right, we talked about setup. Plug it in and drive in 5 minutes. No more 8-degree mount. Instant mount cure. That was 48 hours we took away. 1-minute CI. They came to the setup experience too. Comma power is optional. We shipped that to your 3X too. It's always good to emphasize though. People love that one. Comma power is very optional. And we now cache the most common software on the device. So Wi-Fi is optional. You can get the device, like you buy from comma.ai/shop. It gets delivered to your house in 2 days. They'll get rush shipping. You unbox it. You're excited. You tear open the box. I know a lot of you guys already have 3Xs. You're going to have to remove the mount. But let's talk about your uncle, right? You're going to buy him a device. You can grab the box, go drive over his house, tear open the box, stick the mount on, take down the rearview mirror trim, connect it up, slide it back on, and you're going to click use openpilot. And you guys are going to drive. All right. We got comma care. It's 3 easy steps. You sign up for a comma prime trial. You got to get it right when you buy the device, like Apple. You keep your comma prime subscription active, and then you enjoy your extended 2-year warranty. Comma 4 comes in 2 sizes. Sizes are important. You got to give flavors. Ooh, this doesn't go well with the black. We'll have some on display for you guys. You can go check them out over there. We're going to have some really cool comma 4 displays. But this is the 10-watt variant. This is the 100-watt variant. Not ready yet, Q1 2026. But you plug your comma compute into your comma 4, and it's got the same auxiliary USB port that your comma 3X has, and you can upgrade it to basically FSD levels of compute. And the cool thing about this is it scales a lot better than mobile SoCs. You want to keep getting the latest Snapdragon, well, you're not going to get nearly the performance you want. If you want to take like an existence proof, right? FSD is a system that ships today, right? And it uses a certain amount of power, it's got a certain amount of flops. This will be able to match that. So we've got an existence proof, we can match that in terms of compute. You can expect it sometime next year. As for the 10-watt variant, we like to call this the Snapdragon 845 Max. It's got maxed out cooling.
You guys know you still got to buy the 10-watt one, right? You buy that one today, then you buy the add-on next year.
Optional add-on. We've got to emphasize this. The 10-watt is the real chill one.
Don't wait till next year to buy. You need this one in mind.
It's the same one. We're not swapping out the 10-watt version to the 10-watt plus 100-watt compatible version. It's always 10-watt plus 100-watt. So the chip, the 10-watt version ships with, sorry, it's all the same version. But the 10-watt chip is the Snapdragon 845 Max. The reason we call it the Max is we maxed out the cooling. Yes, it's the same chip. But it sustains 10 watts. And we can run bigger driving models with that. It's also whisper quiet. So we talked about never overheating. It's all fixed. It's all fixed. And we have big headroom to run bigger driving models. This thing does not make any noise. This is one of the things we put the most time into the comma 4. The comma 4, it's easier on the senses. I like to refer to it just being opt-in. It's there. You can pay attention to it. You can listen to it if you want. It's got some nice sounds. It's hard to hear the fan. If you really want to, you put your ear up to it. You can hear it. It's really hard, though. If you want to look at a big screen, maybe you can add it with the aux port. But the screen is just kind of there if you want to look at it, if you want to peek. What is OpenPilot trying to tell me right now? Otherwise, feel free. It's not asking for your attention. And there's a comparison with the comma 3X and the comma 4. So if we look at the fan power, we get about 3C per watt better on the cooling. And this is very close to the max you can do on a Snapdragon 845. We can sustain max performance that we'll ever be able to ship to an 845 very comfortably on the comma 4. So that's where it gets its max name from. All right, so specs. It's got an OpenPilot size form factor. That's number one. It's got a beautiful 536 by 240 OLED, still a touchscreen, still color, and the very standard 536 by 240. We've put a lot of work into each one of those 536 by 240 pixels. Put a lot of work into each one of those. It's got the Snapdragon 845 Max. It's got 360-degree vision, same as the comma 3X. A bit different image sensors, but you'll see an advantage of the image sensors in a second. Very similar to what we shipped in the past, though. It's got the same 120 gig UFS, but this results in 10 hours more of footage. We do a downscale on the ISP now from these image sensors. Same driving performance, same capacity for driving. The footage is half the size now. This makes our training stack, it's OpenPilot sized. Makes the training stack faster. It's the correct size, you know? I was in the factory the other day, and I was watching our stress test boot up, and it boots up way faster than the comma 4. And you're like, okay, why is this? Well, everything is just a little smaller. There's actually, like, the firmware is a little smaller for all the auxiliary things. The modem firmware is like 10x smaller. It's all just smaller, and the correct size for OpenPilot. It feels, you feel it. It boots up faster. It's OpenPilot sized. It's got an eSIM too. So no more SIM slot. We got to kind of avoid that mechanical design problem, and I think it was a much better experience. All right, it's designed for scale. So when we say we're not ready for Linus Tech Tips, that means a lot of things. It means OpenPilot's not ready, the software's not ready, from many perspectives. Only recently did we solve fingerprinting. A couple of things in the video that I saw that I was like really watching out for in the video. Is it going to fingerprint? Did they get a good car? Did they have to understand any of the subtleties of the branch names? And like, do I need alpha longitudinal? Do I need to SSH in? Should I run a fork? And then, like, if the review's good, which it was a very fair review. I think it was a very honest review. If this leads to conversions, are we ready to sell devices? At the time, we were not. The comma 4 is designed for scale. So before we ever did any CAD, before we laid out the board, before we did any of that, we designed out the production steps. Each rev, the comma 2, it's so simple to build. It's like, you don't really need to do this. We just kept building them and outputting them, and then we just shipped the best ones we had. The comma 3, we just threw in everything we thought was really cool, and then we're like, all right, cool, we gotta build them now. Turns out that's not how it works at all, and this drives a lot of cost. The comma 3x, we kind of did a mix of both. We were like, oh, let's do a little design, now let's do a little bit of design for manufacturability, now let's trade it off a bit. The comma 4, we designed the factory first. We're like, okay, cool. How are we gonna we need to use auto-feeding screwdrivers. We need to be able to build 100,000 of these a year with the same team, same office, same setup. We have not really grown the production team size since the comma 2. And we built 3x more comma 3x's than comma 3s. So we're going for a bit more than a 4x here. It's got 2x less parts. And the parts that do remain, we have multiple suppliers for each of them. You never want to get to the situation where you're like, this is a fun story from the comma 3. The screens were like they would trickle in. We were living week to week on the screens for the comma 3. Beautiful screens, beautiful Samsung OLEDs, awesome glass, but they trickle in like 40 a week. And that's not scale right. We ended up having to send a PI to our screen vendor. And we're like, are the screens there? We're like, can you just take some pictures and see if the screens are there? So we're well beyond this now. Multiple suppliers for every part. It's got a real supply chain. It's 4x faster to assemble. That's just right now. Got a lot of refactors planned, but we gotta ship the ones now. You always gotta ship your refactors. You do the dumb thing, then you do it again, then you do it again. You just do the most obvious thing. And this is the loop. It doesn't end. It's got a real fulfillment line. I think many people would be surprised to know that the bottleneck during sales is fulfillment. Our awesome fulfillment team, it's you can meet them over there. Ada and Marlene are our awesome fulfillment team. They can do like 200 a day peak, and then this is just, they get there and they're like, all right, Adeeb, we can't do it. I'm like, it's all good. We do an awesome job of fulfillment. We get the 2 days out right away, but it's a bottleneck. The box is hard to fold. You got all these little inserts in them. You got a lot of little pieces. We used to have a little towel that we'd fold like this, and somebody would sit there all day and like fold a little microfiber cloth. I was like, is that a real value add for people? Do people want to pay for this in their BOM in the device price? Obviously, we can improve that, but you got to get there. You got to get there. So if you want to find Nick and talk about the box design and stuff, we really took all this stuff. We had a lot of fun with it. So it's got a real fulfillment line. And we refactored the whole factory. We did a whole bunch of construction over the last few months. Our fulfillment room was, it was a little cramped. It was basically storage and then like a little area to walk in, and you get a few boxes, you put the parts in, then you can do a couple more. So we've got a nice big fulfillment line. We have a nice big assembly area for the comma 4s. It actually looks a little sparse because they're just so tiny and they're so easy to build. So we gotta put some plants in there or something. We gotta fill up that space. And then for our SMT line, we got a brand new second SMT line that will run one side. We'll see the board in a second. There's one very dense side of the board that looks like a phone motherboard. And then the other side will run camera bars and the top side of the board. So it's very beautifully balanced. And to crank out 100K a year, perfect redundancy between the lines. It's got OpenPilot 010. We put a lot of effort into reliability. how often do you hear fingerprinting on Discord anymore? We got the fingerprinting wizard right here. How often does it come up these days? If you got a Mazda, maybe. We got a dashboard and it just goes, it converges to 0. It takes a while to fix these things. Like it was only like a year ago that we got rid of like the RTC, and this caused like all these like weird bugs. The device isn't a clock. You gotta like you go back to Maxime's talking, like you go back and you revisit your requirements. It's the Elon thing, like make the requirements less dumb. Why is the device a clock? Why do we rely on absolute time? And this drives decisions down from the microcontroller that does this functional safety on the device all the way to the front end app and Connect. We deleted so many lines of code and just a whole class of bugs. There's a lot of cool things in OpenPilot 0.10. You'd be surprised to know we spend basically very little time on validation of individual commits. We do spend a whole lot of time on building the CI systems that we talked about today. But we spent very little time like, all right, this OpenPilot release has to go out. All right, somebody's got to get a device. Somebody's got to like put it in all the cars. Somebody's got to do this. That's not really how it works. We spend very little time on individual changes, and we spend a lot of time on the infrastructure. You ever hear the quote, the product is the factory? OpenPilot 0.10 is ready for scale. You can't tell people, go make a pull request for your fingerprint. So there's the motherboard. So we got our beautiful Snapdragon 845 Max right here. You can see this thermal underfill. So you get some, this is where you get some of your cooling improvements. We got 3 tricks for the cooling that really improve it. Each contribute basically equally. So this thermal underfill is one of them. It should also massively improve the reliability. You ever see like the remaining camera malfunctions and stuff? It's due to this package on package on the 845. And we've got like the most awesome SMT lines to start with. We got vapor phase ovens. This is nicer than most SMT lines. It's basically the max you can do. We got like electroform nickel stencils. We just bought a super nice stencil printer. We got 3D AOI. This is kind of the next step in this. So you get about a third of your thermal improvement over the comma 3x from this thermal underfill. And then you get some reliability out of it. You got your PMix. You got your Panda. Same red Panda. It's all very familiar from like the OpenPilot side. You got a microphone and an LED, OBDC port, aux for your comma compute. You can ignore the SIM slot. The SIM slot is, if you want it, I don't know how many people know this about, I'm sure many of you know the Humane AI pin. They were not able to reuse, like they couldn't refurbish their returns or do anything with them. It was basically like dead weight once they returned it. They had a pretty high return rate. And this is because T-Mobile wouldn't let them reactivate the SIMs. I was like, there's no actual reason for this. But this is just how the carriers work in the US. Also a fun story. We would not have eSIM in the US if it wasn't for Apple just telling the carriers like, hey, by the way, this generation only has eSIM. The carriers do not want eSIM. Otherwise, they're going to send you a text message and be like, all right, if you switch to T-Mobile today, we'll have your bill. Just click this button right here. They don't want that. So we have Apple to thank for eSIM. Thank you, Apple. So it's in there if you want it. We got the fan connector. And we got this beautiful edge here. And the whole heatsink goes right over here to beautifully shield this whole area. And what that gives you is really awesome GPS. So tiny form factor, tinier antenna, but same GPS performance. The other thing you'll notice is this is all chip level. There's no SOM. The SOM will take up about this much area. So obviously SOM is out. You want to make a small device, SOM is out. It's a chip level design. Like it looks like a phone, right? It is all the phone parts too. It's like an 845. The backside, pretty sparse. So this is one of our other tricks for the cooling. You see these big holes. We just shove copper posts through there. And then, yeah, so you see these big holes. We have a big copper plate that goes on the back here. And we're able to conduct the heat through the back to the heatsink. So this gets you another third of your cooling improvement over the comma 3x. There's the Quectel. It's a little smaller than the one on the comma 3x. If you want to ship the one on the comma 3x, it's this big. Doesn't work. Then you got a board-to-board connector, one connector to the other PCB, to the beautiful camera bar, and your GPS antenna. All right, we've got one more product to get through, and then we'll take questions. I want to talk about this thing. I want to see what questions you guys have. Body V2. It's a prototype. We got some for you guys to drive. right over there. So we got 5 of them for you guys to drive. Doesn't balance anymore. That was a bit silly. We realized that. We reverted that on body view 1. But from the start, no balancing. Compatible with comma 4 and comma compute. It's a whole family. This is kind of the end game. We're not there yet. That's why it doesn't balance. But works with the whole ecosystem. You take it for a test right at the booth. And ships Q1 2026. And then the other thing I want to emphasize, your comma 4, still your comma 4. Everything's still open source. We're not locking anything down. In fact, we got a Sunny Pilot booth right here. Shout out to the Sunny Pilot team. They're really like the Debian of the OpenPilot ecosystem. Still got comma body. You guys might have seen SimCity on Twitter. He's doing really cool stuff with his commas. I'm sure he'll enjoy his comma 4. It's more size for his RC car. It's just the right size. Yeah, your device is still your device. None of this is changing. The ceiling is still here. The ceiling, we're not moving down. We're not locking down your device. But the floor, I mean, everybody wants this stuff, right? We were going around. Everybody wants it whisper quiet. Nobody wants it to overheat. We want room for bigger driving models. And easy install. So it's $9.99, all in, no harness. So those of you concerned about the price, don't worry about the harness anymore. Why are we asking you about a harness? Just tell us what car you have. We'll send you everything. And it ships in 1 to 12 weeks. You can go to comma.ai right now. You should be able to pick one up. And we'll try to get these out as fast as we can for you guys. The factory will ramp up pretty quickly. We got a couple more things, Julie. We got a couple more things. So Robbe, who's one of the main engineers who designed the comma 4, we went to Shenzhen a couple weeks ago, and I just want to show you guys some vacation pictures from our little field trip. All right, so this is the mold for the comma 4. We visited the mold shop. You guys will never guess who this guy is. You guys will never guess it. This guy hand finishes every mold. So you like the finish on your device? It's this guy. And this shop is really cool. They make like a whole bunch of molds for like BMW, like interior panels and stuff. China's the most incredible market. You get access to like these incredible vendors. But yeah, you can see the main case, and then we have the top case. It's 2 halves that go together. You see the little screws that go through the case. It's got little hexagons. Hexagons get you that whisper quiet and that awesome cooling. This is the lens holder. So your narrow cam goes here, your E-cam goes here, and then your D-cam. We put it on the same side of the PCB so we can do this all the focusing all at once. Focusing was another big bottleneck that we addressed. And then the D-cam has a separate piece that connects right there. And then it's die cast. This guy runs the die cast shop. Super cool guy. All right, there's a heatsink. This place is also super cool. Their main business is like, they do like 100 different variants of like water cooling blocks. NVIDIA is like one of their biggest customers. Same manufacturer that builds stuff like the 3X and the comma 3, and the comma, I believe the comma 2 was built here too. So this is their CNC shop. It's like 3 fixtures for the heatsink. They do these like really cool blanks. Very cool shop. So now we're going to comma HQ in San Diego. Like I said, we have a beautiful SMT line. This is the kind of stuff we're doing for reliability now. For those who don't know, this is a procedure called die and pry, where we run boards and we just pull off the chip and you look at how the soldering looks. So you got some camera sensors, and then you could see a whole bunch of devices. So you dye them red. This is a little cut of the MISI board. And then you want to epoxy it. You got to wait like overnight for it to dry. You try to pull it straight up, and you look at it under the microscope. And if you see any red, your solder is you've got to tune your procedure. This is our camera focusing setup. So like I was saying, you focus 3 devices at once. With the comma 3X, at our max rate, if we had our very best DCAM guy, shout out Juan, he could do 80 a day if he's having like an awesome day. He comes in, he's like, all right, guys, I'm going to crank out some DCAMs today. He can do 80. Our target is to do 100 camera bars per person in a given day, like in a chill day, it's a Monday, and you're like, oh, okay, you should be able to do 100 comfortably. So massive, massive improvement on that. It all focuses right here. We used to have this complicated setup with mirrors and stuff. Instead, we just have this beautiful setup, and on one panel, I should have put a picture of the panel, but on one panel, you get 3 devices worth of camera bars, and they're all oriented the same way. So you just go in a line down 9, and that's it. You pull them off, and they're ready for the line. And they got ultimate provisioning. The reason it's called ultimate is this is basically everything we could test in an automated way on the device, and this runs at the very end. The comma.3x's were all built with something called stress test. This just merges all our flashing step. We had a final provisioning step. We had a stress test. Merges it all into one called UP. Device comes off the line. It goes right on this. You might recognize the screen. Same screen. So we basically built a mini comma 4. It goes right on top of it. And then this is you got a device under test. And then this is your tester. We call these the UPs, ultimate provisioners. And they just handle it all in one. We get to test the full bandwidth through the USB 3 port, so that we make sure your comma compute is going to be 100% reliable. And we have 80% test plan coverage. So when you design something, you have a big list of all the things it has to do, right? And you do it for the ones when you're designing it, and then maybe when you run your first production boards. But what if you could do it for every single device? And then one of the things that we really looked at with every rev of the comma 4 was, is there some test plan item that UP can't cover? Should we just delete should we just not expose the interface? Does the part need to get deleted? Sometimes the answer is it needs to stay, but oftentimes it's just deleted. And then a shout out for our Appot members. We built a lot of comma 4s. This is our most well-validated hardware. You can see they drove almost 100,000 miles. Got 3,300 hours. For reference, I think the comma 3x was probably around 700. Comma 3s we took a bit longer to build, so they're probably closer to 1,500. We did not build 157 of any of the other devices. We built a lot of every rev. The SMT line is a real superpower. Every time something comes in, we're just all right, run it, build lots of them, and you get you get to do iterations on your whole production procedures. So big shout out to our Outplay members for putting up with all the bugs and helping deliver you guys a refined experience. So round of applause for our Outplay members, please. All right, and then this talk does have an agenda. I try not to tell you guys the device. I just want to show you the cool thing we built, but I do have an agenda. Come build a 5, 6, and 7 with us. I love this video of Kobe from the finals back in the day, where the reporter's like, you had a great game. Are you happy? He's like, is the job finished? It's not finished. We're going to build so many more of these things. This isn't the last Comic-Con. If you want to come up here, talk about the cool shit you did for the next comma 5, 6, the 7, we're just going to keep doing this. There's so much more to do here. Self-driving cars, despite what you see on Twitter, it's not solved. We're not close. So, call me /jobs if you're interested. This is not a bug. We're not hiring 3 supply chain engineers. I just want to emphasize this. If you just want to talk to suppliers all day, you want to just get your stuff and count it. This sounds like a simple job. This is a very legit job. We've got some cool problems to work on here. So, love to hire somebody to make an awesome mobile experience for openpilot. Supply chain, obviously, and we build a lot of products. The tiny stuff can use supply chain too. And a systems engineer to work on more stuff, like you heard from Maxime and Shane. Ship a new update or make the boot time 5 seconds. If you just want to make beautiful software, you like writing MIT licensed software all day. I really like it. If you're out there too and you want to work on this stuff. All right, question time. What do you guys want to know about comma 4?
Questions? We must have some questions. There's a lot in there.
Hi. What does the 100-watt box do?
Yeah, so the comma compute, we could elaborate on this a bit more. The 100-watt compute is for driving, you can think of we'll have 2 classes of models. Right now, everything openpilot ships, the driving model takes about 1 watt. And we can bring that up to 10 on the device. But what if you want to go beyond 10? There's existence proofs in other systems like FSD. And this allows us to effectively scale the compute on the device a lot better than shipping new SoCs on the device. So new desktop GPU comes out, swap it into your comma compute. We'll sell a standard one, and that'll be the 100-watt big model class. And our autonomy team will essentially work on shipping 2 classes of models. Our very best stuff will ship to the 100 class, and then it should trickle down. You see this with LLMs today, right? You would love a tiny LLM versus like the biggest LLMs 3 years ago. So we expect a similar kind of thing to shake out for driving, where we're able to ship way more performant 100-watt models. And if you really want to play on the bleeding edge, this isn't for everybody. We know this is not for everybody. But if you want to play along on the bleeding edge, that's what this is for. Also love to answer questions about openpilot, anything.
Questions?
Tell me about the new comma body. That's what I'm most excited about. What's the payload capacity? And is there anything new with the interface to allow you to teleop it?
Yeah. Okay, so comma 4, obviously a product. We've been at this for 10 years building commas. Bodies are much less mature. If anybody's ever seen a comma Neo, we've got a display with them if you want to check it out, see the progression of the hardware. The body and the eGPU are very exploratory products. We're showing them some prototypes today. They're not comma 4s. You know, it's not ready for your uncle, for example. So the body, to put it simply, an intern's been working on it for like a month and a half. We're just like, it's time for body v2, and we had an intern explore it. So we're expecting to like redesign it a bunch. We're basically showing off like, here's all the secrets. I don't know. Yeah. So I just recommend going around playing with it. If you want to load it up and joystick it around, that's what this booth is for. And you're like, hey, what if this was right here? By the way, if you want to go talk to the hardware team about anything on the product, it's like, why didn't you do this? Or why? Sometimes the answer is just like, I don't know, we don't know how to do it better. And the next one, 5 will fix it. So we really encourage you guys to go. The production team and the hardware team they should be around all the products. So if you want to know anything about these products, and especially the comma compute and the body, these are just prototypes. You know, if you want your feedback incorporated in them, let us know. Like, pack around with them, play with them. Yeah, come play along with us. That's kind of what this is for.
All right, we got another question back here.
Yeah, how long will the comma 3x be supported, or is that to be determined? I know comma 2 was supported for like, I think 6 months or a year. Is that going to be the same with?
Yeah, we don't have any immediate plans. I don't want to repeat what we said with the comma 3. I mean, what we said with the comma 3 is true in that it's like a very similar platform. And then you can't predict like when the software will diverge and in which ways it'll diverge necessarily. So we'll say we'll keep it around for at least a year. And you know, the comma 3 is still getting long-term support, like critical bug fixes. But yeah, the comma 4 has a bit more capacity. It's a bit different. But there's no immediate plans to, you know, to do anything with the comma 3x. They'll get the same updates.
All right, we got another question up front here.
Thank you. This is awesome. I understand the comma 3x had like around close to 130 unique parts, so you're going down about half. I understand the thermal management is going to be better, shielding the GPS is going to be better. I can see all these things. What else is giving you guys the confidence of this 2-year warranty?
Yeah. So like I was saying with like the reliability stuff, we built 157 of these things. I think we maybe built 300 comma 3x's, not 30 comma 3x's before we shipped them. We built 157 of these things. And we saw everything that failed. It's really this simple. I'll tell you guys our process for like fixing the bugs on the revs. This was like fairly revolutionary for us. We made a GitHub issue. And instead of just like posting on Slack like, hey, by the way, the Panda kind of like drops out on this one sometimes. It's like it's on a GitHub issue, and then we just close the issue every rev. You root cause it. As long as you manage your state well, and you just make sure that like it doesn't regress. The comma 3 is also the comma 4 is also shipping on Rev I. We did a lot of revs. We basically did 2 big refactors of the whole design. So this is what it's designed for. Another thing I'll tell you about the comma 4 is the team that designed it. I think Harald and George are the only people who were around when we started the comma 3. And you know, I was part of the team that shipped it. Robbe was part of the team that shipped it. This is kind of the first one we're doing from scratch. we did the comma 3x from scratch, but it inherited a lot of the DNA from the comma 3. This is kind of the first one we're doing from scratch, and we learned all those lessons from that. There's a lot of continuity in the team too.
Hey, congrats on the launch, by the way. I was looking at one of the pictures, and it looks like the rearview mirror might obscure the screen a bit.
Mm-hmm.
Is there, I don't know, is there a reason why you didn't integrate the screen into like a replacement rearview mirror or something like that looks more OEM?
Yeah. So there's some comma forks that do this. The comma ecosystem is growing. I have this idea for next Comic-Con where we do like fork Candyland. I think it'll be a lot of fun. Hopefully there's a little more diversity in the forks by then. The hardware forks are starting to diverge too. You can check out this one called Sidecar. They shipped a few of them, and they ditched this idea. They basically replaced the trim cover. And it was a pretty cool form factor. But then they realized, okay, this only works on 2 models a year of one Corolla, and we have to do this. 325 supported cars. Oh, but this one has a different connector and has a thing right here. And you want to injection mold it because like theirs is printed. You want to injection mold all this stuff. So it's not really scalable. This is designed for scale. But the whole device is designed to be as small as possible. So in a lot of cars, you can shove it a lot higher, such that you don't see it at all. But you have to mount it such that it's designed such that you see the little strip of the screen in the DCAM, and DCAM can stay watching you, and you can see what OpenPilot's saying at all times.
Hey, with regards to your eSIM support, referencing the first presentation, did you do anything? Did you do your own eSIM stack? Are you doing modem manager and having to pull in glib and dbus and all those stuff? Sorry.
That's next. Sorry, I'm a little triggered with that.
Sorry.
No, I was so happy to remove Weston. I really was pushing for that the last few weeks. I want it to be like beautiful inside and out. This stuff is, I don't know, it makes it more fun for me to work on. I know like sometimes it doesn't matter, but like it matters that the thing is fun to work on. So we haven't touched the modem stack that much yet. There are plans to clean it up. We have a lot of issues with this stuff. If you want to come like work here and work on this stuff, I think it's a lot of fun. I don't know who else thinks it's a lot of fun, but you like get to just ship bug fixes all day and like make the thing work. Like it works. Remember the rock?
We got more questions?
So now that the screen is a lot smaller, how does accessing the settings and maybe in the future navigating on OpenPilot going to work?
We have a lot of ideas for Navigate on OpenPilot. It's not quite time for Navigate on OpenPilot, but when that comes back, we have a lot of ideas. The Comma 4 is ready for nav. As far as the settings, you'll see. You can play around with them here. Nick did a really great job with that. You see a lot of this event. This was Nick. You can imagine this on the small screen. We got the keyboard. We did so many revs of the keyboard. The keyboard is incredible. It's actually quite delightful because you don't expect it to be good. So I think that's one of the cool things about the form factor. It totally works. It wasn't clear to us that this stuff would work, and then you just build it and you see. So totally works. There was actually a funny quote from Harald yesterday. He posted, he drove, I guess he'd been driving the Comma 4 for a few months, and he went back to a Comma 3X, and he's like, this just feels like watching like a big TV. You know, it's like the opposite effect, right? If you went to a small TV now, you know, you went to like a 24-inch, you're like, what is this? You got the opposite effect with the Comma 4.
All right, another question over here.
Hey, congrats. Does the Comma Electronics complies like fully formal certification?
Yeah, it's FCC
automotive?
certified. Yeah,
Oh.
it's got all the things you need to use it.
There are like levels or grades like about the certification or
As far as what?
about the components like safety or
Component safety. What do you mean by component safety? So there's like standards around functional safety, right?
Right.
And yeah, it inherits all the same stuff from our previous products. Yeah, we observe ISO 262. You know, it's FCC certified. It's a good product.
Great.
All right, we can take one more question.
With the confidence circle feature that you have, what's
Yeah.
been your experience in terms of driving and using that? Is it just kind of something that's interesting to look at, or does it change kind of how you use the product?
It's changed for a little bit for me. It's also fun because experimental mode is just kind of getting good now, and you can kind of see what it's thinking. But the whole UI just communicates a lot more about, like, especially since I know how a lot of it works and how a lot of it is written. I get, like, when I see like the torque bar like do like a little jerk or something, I'm like, oh, I see that bug that we have in like the lateral control or something. It exposes a lot more state to you. And I think it communicates the same thing to users who don't understand the internals too, just a bit more implicitly. So I think that's one of the really cool things about it. I'd be curious to see how it would look. Unfortunately, experimental mode got good at the same time. Unfortunately. But you can kind of see when experimental mode gets a little bit better, as it has been getting a little bit better each release. It gets a little more confident, especially on my commute. I can see I got like a lot of roundabouts. I change highways a lot, and it's a lot of fun.
All right, thank you guys. Adeeb will be available for questions also in our
I won't talk all
general
day about this
Q&A.
thing, so.
He's around. Find him, ask questions. It is lunchtime, but just if a reminder for anyone that pre-purchased merch, it will be available at our comma shop over here, which will be brought out shortly. The booths have changed a little bit. You will see that the Build a 3X will be now Build a Misi. We have some exciting things around, so please feel free to go grab lunch and then browse all of our booths. We're running a little bit late, so we will kick back off with the talks at 2 p.m. started in about 5 minutes. guys, welcome back. I hope everyone enjoyed lunch. Our next presenter is George Hotz, so please gather around, and we're very excited to bring you the second half of the talks. Welcome, George.
On the mic, and then it turns green, and then you can hear me. I'll give everyone a minute to get in here. I made this logo myself. Let's see if the clicker's going to work. We only have one AI picture in the slides. You'll see. Yeah, so, this whole space really is a game of Survivor. A lot of people have been voted off the island. So that's kind of what this talk's about. I thought it was appropriate to steal branding from a reality show. My name is George Hotz, and this is Outwit, Outplay, Outlast. So does this work? There we go. So you know what? I don't work at Comma anymore. I am still the president, but you heard from Adeeb, who presented the Comma 4, and you'll hear from Harald after me. They are the executives who run the company. I am a cheerleader. Right, so I'm mostly here to cheerlead. Sometimes I complain. Like, oh man, you think the cheerleaders ever complain? Like, why'd you guys lose? That sucked. I could have thrown that ball better than that. Yeah, those are the things I do. You're hearing from a cheerleader here. You're not hearing from anyone with any secret inside knowledge, but this has just been my observations. I used to work at Comma, so I know a little bit about it. We can talk about what the original plan was. We were going to contract with Tesla to replace Mobileye. The deal fell through. He had some good press around that, though. It was fun, Elon's a great guy. It's really, you just got to think about, the thing I really like about Elon is he inspires you, even if you're his enemy, if you're his friend, it doesn't matter. It's like, it just shows you that great things are possible. Right? And this just, it makes me really happy. So, even though the contract fell through, great things are possible, right? So we're going to build autopilot anyway, right? My contract was to replace Mobileye and the original Tesla autopilot. We build it anyway, and we're going to sell it to car makers. A lot of people are like, George, why doesn't Comma work with car makers? This was the original plan. We were going to go sell to car makers, right? So we built it. This was the original Comma car. I stole this from another TV franchise. We got Engage, right? This was on Bloomberg 10 years ago. We had all this stuff. I think Adeeb talked about this a little. Hotz added a joystick to the car's center console. A pull of the trigger engages the self-driving system, right? Why did I use the cruise control button? But business. So this works, right? It was really good. We did a road trip to Vegas. We're driving. Again, it's not quite as good as modern OpenPilot, but a lot of it was there. A lot of the stuff we've done for the last 10 years was shippability. So we build this, and I'm like, okay, so now I just got to talk to that's the only AI generated photo in the slides. It's kind of like, hello, Mr. Ford. Yes, okay, so you see this? Mr. You don't, what do you mean, you don't know what a PID loop is? No, but it's using an AI model and predicting the steering angle and putting that to a PID loop, yeah. It might as well be AI generated, right? There is no Mr. Ford. I was misled by how Tesla was run, because there actually is a Mr. Tesla. You can go to Elon and say you're using a neural network with a PID loop, and he's like, that's shit, we got model predictive control. So it turns out you can't just do this, right? And even people today say, well, why doesn't Comma work with car makers? And I want you to take that and then think about that a little bit more and think about how that might actually happen, right? Notice that a lot of people have this idea. A lot of companies have the idea that they're going to sell to car makers. And we're going to look later in this slide into how it worked out for them. So giving up on this idea was the right move. I understand that it doesn't feel right. I understand that people have this idea that, well, but you should. That's what makes you a legitimate business. Look at my figurehead polishing machine, right? It is fake legitimacy. So we're going to pivot. Right? I think let's sell to car makers. Who came up with this idea? No, me? Oh, let's fire that guy. We're going to pivot. And what are we going to pivot to? Well, can a cell phone drive a car? It was kind of the original question. We thought about all that stuff, and we're like, can we run all of this on a cell phone? And the answer was yes, and we did it in about 6 months. And then we launched the comma.1. The comma.1 was shipping by the end of the year for $9.99 and $24 a month, right? Which is actually exactly what the comma.4 is. The comma.4 is $9.99 and optional, $24 a month. We don't have a page on the website describing it now, but you guys should buy Prime anyway. It's in the FAQ, don't worry. It's the exact same thing. It's the exact same thing. But I didn't realize actually how hard this was. Many times in my life, I've been hit by Dunning-Kruger, and no one is ever going to start a company if they don't believe that things are easy. Right? What's the saying? It's, we didn't do it because it was easy. We did it because we thought it was going to be easy. So. I mean, and I didn't really, see it, but, we just kind of weren't there. And then we got to reach out from Nishta. I'm like, oh my God, guys, it's a cell phone in a plastic case. You're already harassing me and telling me you want fines, and I'm just like, when they go left, you just eat a cheesecake. You see what I mean by that? Right? It's like, the saying, when they go left, you go right. When they go left, you eat a cheesecake. These people don't even understand. Nobody understands what's happening, right now with AI. It's so fake, and it was fake back then. It was just the beginnings of it. Now people are kind of starting to catch on. You know what I mean? But 10 years ago, people were like, oh, the media. Oh, this is in the New York Times. That's a legitimate news source. Right now it's the media, right? Try until you die is not what most people would advise. In this case, however, startup comma.ai is probably close to calling it quits. /gear 2016. Lessons from the failure of George Hotz and the comma.1 semi-autonomous driving system, Forbes 2016. Comma is taking its ball and going home, Automotive News 2016. Autonomous vehicle company shuts down in fear of regulation. And this just isn't true. And it's so interesting, when you see a media story about something that you understand. This is Gelman amnesia, right? You see a news article. Let's say you study physics, and you see a news article about physics, and you're like, oh God, these people don't know anything about physics. Why can't they get a physics guy? Ooh, international politics. Wow, Iran is sure causing trouble. They must be really informed about this. It's just no, they're so skate where the puck is going, not where it has been. So this was the first video of openpilot driving. We open sourced it. This was the first openpilot release. Openpilot is an open source driving agent. Currently, it performs the functions of ACC and LCAS for Hondas and Acuras. It's about on par with Tesla Autopilot at launch and better than all other manufacturers. And that's still kind of true. So we didn't ship the comma.1. It actually took a long time. And again, it really is Dunning-Kruger. And it's, no one's to blame but myself, right? I don't blame Nishta. I don't blame the media. It's fun to make fun of these people. But fundamentally, at the end of the day, I had a phone in a 3D printed case. So 4 years later, we shipped a phone in a 3D printed case. No, but like, look, the case is like smaller, and look, we added some IR LEDs down here. We had a GPS, there's a board in the back here. It's pretty nice, right? Who owned a comma 2? I had a few people, yeah. It was, it was something. And it was $9.99 and $24 a month. So then after the comma 2, we shipped the comma 3. The comma 3 was starting to look like a real product. The comma 3 actually shipped pretty quickly after the comma 2. Look at that openpilot. It looks pretty modern. It looks pretty good. But the comma 3 was too expensive. Right, who had a comma 3? Wow, more of you than comma 2s. I'm sorry you guys paid so much money. But you know what? Don't feel bad, because however much money, you're out $2,000 for a comma 3? We're out $5 million on the comma 3. Comma lost $5 million on the comma 3 project. Sales stagnated. The product was too expensive and undifferentiated from the 2. It was a lot better. We made a lot of progress in making the thing look like a consumer electronic. But fundamentally, this didn't drive sales. This is the comma 2 era, and this is the comma 3 era. But, we fixed it. We shipped the comma 3X. How many people had comma 3X? All right, a lot more comma 3Xs out there. And it was sold for a good price. And that fixed sales. All right, so what do you guys think? This is future-facing statements. I got future-facing statements here. Yeah. So, no, I think that, the presentation's pretty good. The website's pretty good. The device is amazing. None of the stuff we've shown off does justice to just how much better this device is than the old one. You see this picture in the UI, and it looks like, this could be Photoshopped by some fake company. It's so difficult today to tell the difference between what's fake and what's real. Because what makes something real is an incredibly difficult engineering problem. And hopefully we conveyed some of that to you today. How just insanely difficult it is to make this device. And people are like, oh, you're on an 8-year-old mobile phone chip. None of that matters. My Apple II was more responsive than Apple II running VisiCalc was more responsive than my M4 MacBook running Google Sheets. Why is this? It's just due to this insane complexity of software. None of it has anything to do with the actual hardware. This thing is 10 years of refinement in a piece of software. You saw the first version of the software, you see the current version of the software. I'm hearing about mutation testing this morning. I'm like, damn, we got to put that in TinyGrad. Yeah, I think this is the first one that is really a top tier consumer electronic. I love consumer electronics. Adeeb really loves consumer electronics. Yeah, it's really, if you buy this device and get one shipped to you, I think you'll find it might actually be the best unboxing experience you've ever had. And I don't say this I say this, I'm actually thinking about it, right? Because when people buy a new laptop, right, it's okay, yeah, it's a little bit better than the old one. And if you guys had a comma, maybe, some of the magic would be lost. But for someone who's never had this, for someone to realize that you can buy a little device that fits in the palm of your hand, stick it on your windshield, and it drives the car, that's magic. And you can describe it to a 6-year-old. All right, so here's your test. Here's your test for all technology. Whenever someone tells you that they have some new technology, oh, we're building humanoid robots. Okay, cool. Can I have one over and have it cook me some pasta? No, that doesn't exist. But you wouldn't know it. You wouldn't know it. If you consume media, if you consume advertising, all of this stuff looks possible that's fake, right? Oh, AI coding is going to lay off 30% of engineers. Actual AI coding, right? You can't even use these things for customer support jobs. The disconnect from reality and hype is insane. And I don't have any language to convey. Like, I'm not better at hype and better at advertising than those people. They're actually better at it than me. But what comma is better at is making a product. So I think if you've never driven a comma and you buy this comma 4, it might be the best consumer electronic experience you've had since, like, I don't know, you guys remember getting like an N64 when you were a kid? Those are the real magic ones, right? Because from the SNES to the N64, that was magic. From the PlayStation 4 to the PlayStation 5, and now I'm playing Modern Warfare 6 instead of Modern Warfare 5. Well, it's not really better, but they're shutting the server down for Modern Warfare 5, and okay, all right. So, it's a top-tier consumer electronics. Look at this great circuit board, right? Now that's the circuit board from the comma 3. That's the circuit board from the comma 4. Adeeb already went through this, but yeah, I mean, that's on par with the true state of the art. Like I said, we have an SMT line that's, doing things that they're not doing in the fanciest SMT lines in China. Vapor phase oven, 3D optical inspection. They're good about inspection, but they don't have the nice ovens. That's what the front of it looks like. This is an LTE modem, GPS antenna. I did have a contribution to this. I did. Even though I'm a cheerleader, I cheerled for something. I wanted the GPS antenna to be big. Right, there was going to be a small GPS antenna, but I'm like, if the photons come from the sky, and here's the antenna, and you got to hit the, right? So, camera board connector, comma 4. This projector has very low dynamic range. It's hard to see though. But yeah, all right. What is success? I mean, these are the kind of questions you start to think about. Who's succeeded? I should have included this in the talk. There's a great quote from Jensen. This man owns the biggest company in the world. And he's just like talking candidate interview. He's like, man, if I'd known how much headache it was going to be and how hard it was going to be, I never would have done it. I love this. I love this. I love, it's great that he, it's great to see the success of people like that. And yeah, I mean, if the top company in the world, the greatest founder in history, this is the biggest company in history, is saying this, then what is success? And you think about a game of chess. You think about what success means in a game of chess. Success is when you win, right? And you might lose, you might draw, but either way the game ends. Chess is a finite game. But what does success look like in an infinite game? Success is simply surviving. So, this is Founders Fund back, Keith Robbe. The founder of this company steals all the comma rhetoric, literally steals all my rhetoric, has over 10x the funding. Oh, they're gonna ship, now it's automaker partners, but originally they were gonna ship a kit to put it on your car. $220 million. Who remembers Embark? Did a SPAC. Did anyone ever do a SPAC and succeed? Did anyone ever go, oh yeah, I'm so glad I invested in that SPAC, bro? Come on. Ego-based. I was on a panel with these people. You know, I hear myself talking and I'm just like, oh my God, you have no idea what the hell I'm saying. They're actually being investigated now for like selling secrets to the Chinese or whatever. And you know, my thing is just like, what secrets? $1 billion hit on Argo, right? This was the Ford Volkswagen joint one. Shifts its bet to driver assist tech. Yeah, you can right now go use Blues Cruise on your Ford, or you can buy a comma. How many billions, you know? And then there's the really big one, of course. Yeah. Despite $10 billion spent. Did you know that Cruise was originally, I talked about this in last year's Comic-Con, or 2 years ago Comic-Con. Cruise was originally building a $10,000 aftermarket kit for Audi A-Force. Kyle Vogt gave up on this dream. He gave up. He talks about this in Lex Friedman because it was too hard. There are too many different cars you're going to have to support. So figuring out how to support all those cars is too hard, and figuring out a graceful degradation if everything isn't working perfectly is too difficult. Comma solved all these problems years ago. None of this stuff was hard, right? But then people look, and it drives me crazy. It's like there's still people out there who think Cruise is a bigger success than comma. They lost $10 billion. I don't even know what to say. Like reality comes and smacks you in the face, and you're like, yeah, no, but it was a good run, man. It was a good run. For $10 billion, you could have had 6 of these. This is the biggest building in the world. We could have had one in Chicago. We could have one in San Francisco. We could have had one in LA. We could have had one here in San Diego. But no, we had Cruise. Oh, yeah. By the way, Kyle Vogt, he's looking for investors. He started a company called The Bot Company. They raised $150 million. They're building humanoid robots, guys. Yeah. It's self-driving, that was too hard, but humanoid robots? We chose self-driving because it's the easiest problem in applied AI, and it's still not close to done. We can get to some things about that in a little bit, but humanoid robots are way harder. Humanoid robots are so much harder than self-driving cars. And so, if you like losing money, I mean, you can say it was a good ride, Or invest in the new Burj Dubai. I believe that. Someone should build that. Or actually, I really want to build a large statue of Taylor Swift. I want to build a 500-foot stone statue of Taylor Swift on that highway from LA to Vegas. It's going to be sick. It's my Taylor Swift statue. If I ever get rich, that's what I'm going to do. So this is my slide from 2016, the players. So we have Google. We have Otto. Well, Anthony Lewandowski walked away with a lot of money until they sued him for it. And we have Tesla. Let's... Who was notably absent from the Old Town Road, compilation was Waymo. Waymo's actually pretty cool. And I'm not saying this, ironically. And, what makes them cool is that I can download an app and use it. And that's, again, my test for what real technology is. It's not real technology if you see a video. It's not real technology if Waymo is talking about how we're going to help the blind get around. Why can't they just use Uber? I don't get it. Stop it. But when I can go to San Francisco and download an app and call a Waymo, that's actually pretty cool. They're human supervised and quasi-teleop. They're not a solution to self-driving cars. They have questionable unit economics. They use maps. But they survived and they shipped. And that makes them cool. And it's really nice to be in the car alone. If you read my 100x investment, I wrote a blog post about this in 2018. And my criticism of Waymo actually was not that it would never work. I remain quite optimistic that self-driving cars are going to work, and we're going to get to when the timeline is. And I think that it's very possible that Waymo will actually have the first solution with these caveats. But the unit economics of Waymo would never be as good as the unit economics of Uber. I dated this girl for a bit who was an Uber driver. And I just looked at how much she was making on the rides and stuff, and I'm like, you're losing money. Like when you take the cost of depreciation and gas and car maintenance, she's actually losing money. Right? Uber's new system has figured out ways to prey on people who are bad at math pretty much. Or they have like Uber drivers who are like, they carefully like, it's so amazing when you look at the disparity of resources between an Uber driver and Uber and all the little tricks they can pull. So Waymo will never be able to compete with Uber on unit economics. But they actually might not have to. I thought that I was in the minority of people who didn't like having the person in the car, but I actually think that's like 80% of people. So Waymo, despite being teleop and despite having questionable unit economics, may very well be a cool, successful service. So, and it's interesting, they take the same, how Waymo outlasted the competition, right? Surviving. So yeah, the players in 2024, right? Like who's left? Did I miss anyone? Zook's okay, to be fair, Zook says something. Does the car drive in all directions anymore? Something. But no, I mean, look, the big player here is, of course, Tesla. It's always been Tesla. We can just talk about, since the beginning, we've always talked about how far we are behind Tesla. And it has stayed that way. They have managed to stay about 2 or 3 years ahead of us continually. The new FSD, I was blown away. Like at the leaps that were made from like the FSD 12 that I tried, that I was like, this is literally worse than OpenPilot, to like FSD 14, which is like, all right, they figured something out. We got to figure that out too. I think we got it. But so you can look at the fleet size. This is the Waymo fleet, the comma fleet, the Tesla fleet. Comma is the second largest video connected fleet after Tesla. And these are our growth numbers. So we have almost 7,000 dailies and almost 12,000 monthlies. So yeah, we're gathering big data, but again, there's really only one company to compare yourself to in this space, and it's Tesla. So let's talk about our distance to Tesla. Here's some breakdowns of some different axes, right? So when you look at the difference in fleet size between comma and Tesla, we're off by 3 orders of magnitude. So comma's 10K, Tesla's about 10 million. When you look at the total number of total amount of training compute that we have, so you can see the Tiny Corp, you see the Tiny Box Pros over there. You'll hear about them more in a talk later. We have about 1,000 GPUs. Tesla has about 100,000 GPUs. So we're off by 2 orders of magnitude there. Inference compute, which is how much compute is actually on the device. So if you heard about the 10-watt version and the 100-watt version, right? The 100-watt version is not a different device. It's literally just a GPU that plugs into your comma 4. It's a consumer GPU that plugs into your comma 4. Your average consumer GPU has the same power as the Tesla FSD AI computer, right? Tesla will never tell you this, but like a 5090 crushes it. A 5070, that's about the same. But a lot of this is just because of power. Right? The Tesla thing draws 300 watts, a 5090 draws 600 watts. So yeah, inference compute, Tesla's ahead by 2 orders of magnitude, but we'll get to that one later. And then we have yearly spend. So comma's yearly spend is about 10 million, Tesla's about 100 billion, so that's 4 orders of magnitude. So training compute, we closed from 3 orders of magnitude to 2 orders of magnitude by building a computer factory. Inference compute, we've closed from 2 orders of magnitude to 0 orders of magnitude. So over there on the table, we have the comma compute boxes, but that's what the comma compute box really is. This is a AMD RTX 9060 XT. It's a $300 GPU, 205 TOPS, and it already just works with the comma 3, 3X, and 4. The software won't come to the 3, but the software will come to the 3X and 4, and someone can backport it to the 3 if they want. Nice power enclosure coming soon, or you can build your own out of parts on Amazon. We'll charge some amount of markup for the nice box, but you're welcome to build your own. Okay. So how much longer to solve self-driving? This is TeslaFSDTracker.com. It's probably the best way to kind of get at this. We have an internal version of this, but it's a little bit different. I mean, like Tesla and comma are pushing on fundamentally different things. Tesla's slogan, or comma's slogan is make driving chill. Our question is like, how do we achieve highway perfection? Tesla's question is, how can I ship this crazy feature? Right, like look at this crazy feature is kind of like Tesla's unofficial slogan. So yeah, you can look at the numbers, and you can look, the FSD 14 has really, the felt experience is really noticeable in data. However, every order of magnitude takes the same amount of time. There's a simple way to predict how long things are going to take. Human car accidents happen about every 500,000 miles. If you believe FSD Tracker, current Tesla stuff is around 3,000 miles per critical disengagement. It gets about 2x better every year, right? If you want to figure out how long something's going to take the trend line and continue it. We have 8 more years. And you know what? Whenever I say 8 years, there's 2 groups of people. There's 2 groups of people. One's like, no, man, have you seen what ChatGPT can do? It's going to be like next week. And of course, those people are never right. But there's another group of people out there, too, who says, no, man, AI is never going to have like the human reasoning needed to drive a car or something, or the brain is. And it's just like, you're not right either. The actual timeline is going to be about 8 years. And that's for Tesla. If Tesla will be there in 8, we'll be there in 10. So, we're halfway. And this is my last slide. I want you guys to remember something else that's lost in a lot of self-driving car rhetoric. A self-driving car is not a car. I have no idea why Cruise and Waymo and Zoox decided to build cars. It's nonsense. A self-driving car is a dude. Hey, he's the self-driving. That's a car. We just want to build the self-driving. We don't want to build the car. The ultimate comma is not a device that plugs into your car. It's a robot that gets in the driver's seat. Right? That's where we're going. Why should we, you got to crack the Toyota security. Oh, no. Who cares? Build a robot that gets in the seat and grabs the wheel and turns the wheel. Now, don't do this tomorrow because it's not going to work, right? Having accurate predictions about technology is super important if you want to know where to do investment. I wish VCs understood any concept of this. But yeah, OpenPilot is a general purpose robotics operating system. OpenPilot, everyone always says, oh, well, you're going to die if you don't partner with car makers. Everyone's going to get security. Or, oh, my God, I don't care. I want to build a robot. I want it to cook and clean for me. But, actually do this. Not build up some hype. Right? In the same way Cruise told you they were going to solve self-driving and wasted $10 billion, you're going to see all the same stuff happen in humanoid robots. And guess who's going to be there to pick up the pieces? Comma and Tesla. Same people who are there today. The comma 9 is going to be that guy. Get your car. Yeah. Is it compatible with my car? Yeah, bro, he sits in the seat. All right, that's my talk. I'll take questions.
All right, do we have some questions? I just want to say I'm ready for the comma 9.
Yeah, right?
Do you see any reason to shorten that 2-year gap after Tesla? Would you want to make that shorter, or are you fine being at that?
So when you look at some of the fundamental things, like that training compute order of magnitude thing, so Comma's new compute cluster cost about $2 million. Tesla's new compute cluster cost about, at minimum, $200 million. Right, so it's even more like $500 million. So they're paying a ton of premium to be early. I don't think it's worth it. I'm certainly okay with being 2 years behind, meaning if you could have a sustainable business in the meantime. What might shorten that gap, if it turns out the comma 4 sells wildly more than expected, and we have tons and tons of money coming in, we may be able to deploy it somewhat to shorten that gap, but I can't even make any guarantees. Right? If I could make guarantees, maybe it's worth raising the money, But you can't make guarantees. But I do think that maybe if we, again, the most important thing is survival. So the question is not, do you want to shorten that gap? The question is, how much extra risk are you willing to take to shorten that gap? And the answer is 0.
I was just curious, when you speak about this being comma 9 and cooking and cleaning and all those sort of things, do you mean that literally, that the final form factor of a comma would be a general purpose robot
of course.
some kind? Okay, wow.
Yeah. Right? The car thing is just, again, cars are just the best applied AI problem that exists today. Self-driving cars are going to be solved long before humanoid robotics. Yes. But yeah, what, we're going to stop? Oh, guys, innovation's over. Let's exploit. Right? Yeah, let's crank up the monthly subscriptions on people. Let's put some ads in that shit. Yeah, what am I going to do with the money? All these people who are like, I got rich. What did you buy? There's nothing to buy. Taylor Swift statue, good point. It's actually, I think it can be done pretty cheaply. I'm not licensing Taylor Swift, by the way. It's called generic female pop star, if anybody asks. See, actually, I could probably do this today, but I would need, time.
So I share the sentiment that human robotics startups are dumb. They will fail. But what makes Tesla Optimus a good bet? Or is it a good bet?
Yeah, do you know what Honda Asimo was? So Honda, really in its heyday in the 90s, also built a humanoid robot. For a largely successful car company to take 0.1% of their operating budget and dump it into humanoid robots for press, great idea. For a startup to raise a huge amount of money saying they're eventually going to pay investors back, that's absurd. Tesla's building the Optimus. Tesla already has Optimuses deployed. They're already useful. They're in the Tesla showrooms waving to you. Right? That's sick. Right? Spending, $10 million, $100 million on a sick PR project for Tesla that may turn into something in the future, so worth it. Raising that kind of money, ridiculous. Right? The reason it makes sense for Tesla is because they're a highly profitable automaker.
Questions?
So to continue on and look at the chasm that exists from where it is today to comma 9, and that what we see now is body is kind of the beginning of the compute core for that. What are your insights around the grassroots-oriented applications for comma body to start stepping towards a dude who gets in the car?
Yeah, I mean, okay, so there's one example of consumer robots that actually works. Who knows what it is? Vacuum cleaners, right? So yeah, I mean, can the comma body vacuum? I mean, I want to do it a little bit differently, right? I don't really want to build a vacuum. My idea is can we just buy a vacuum off Amazon and then have the body grab it and vacuum, right? It should tool use, right? So I think once we're at that milestone, we've also considered the comma body for security. But then you realize that 95% of what you want is just a fixed mounted camera and a loudspeaker, and good software. Right, so you actually don't need the robot form factor for that. But vacuums are the first robotic form factor to pay for themselves. So once the comma body, once the general purposeness of the comma body is capable of grabbing your existing vacuum cleaner off Amazon and using it, then I think we can start selling the comma body into people's homes. But fundamentally, it has to come, and someone might figure out an application. Right? I don't know if the body is going to be talked about more, but our goal with the new body, the first body was $1,000. That's insane. Right? How can we try to charge you? We charge you $1,000 for a comma 4, and you'll use that shit 40% of your days, right? That's so worth it. But if you buy a comma body, okay, it's a cool toy. We got to price it more like a toy. So the new comma body is going to be priced at $200. And I hope that someone out there with a comma 4 and a comma body figures out some use for these things, and we'll productionize it. But I mean, I think Unitree's making the same play, right? We bought 2 of those dogs. They're cool, but they don't make money. There's no way to deploy this thing in a real application where it provides value to you. It's a toy. So yeah, we're targeting the toy market for bodies. Hopefully someone will figure out what to do with it. The software will get better. But yeah, until you figure out how to make the robot do something that makes money. Yeah.
All right, next question.
Hey, George. Hey, if you were looking to put me to work, how much would you buy me for?
Negative. Honestly, negative. And here's why, right? So much of the fact that things don't scale is due to managerial overhead. right? So if someone comes to you and says, how could you put me to work? You're actually asking something of me. You're asking for me to do something, right? And that's why it's negative, right? You got to pay me for that, right? The real way to be put to work is to go work on TinyGrad bounties. Just go work on them. Or go work on comma bounties, right? But yeah, no, I think yeah, I mean, God, we're getting to the point where the marginal utility of a human is negative, and that's scary, but.
All right, another question?
Thank you for the talk. I wanted to ask about the Chinese competition, especially like Baidu and these companies.
What about them? I think they make a search engine and a maps app that's kind of confusing to use.
I think they are making 500,000 trips a week.
Where?
Baidu in China.
In what city?
Wuxi, I think.
I haven't been there.
Okay.
I haven't tried it. I mean, again, probably what it is, I'm surprised by that. I mean, Baidu's stack was open source at the beginning. AutoWare. I don't know if it's still open source. It's AutoWare, right? Is that the Baidu one? Baidu Apollo. Yeah. Who was AutoWare was another one. Yeah. No, they were open source. Yeah, it was Apollo. I remember their moonshot rhetoric. I wonder what's still open source. I also wonder how teleop it is. So like, I think the Chinese are generally more open with showing you their teleop stuff. By the way, Waymo admits to teleop and you've never seen a picture, which means that the teleop's a lot more than you think it is, right? I think the Chinese actually show you, well, yeah, we hire people from this rural province to come sit in this gaming chair and drive you around. Okay. So yeah, no, I think that a lot of this like teleop stuff is just, it's not self-driving cars. It's cool and it might be a cool service, but it's not the same thing as solving the AI problem of self-driving cars. There's a lot of other fun problems to solve on the way. But yeah, I mean, that's kind of my take on Waymo and all of these kind of like robotaxi kind of things. It's actually cool, and it actually has carved out its own niche that has shipped, but it's not AI.
All right, we got time for 2 more questions. Anyone?
Thank you. Hi, George. You've been posting a lot lately on well, first you started Tiny and you've been selling the Tiny box. And then you've been posting a lot on external GPU. I don't know what you would call that, but some way to connect a GPU to MacBook.
Yep.
And so can you talk about, I guess on a small scale with that second thing, what you're hoping to accomplish, and then more broadly, what do you want the ultimate goal of Tiny to be?
The mission of Tiny is to commoditize the petaflop. So what that means is right now there's an extreme premium for NVIDIA petaflops. We'd like to bring the general price of the petaflop to only be slightly above the cost of the silicon and the cost of the power. That's mission 1. Mission 2 is to rethink about how software is made. Tiny has cut through every dependency in the NVIDIA stack. We're speaking directly over PCI to the NVIDIA GPU. Without NVIDIA's user space, without NVIDIA's driver, without anything from NVIDIA, without cuBLAS, without any of that. So I think that in order to get very reliable robots in the future, you're going to need an operating system that matches that level of robustness, of reliability. And I don't think that we're going to get that through things that look like the current stack. Tiny is radically 100x simpler than the existing stack, and that's what you're going to need to get reliability of things that, like, a human is never going to glitch out and slam their head as hard as they can into the table unless there's something seriously wrong with that human. Like, that's not like some probability. That will just never happen, right? With computers, oh, sorry, your kernel got stuck in a thing where it was servicing this interrupt for 300 milliseconds, and the motor was at full torque. Okay, yeah. So I think we need high reliability, deterministic computation. That's kind of what TinyGrad is. For robots, runs in comma already. So.
All right. George will be available also in the Q&A. So we're gonna finish up with his talk. Thank you so much, George, for that.
Thanks.
All right, this is Harald, here to talk to you more about robots. Harald is our CTO. Welcome, Harald.
Hello. Yes, I'm going to talk about robotics. So I lead the autonomy team at Comma, and what we're doing is we're building autonomy software for robots. So to start, I just want to make it very clear, if that hasn't been made clear already, is that Comma is a robotics company. I joined Comma 8 years ago because I was really excited about robots. I think any vision of the future that is exciting, that I'm excited for, is one that includes a lot of robots. And back when I joined, almost 10 years ago now, been there 8 years, it seemed like self-driving was just the best applied AI problem that would kind of bootstrap robotics into becoming the robotics future that we all kind of dream of. So I joined back then for that reason, and even today that still seems true, is that the most interesting developments made for robotic software are being made in the autonomous car space, and Comma is now part of that. So as part of that goal to develop that software, we want to make a useful robotics product. That's what I want to build. That's also what I want to buy. I think that's the kind of stuff that excites me. To make it a real business, you got to sell it for more than it costs to make. You guys saw the new comma 4. The comma 4 is a great step in that direction. Fortunately, my slides are not up to date as of this morning. And I want it to be open source. When I use products, it's really nice when it's open source because I think it makes it way easier to align the product and the software to what the consumer wants because you can just fork it and make it the way you want. If the ecosystem's entirely closed, you're just kind of at the whim at whatever this big company decides. Whereas open source, you kind of give people the option to improve it. And then this last point is something that I'm going to talk a lot more about in this presentation, and that I think is really important and also a big deviation from what people generally do in this space, which is no cloud whatsoever. Everything that we do, all the development, all the data, every experiment needs to happen in our data center, which we own, we control, and we operate. And I'll tell more about why I think that's so important in the future slides. So unfortunately, when I said robotics, some of you started thinking about humanoids again. And so I think it's important to just start this presentation with a reality check. And I didn't review anyone else's slides before starting today, so this is going to be the first of many deja vus. The good news about the deja vus is that I'm saying the same things other presenters said, which proves that we're at least somewhat aligned inside the company, as opposed to accidentally saying the complete opposite. But so, figure is dumb. Anyone who's trying to tell you that a robot's going to do your laundry in any of the next few years is just trying to sell you shares. That is completely unrealistic. There is no intermediate product that is being sold that does anything that even looks like that. So it's a completely absurd proposition, and that's just PR. They're trying to sell you shares, and we shouldn't buy it. So that part of the reality check over. I don't want to just be a downer and hate on fake hype. I also want to talk about some of the robotic products that actually exist. George already talked about this. Waymo is a real robotics product. I've used them. I think it's extremely cool. I like Ubers in that they get me places, but a Waymo is just a better experience. It's really cool to see a robot move down the street and be useful. You're alone in the car. You set the music as loud as you want. Nobody complains. It's awesome. It's genuinely really cool. However, there are some downsides. On the technical side, George already addressed there some form of teleop. Even though it's clearly a robot, it's not necessarily an entirely autonomous robot. But I think the bigger problem in terms of a robotics product is that you can't buy one. Any of you here have $1 billion, you still can't get to buy your own Waymo and sit in it. And also for them, it loses money. So it doesn't really satisfy these conditions that I set out as our goals. Then we go to an even lower level of reality check. What are the useful robots you can actually buy? In industrial applications, there's quite a lot. I don't know if you guys, one of my pastime for a while on YouTube was to just look through farming videos in the Midwest, and it's absolutely incredible what farming robots can do. You can have a few operators run what used to take 10,000 people to run 100 years ago. And a lot of this stuff now is quasi-automated. They live in some constrained environment, and they can have technicians, and it's very constrained compared to like a real-world environment on the road, but it is largely autonomous and extremely useful. Then we get to Teslas, which, they are autonomous robots. They might not be unsupervised yet, but they're a cool product that you can actually buy. And then the lowest tier is what useful things can I buy in my house? And genuinely, the most useful robots you can buy for your house are a dishwasher and a vacuum cleaner. There really isn't anything more sophisticated. So I think this is the status of things, and we should forget about this whole humanoid crap until there's something that looks slightly more advanced than a vacuum in my house. We can stop thinking about humanoids as the next step. So what's noteworthy about all of those actually existing useful products that you can experience today is that they all existed 10 years ago. 10 years ago, Waymos were operating. It wasn't an open beta. That was only, I think, 8 years ago that started. But 10 years ago, there were Waymos, and they were driving themselves to some extent. I had a Roomba 10 years ago that kind of did something. It's not nearly as good as it is today, but there was Roombas, there was Tesla Autopilot, dishwashers obviously quite a bit older than that. So I think the point of the reality check here is just that these things are getting better. I'm far happier with the current versions of ADAS. Obviously, OpenPilot has improved a lot. I'm far happier with my vacuum cleaner and my dishwasher, but it doesn't make any step changes. These type of step changes of you have a Roomba that eats your cable to all of a sudden you have a humanoid folding your laundry and comforting your dog, that is marketing hype. These type of step changes just don't happen in reality. If you want to create a truly magical technology that is useful, like a dishwasher is, that is integral to everyone's life, you need to iterate, and it takes time. You need to ship a product, and you need to improve it, and over time, you start to create something that if you look back and compare to what was there before, feels like complete magic. I think a clear example of this type of effect is the iPhone. A lot of people talk about the iPhone moment as if there was this step change that happened in consumer electronics where, we were all, calling people on landlines, and all of a sudden the iPhone came around and everything changed. But that's not really true. If you look at this graph on Apple's revenue, you don't even see where the iPhone was released. Even the iPhone, which felt culturally like a step change, still just follows a natural exponential trend. The launch, for those who are curious, is here. And as you can see, they started selling iPods, they started selling more of them, and then they started improving them. And obviously today, an iPhone is an incredible product. So the last thing I want to talk about, this iteration stuff and really driving this point home, is this is my favorite plot of iterative improvement. It's about the corn yields on American farms. This is how much corn you can extract from a fixed piece of land. That's something that people have been optimizing for a long time because it makes your farms more productive. And what's crazy about this plot is just how straight this line goes up from when the iterative improvements really started. What's crazy is nuclear power was invented there, electronics was invented, the internet was invented, and now we have AI. Yet in the plot of corn yields, all you see is that things just gradually get better because they iteratively improve, and these type of step changes just aren't really reflected in the data. So, with that said, I want to have the complete opposite end of the talk of trying to hype some kind of future fantasy world. I just want to talk about what do these iterations look like behind the scenes. We've talked a lot about the kind of models we train and kind of the autonomy software and how the autonomy software works. But I think there's a bigger picture that is worth talking about that we rarely fully describe, which is to make these iterative improvements to the model, you need all sorts of scaffolding and infrastructure, machines and tools, and I want to talk about how some of those work just to give more of an idea of what I think is the stuff we prioritize at Comma to make improvements to the driving experience. So we're just going to talk about some concrete engineering details. So one slide about what we actually shipped, just so that we have in context the kind of improvements that the tools I'll be describing actually helped create. So one big thing that we were working on, and we've had presentations and papers about this, we published a paper at CVPR about a new method to train the policy models, which are trained in a diffusion generative simulator. Some version of that we shipped to a recent release, and that recent release caused a engagement spike here, which is what we were really trying to go for. So experimental mode is the mode where OpenPilot controls everything, the steering, the gas, and the brake, and everything's completely end-to-end. And there was a lot of usability issues with that we were slowly trying to improve, and you can kind of see the effect those releases had. So this is basically over this year, we went from like, slightly over 20%. This is a noisy graph, but it's roughly a 5% increase in engagement that we've been able to achieve by doing these kind of iterative improvements, trying to improve the end-to-end longitudinal control of the models. So that in mind, that's the kind of improvements that we're talking about. So at the autonomy team, our job is to develop the models and also the control stack to improve driving on openpilot. But one thing we internally always talk about is that the real thing that we need to do is we need to improve the infrastructure, the tools, and the test. And this has been on the whiteboard at the autonomy team for basically as long as I've been there, which is that machine learning and this kind of robotics improvements is 90% is infrastructure, tools, and tests. The actual machine learning kind of happens by itself if you figure out the other stuff. And it says here too on our whiteboard, we got to make the tools and tests that make improving driving fun and easy. And that's really the key, is if you make the path of least resistance, the fun engineering, if that happens, if it's fun to improve it because the tools are so good, because the infrastructure is so good, it will improve by itself. So the real focus of our team and of really everyone at Comma that's trying to improve these things is to improve the experience of iterating on it, on trying stuff. So I talked at the beginning about running stuff on our own data center. So one really big part of these tools, tests, and infrastructure that we use to improve driving are the physical machines that all of this stuff actually runs on. So we'll start with just the workstation. This is all pretty standard, but I thought I'd add it here just for completeness. We have a standard workstation that basically everyone uses. It's just a Lenovo workstation. They're connected. We try to connect them all with 10 gigabit to the data center. It's just Ubuntu. It's nothing fancy, nothing super weird. And we have a mono repo that all of our code runs on. It's just one repository that we all have, and there's a Python virtual environment. So on our workstation, that's what the workflow looks like. It's nothing really crazy. It's all mostly standard stuff. So then where this stuff actually runs is in the data center. So here's a pic of our data center. This is a realistic picture of what it looks like. Some of our pictures are more staged, where there was more cleaning going on. But on an average day, it looks kind of industrial. So before I move on, I want to talk about the own and renting thing. I think this is really important. Owning the data center, I think, aligns incentives with experimental development so much better. The average engineer working in the autonomy team trying to improve the models, what they really want is just to make a model that drives better and that they can put on openpilot, because that's what makes us happy. Now, if you run stuff in the cloud, the easiest way to do that is just to spend more. You can train the models for longer, you can train the models on more data, and all you have to do really is to change the scaling factor, but also the spend. And so the path of least friction into making a better model in the cloud is just changing the budget, which that's not really great incentive alignment, because as a company, we're trying to make money. So the incentive alignment on our own data center is much better, which is you're using all of the compute already, but your model's still not improving as much as you want. So what do you have to do to do that? You have to change the code to make it more efficient, to make it train faster, so that in a realistic amount of time, you can get to a better driving model faster. So I think this incentive alignment is really important. And it also leads to other things like, if the data center is idle, if it's our own data center, we're encouraged to experiment, which is a good thing. You want engineers to use the idle compute to find out stuff, to experiment. In the cloud, every experiment costs money. So you're kind of disincentivized from experimentation and kind of incentivized from doing these large-scale production runs, which I think long-term costs just way too much money for what it achieves. So we need our own data center. This is what we have. It's been talked about a bit before. There are about 200 machines. Absolute max capacity is theoretically 400 kilowatts. We haven't achieved that yet, but we're working towards it. I mean, having more power usage means that, we're more effectively using the GPUs and CPUs, and as long as we're not running some kind of burn script, that's a good sign. We have about 1,000 GPUs. A lot of them now are these TinyBox Pros that you saw a demo unit of there. All of the data that we use for training is also stored inside this data center. We don't have air conditioning because power is very expensive in San Diego, so we just have standard fan cooling, and that works pretty well for us. In terms of software, they're set up kind of the same way as the workstation, so there's nothing custom there again. We just have Ubuntu running on them. They're managed by the same software in the back end, so that's all pretty easy. That was the highest power usage I saw when I was making this presentation, which was 235 kilowatts. However, we made some improvements since then, and made some, installed some more computers. So yesterday we hit 320 kilowatts, and once the full build out is complete of the Tiny Pros, we should be hitting closer to 400. So there's several services that we use when we develop stuff. For example, we have a data server, which you can ask for the driving data. We have model servers that you can ask for model weights of a particular model, and all sorts of kind of small services that are critical to the development that we do. And all of them run on just this picture of machines. This is about, in total, it's about 8 machines, I think, that run essentially all of the services. They're the masters for all of the services. These are just 3 big Supermicro machines. And then we have some of these Dell machines. I think one of them is the climate controller. Climate controller's data center is very important because if that fails, then kind of everything crashes. So that's a dedicated machine. One of them is a router. We have one that manages the data ingestion. And that's pretty much it. I mean, this half rack is really all of the centralized services that we use. They run everything. Everything else in the data center is just compute or data storage. So you'll hear a lot more about data in the next talk from Mitchell, but I'll just quickly give a fast overview. We download a lot of data from the devices when they're driving on the road. That includes camera files. It includes openpilot logs. It's just in 1-minute chunks. Right? We did some work to improve the ingestion. So right now we're doing about 1,000 hours a day. So that's quite a lot. I mean, George already mentioned it. We are the second biggest fleet after Tesla. And I think on a per user basis, we ingest far, far more data than even Tesla. So we're really doing quite well on the data aspect. And you can see there in our last few months, we really upped the ingestion. We released a model trained on a lot more data. So I talked about the data storage. So one of those servers that I showed earlier is the master, and then we have all these nodes that essentially have a bunch of hard drives in them. I think they're not sure how much one machine is. I think it's like 80 terabytes or something on one machine, and that's basically, that array is all the data that we have, and it's all stored locally. It's all non-redundant. If we lose it, it's gone. It's cheaper that way. We hope there's no fire, because then we'll have to pull in data all over again. So this is a distributed key value store. It's single master. It's open source. George open sourced it a while ago. So if you're curious how that works, you can check it out. But the key is it's extremely simple. Having one master makes things much easier and hasn't really caused many issues. So that's where all the data is stored, and it's just a web server request to get the data in whatever you're using. So data is one part, but the other part I talked about is that all the other nodes are compute. So there needs to be a convenient way to use that compute. You need to be able to just write easy code and then run that compute on all of the machines easily for the development to be fun. So we have this tool called MiniRay. Unfortunately, it's not open sourced yet. We're open to open sourcing it. It's just kind of hard with some of the, how it's integrated with some of our other stuff, but that's something that we're going to work on. Basically what it allows you to do is it allows you to write some arbitrary Python code, and then you send that to some master server that hosts the request, which contains some code and potentially some data, and then that gets sent to really any node that's a computer that has compute available that can run it. And every machine in our data center that's not doing something else is available as a MiniRay consumer, so it can consume these jobs and run this arbitrary code. Of course, GPUs are very relevant now. We do a lot of GPU work, so we make it support GPUs and have like a model server for efficient batching and that sort of stuff. But yeah, so you can write any kind of Python code, and you can access, of course, any of the data that's in the data server. So if you want to do any kind of driving experiments, you can do that. Not going to go through the specifics of this, but I just added this here. It's extremely simple stuff. If you want to run any Python function on all of the machines, like a simple function like isPrime, really you just have to write this code. It's written the exact same way as a normal thread pool executor in Python, and you can just distribute it across the entire data center. So we've really put a lot of effort into making this simple. You know, this is the result of many iterations of distributed compute, and this is kind of the final result. It's funny because in retrospect it looks obvious. We just copied the Python thread pool executor API, which seems obvious in retrospect. But of course it takes many hacky detours to kind of come to this clean solution. But right now, that's all you need to do to run if you want to run your isPrime function with 200 kilowatts, that's all the code you need to write. So just giving a quick example of how you would use this on an average day if you want to do something cool. So this function right here, this is a real function. This allows you to get a list of all the data in our entire data server. So it's several million minutes of driving, and we can enumerate all of the files in that whole data storage in just like 20 seconds. So all you have to do is do this, and you'll get literally a list of all data that we have stored locally in the data center. And then you want to run some stuff on mini-ray. So in this case, we can just run some easy thing like, oh, get the hard brake segments or something that might be interesting, and then you just display a video. And this is real code. This is actually code that exists in our code base. It really is this simple. It was a huge effort to get to this level of simplicity, but we're very proud of the state it's in now. So if you run that, the result you get is something like this. So this is something I ran like a week ago. It just goes through basically all the data we have stored and just looks for hard braking events, and they're just like some interesting examples of just weird things that happen on the road. This is all human driving. I mean, ADAS systems are not even allowed to brake this hard without AEB, so OpenPilot doesn't do this sort of stuff. This is just humans reacting to weird stuff on the road. And you can see all it took is like 10 lines of code, and you can kind of scroll through the data like this. This is another example. This, instead of looking for hard brakes, is looking for hard swerves. You can see a recurring theme is we've got people on the highway merging into your lane, and then the driver kind of avoiding that aggressively. We've also got like a deer here. If you look through this sort of data, you find a lot of animals crossing the road. Okay, so we've got the compute covered, the data storage covered. That's kind of the real physical hardware and what those machines do for us. Now we talk about some of the tooling that is basically used all the time in the driving development that we do. We call that Arena. What Arena allows you to do is like any kind of RL setup. You have an environment, you have an agent, and you can run a rollout. So that's really important because this allows us to run driving policy in the loop in a realistic environment, and we can kind of customize all that to either do some kind of test to figure something out, or we also use this for training. So here we have it running just the normal OpenPilot policy, the one that we released, in Carla, which is some kind of classical simulator. We do all sorts of sanity tests in environments like this. We can just make sure that it stays lane center, that sort of stuff. And here is again actual code of what that looks like. We have just some pretty verbose config. We can config thousands of things about these rollouts that are useful for different things. And then all you have to do is set the config, and then you run it, and then you get this. So this is, again, tooling. This was probably about a 6-month project to go from kind of one-off scripts that did this type of stuff to building a real tooling infrastructure with usable config that's way easier and way more fun to use. So that was, I think, end of 2 years ago, we started working on that. It took probably about 6 months to get this in a good state, and it's been way easier to do this sort of stuff since then. So an example of how we would use this, so that kind of simulation architecture, we can then combine that with the distributed compute that we have, and we can kind of run a whole bunch of rollouts all simultaneously on the whole cluster. And I'm showing you the results here of basically the changes that we made from shipping the models we were shipping last year to the ones that we're shipping now that have much higher engagement longitudinally. And this test makes clear why. So this test puts a car on just an empty simulated road here. Like this is kind of simulates an infinite long highway. And we just kind of put the car at different speeds. And our expectation is that OpenPilot understands the scene in a certain way, thinks about it, comes up with a good speed to drive, and slowly converges to that speed. Now, you can see the top plot is what we were shipping last year, basically, and you can see it just slows down forever, which is a terrible experience, and those of you who've used experimental mode will know that's how it used to work. If you're on a just empty, super long highway, it might just kind of slow down, and at some point you're driving 45 miles an hour on a straight, long, empty highway, which is obviously a terrible experience. And then here you can see what the latest models that we ship are. So it's not really perfect. It doesn't really converge to one speed, but you can at least see that the model is not so stupid that it wants to slow down to very slow speeds on the highway. At worst, it wants to drive 55 miles an hour. So we need to improve this a bit more, but here you can see this is the kind of reports that we're looking at when we're shipping changes and hopefully making improvements. So so far I've described the training, not the training yet. I've described some distributed compute for tests, the rollout infrastructure and the data. Of course, we need to train models. That requires quite a bit of infrastructure too. We recently switched, I think it's been about a year, to managing this all with Slurm. Actually, before we used Slurm, we would literally SSH into a computer and run a command. And if you were running it on multiple machines, then, I mean, there were so many ways to do it wrong. It was extremely inconvenient. But now this is done properly. It's managed by Slurm. One recent feature that's probably only a few months old is before we would have different code repositories that were accessible to the training machines that we had to specify and also make sure they were on the right stuff. Right now we just ship all the local code that's on your workstation, just gets copy-pasted to some shared drive, and the training run happens on that. So you don't need to manage multiple repos. Whatever is going on your workstation, the trainer is going to use that. Training's done with PyTorch. That's, I guess, pretty standard. Multi-machine, we just do with normal DDP, all very standard stuff. And then one thing that we've implemented, this is a few years old now, but I think it's been really helpful, is I mentioned about making sure that you can iterate fast, making the iterations fun. This is really important for development. And one thing we did is your training run just dies after 24 hours. If it didn't make it in 24 hours, well, sorry, it took too long. Of course, it's easy for someone to change the code, but it's slightly embarrassing. So this has been enough incentive to make people make the training runs faster. And so far, everything we release basically runs under 24 hours. Okay, so the other thing we need for training is we've got these machines that do training, they do training steps, they update the weights, but the weights actually have to go somewhere. So we have not just a driving data server, but we also have a server that receives all the model weights during training and also saves them and then can host them. So we call this Reporter. So Reporter is both an experiment tracker. It shows it shows every model we've ever trained since Comma started. This tool is incredibly old. It will show you all sorts of training graphs on the loss and all the individual stuff. And then we also have all sorts of different validation reports attached, so you can read through and get some kind of picture of how the model is doing. This is partially open sourced. We publish the reports on all the models we merge in openpilot, but we're planning to make some improvements to that. Yeah, so Reporter is the other critical part of training outside of the Slurm management. It hosts all the weights. It hosts experiment information for engineers to go through. And then the last part we need for the models we train is, I've talked about Arena before, how you can run rollouts with different agents and environments for testing and for debugging. But we use this for training too. Our final policy models are trained on policy, which means they're trained by generating data with the active policy running and then sending that data back to the training machine. And here you can see these are kind of the two configurations that we've used, which we describe in the CVPR paper. This is a classic reprojective simulator, so it initializes on real data, and then the driving policy can deviate from that real data by warping the scene and reprojecting stuff. And then this alternative here is one that simulates the entire scene with the generative diffusion model. And all the difference it takes, I switched these here, but so all it takes is changing the config here from MLSim to TinySim. And if you guys want to try it, that setup back there with the steering wheel, you can actually run the training rollouts and see what the model sees during training. Okay. So let's take a 5-second break here and let all these things come together. So the most complex task that we do at Comma, training or developing anything with driving is running a full training job on multiple machines where it's on policy, so all of the data needs to come from rollouts, from rollout workers, and then it's got to interact with all the data server and the weight server. So when we ship a model to openpilot, it's trained with just something like this, so it's just one line command on our workstation that you run, some basic config that you need to do. We show the data set, so the most recent models we trained were trained on 500,000 segments, the final stage. And so it starts at the workstation, and then you send the Slurm command to the trainer pods, and they pick up the job, and they start, so this is all model weights are synced with PyTorch, and then when they do a step, they send that to Reporter, which hosts the model weights and hosts all the experimental data, and then the rollout workers, which is what's necessary for the on-policy training, they receive the jobs from the trainer, and they receive the weights from the reporter, and then they send those results, the training data back, which is what the trainers use to iterate. And then in the back there, we have the data server that hosts all of the driving data. So, I mean, this is not super easy to wrap your head around right now, but this is a really good overview of basically all of the tools that we need to maintain to have a good experience training models. Some of this stuff is custom, some of this stuff is very different from what other people are doing in the space. Some of it's somewhat similar. Slurm's relatively popular, for example. I think companies like Facebook have a very similar setup to Mini-Ray to achieve the same thing. But yeah, this is how it all kind of comes together. And like I said, it's really fun to talk about, you know, what the actual model decisions we make, and Yassine gave a lot of information about that. But ultimately, to really make progress and really iterate on the experience with OpenPilot, all of these things need to be good first. There's no way to make good machine learning improvements if you don't have really good infrastructure around training models and debugging and looking at data and all that sort of stuff. So this is kind of the full picture of what's going on in the data center most of the time. Yeah, so with that said, the last thing I want to bring up is our next hackathon. We had a pretty fun hackathon with the comma bodies, where we were just doing some autonomous indoor navigation with the bodies. You run your own software on it, and the best people got a prize. I think there's actually quite a few people from that picture here. We had, we had the two of the winning members of the team, I think, are here. One of them is working at comma right now. And so hopefully, if you're interested in this sort of stuff, come to our next hackathon. And it's not really clear exactly what we're going to do yet, I think, but we know the dates, and we'll post more information about what the goal and what the prizes will be at that link. Right, thank you. So, got any questions? Now's the time.
Thank you, Harald. All right, we got one question in the front.
Hi, Harald. Cool talk. Crystal ball, when, if ever, do you see there being end user triggering of, like, when FSD currently disengages, you can say, you know, tell me why it disengaged, and it'll send it to Tesla, and then they'll use it as input, I guess, in theory, to some sort of training.
Yeah, I mean, I'd say the loop that's happening right now at our team is, you know, if people tell us, engineers look into it, and then that is somewhat of a loop, but obviously it's not an autonomous loop. I would say, rough estimate, within 2 years, disengagements are very actively changing the policy that's being updated, yeah. Like, that's something we're actively experimenting with, but haven't shipped yet.
Questions?
Hey Harald, great talk. I was actually curious to know the evolution of your entire infrastructure. Was it always designed to be this way, or very early on you had an infrastructure which looked very different from what it is right now?
I think this design is maybe 5 years old or so. I showcased some of the code to do these things, which I'm very proud of, which is why I added it. I think the core infrastructure was there, but the things were implemented in a very confusing, hacky way. And that stuff is things that have been improving even until recently. Where I, for example, gave the example of the Mini-Ray thing. Before, to run stuff distributed, you had to do some custom thing that was specific to us for no particular reason. That now is easier. And it's kind of the same thing with these training commands. So yeah, the core infrastructure is several years old, but the tools themselves being as good to use as they are now is recent.
Got it. And would you, what do you think was the bottleneck very early on to get to this level of maturity? Like, could you not have, I'm asking this from a very selfish reason, like we are also very early on in our autonomy stage, like we are a startup, and we are just wondering, like, is it worth it to spend time figuring out this entire infrastructure very early on when you probably do not have a lot of compute or a lot of data to work with? Or
I think if you don't have an immediate use for this type of architecture, it doesn't seem that useful to me. But I have to say that, again, when I'm talking about these hacks that we made that seem stupid in retrospect, I don't see why we ever made them. It feels like if we just made better decisions early on, we would have less iterations. But I think it always just kind of looks like that in retrospect.
You showed some results on Carla, so I'm curious, like, what part Carla plays in your autonomy stack. Like, is that purely for evaluating the rollouts? If you use it for training, do you think it transfers well to real-world deployment on 3 and 3x?
So our entire training philosophy is to train only on realistic data, end-to-end, and the assumption is that sanity checks in Carla, because Carla does not transfer at all if you train on it, can give a pretty good picture, because if you make good end-to-end decisions in the rest of the training stack, if you just pinpoint certain things and look at if that works, you can make some reasonable assumption that the other stuff works too. So yes, Carla is not used for training. It is only used for essentially sanity checks. But the sanity checks are very, very useful.
Hey, in one of the slides, it said that you were using PyTorch for the training.
Yes.
And just now you mentioned about distributed work and all that. The question is, why are you not using TinyGrad?
So TinyGrad is incredible at inference on the Qualcomm chip. On OpenPilot, it is easier to compile models, and they run twice as fast as they would if we didn't use TinyGrad. For training on NVIDIA chips, that's not true. So they're working on it. Hopefully we'll get there soon. I think the next step in using TinyGrad would be to do inference in our cluster. I think there's a few more things that need to be fast for training. But yeah, basically it's just not fast enough right now on our configuration of hardware.
Another question?
Hi, really great talk. Have you given any thought to what it would take to do on-device learning or transfer learning so the device could update its model?
So we do some level of on-device learning. Right now, OpenPilot Master learns the lag of your steering interface. It learns several things about the car. It learns several parameters of the vehicle controls. That is some type of on-device learning, though it's not deep learning. I think that will evolve to become more complicated and more integrated with the OpenPilot model, and eventually there will be on-device learning. But I think that's the state it's in now, and it's going to grow more complex, and it has been growing more complex over the years.
All right, last question up front.
Thank you. Do you plan to do full self-driving just using forward-looking cameras, or are you going to add more cameras?
Right now, we're really not interested in unsupervised driving. Like, we're just iterating on a better supervised driving product. I think the challenges are exactly the same. So from an engineering standpoint, I don't think this really matters. If there's ever a point where the disengagements are caused by a lack of sensor field of view, it's just a matter of making a different sensor suite. But I think the hard challenges are the software, not the sensors.
Thank you.
Thank you, Harald.
Thank you.
All right, please welcome to the stage Mitchell. Mitchell is on our infrastructure team and is going to tell you a lot more about our infrastructure and data sets.
All right. Hi, everyone. I'm Mitchell. I'm an ML engineer at Comma, and I'm going to talk today about what it takes to build a data set with 1 million miles of driving. So the first question we should ask is, why do we care about this? Like, what's so important about the data sets? Well, autonomy at Comma, our team is in the business of shipping neural nets that drive your car. And A very wise man once said that a neural net is nothing but a compressed version of your data set. In fact, I think we can be even a bit more explicit than that. The neural net is the data set. And if your data set's good, your neural net will also be good. And so, minus the bugs in the training stack that make it worse. So if we want to train the best driving models that we can, we need a good data set. So the second question we should ask is, why do we need 1 million miles? Like, why 1 million? Why not 1,000? And the answer to that is that Comma's data center has grown over time. From 2017, we had a little pile of servers. This is the oldest picture I could find on our Slack. To 2019, where our servers were in a garage, up to now, where we now have 15 racks of machines, about 200 servers, I believe, with something like a quarter of an exaflop. So we're getting up there. We're still a few orders of magnitude off the hyperscalers. But our compute has grown substantially over time, and that sort of presents us with a choice. We could train bigger models with all this extra compute. We could train on more data for longer, or we could do a bit of both. So how should we spend our compute to get the best results? Well, a lot of people have studied this question over the last 5 years or so, especially in the domain of language modeling, but also more recently for diffusion models. And what's been found, by and large, is that you want to do a bit of both. You want to train bigger models with bigger data sets. So you want to scale up both of them together. And you can kind of see this. This is an old chart from an old OpenAI paper. Every color line is a different size of model. Data set size on the x-axis. You can see over on the left side, our data sets are small. And the big models and the small models, they get about the same performance. The big models just aren't that much better. And then as we scale the data sets, as we go over to the right side of the chart where the data sets are really big, the big models keep getting better and better and better, and the small models kind of plateau off. So big models can take advantage of all this extra data, and they can improve substantially. But if we want to train bigger models and get that performance, we need big data sets. So that's what we're going to talk about. So the first step to getting a big data set is we have to collect some data. Harald talked a little bit about this. We're very fortunate that we have a lot of people out there driving with OpenPilot. So we currently see just shy of 7,000 daily active users, and we get, I think this is wrong, I think it's about 1,000 daily hours of driving uploaded. Now, of course, not everyone who is driving with OpenPilot is uploading that data. Some people opt out, some people just never really connect to Wi-Fi, and other people are driving on forks that aren't usable for training. But despite all that, of the roughly 30,000 devices that Comma has shipped in its lifetime, we have data from about 20,000 of those devices. So the majority of our users are uploading at least some data. We currently get this should be right. So about 1,000 hours of data per day out of the 10,000 hours that people are driving with OpenPilot. So we get a lot of data. We can see, not all users are uploading the same amount. The distribution sort of follows a power law. So some people are uploading a lot more than others, but that's okay. If we look at a breakdown of our data, we can see vehicle-wise, we got a pretty good diversity across a couple hundred different platforms, 35 brands. Geographically, we're not doing quite as well. We can see we have data from about 70 to 75 countries, depending on how you count. But the overwhelming majority of it is still from the US. So we've got about 86% of our data is still from the US. Hopefully, that'll become a bit more balanced over time as we continue to sell more devices internationally. So what data are we collecting exactly? If you've worked with OpenPilot, you probably know a bunch of this. When you're driving with OpenPilot, it's recording data in 1-minute chunks. We call these segments. And a segment has a couple files attached to it. We have 3 video files because there's 3 cameras on the device, so we have the video streams for each of those. We have a log file that contains all the messages being passed around inside of OpenPilot as it runs, and this tells us everything we need to know about the state of the vehicle, the device, the control stack, everything. And then we have a quantized log file that's about 20x smaller, so it might be just a couple hundred kilobytes. And this contains just the very most important messages that tell us, for example, whether data might be useful for training. So we record this data, and then we have to upload it. So when OpenPilot connects to Wi-Fi, like when you pull into your garage and park, OpenPilot starts uploading Q logs to Azure. So we receive these uploads, we spin through them, and we look for segments that we think might be useful for training. We mark these segments, and we request the device to upload them. So we're going to ask it to send the full segment along with all the video files and the full log file. So Athena D inside of OpenPilot receives these requests and starts uploading the full segment to our data center. And then our data center receives that data and copies it all into our distributed mini key value storage system where it's going to live for the long term. So at this point, we have a bunch of data. We've uploaded all of this raw data from our users, and now we have to make a data set out of it. So we have to do a couple things at this point. We need to decide how many segments are going to be in our data set, which segments we're going to use, and how we should split it into train and validation sets. So we'll go through each of these real quick. The first question, how many segments should we use? And you might ask, well, we have all this data, why not just train on all of it? Like, what's the point of not training on everything? And the answer is, we train models of several different sizes at comma. We have the biggest models, like the world models, that we're very interested in scaling to large sizes. And then we have some other models that are much smaller. And you saw from that chart earlier that generally the small models can't benefit as much from these large data sets. So you're just training on more data for longer and making your experiments all take longer for no real discernible benefit. So what we would really like is to have data sets of multiple different sizes. We might have a data set that's like 10,000 hours, one that's 50,000 hours, 100,000 hours, etc. So we'll have data set sizes spanning like a solid order of magnitude or so that we can use for different model sizes and architectures. So then if we're not going to use all of the segments, then how do we pick which ones to use? Well, there's a couple different ways that we could do this. The simplest is just, pick a random subsample. But we can do a little better than that. So you can see in this red shaded area here, remember this is the distribution of how many segments we have for all of our devices. So some devices have way more data than others, and that tends to have a lot of duplication. So people drive the same roads over and over again because they're commuting to and from work, for example. And so this red shaded area here from users with the most data, that may contain a lot of drives that are less useful or more redundant. And so maybe we just want to shade from or draw from the blue shaded area underneath, which contains the vast majority of the data anyways, and this gives us a little bit more of a uniform distribution across devices. Maybe we want to undersample US data. Like we saw earlier, the vast majority of our data is still from the US, and if we're only going to pick a subset, maybe we want to bias it a little bit more towards international data, just so we're getting a bit more balanced of a distribution geographically. Maybe we want to filter out engaged data. Like for some types of models, like the final driving model, we don't really want to train the driving model to imitate the behavior of previous OpenPilot versions. It sort of introduces a feedback loop, so that's not great. So at this point, we may want to remove the engaged data from some of our data sets. And then at this point, we may also want to run experiments with different types of distributions. So we may want to shift it towards, for example, more highway data, less highway data, more curves, more situations that the model really struggles with. This is the point at which we can shift the distribution a little bit in any way that we want to. So, okay, now we've decided what's going to be in our data set. We make some choices for all these questions, and now we have to decide how we're going to split between the train and validation sets. So the training set is everything that the model's going to see during training, and the validation set is what we're going to evaluate on to decide if the model is overfitting or if it's not learning properly. So normally what you would do is take like 10% of your data as your validation set, but there's a couple different ways that you can do this. The standard way in like an image data set would be, you just take 10% of your samples, that's your val set. But in our case, maybe we could think about just taking 10% of the frames out of the videos, marking those as the val set, but this is not really ideal. These frames are way too correlated. You can kind of see here, on the left is the first frame from a segment, and on the right is a frame 1 second later. It's a little hard to see with the contrast, but they look almost exactly the same. Like there's basically no difference between these frames. And so if one of them is in your train set and one of them is in your validation set, you're just training on test. So this is no good. This is leaking information into our test set, and that's going to make our models harder to evaluate. So we don't want to do this. These frames are too correlated in time. So another thing that we could think about doing is splitting by segments. So we take some entire segments and pulling those out and marking those as the val set. And this is definitely better. This is more like what you might see for, as standard practice for like time series data sets, where you pull out big chunks of time and mark those as part of your val set. But this still isn't as good as we would like, because you can see, for example, here, this is a road that was driven by the same driver several months apart. And you can see, again, they're basically identical, where the driver goes under this overpass and then makes a left-hand turn. And so if one of these is in our train set and the other is in our validation set, well, the model's learning some things about what the driver's going to do by looking at this data that's duplicated in our test set. And again, this is not what we want. So what we'll do instead is we'll split by device. We'll have some users be in the train set and other users be in the validation set. And this way we can ensure as much as possible that we're not getting any kind of duplication and that we're really splitting our data into clean train and val sets that have as little overlap as possible. So specifically, we take about 6% of devices plus all of the employee devices. We put those in the val set. We put everything else in the train set. Employee devices are in the val set because we want our experience when we're driving around San Diego to be reflective of what someone might experience with OpenPilot when they pull it out of the box and use it for the first time. So we don't want the model to know all about our commutes. That really wouldn't be fair. So, okay, now we've decided what's going to be in our data set and how to do our train and val splits, and now we need to get the data ready for training. We need to process it a little bit. So what kind of processing is involved here exactly? What do we need to do to get the data ready for training? Well, the primary thing that we need to do is run our localizer. So localization in robotics refers to essentially figuring out where you are and which way you're pointing at every moment in time. So in our case, what we're going to do is take a segment and we're going to run a Kalman filter that takes in the GNSS, accelerometer, gyro, and some visual odometry from the camera streams and stitches this all together into a trajectory that recovers the position and orientation of the device on every frame of the video. And you can kind of see this visualized here. Again, a little hard to see because of the contrast, but there's a blue path that shows exactly where the vehicle is going to drive. So this is the output of the localizer. And this particular output is super critical. It's mission critical for us. It's required for all of the models that we train, for the world models, for the driving models, for everything. And so we need to run it on all of our data. This includes the very biggest data sets, because the world model in particular is the model that we're most interested in scaling, and we want to use the largest data sets for. So up to the very biggest data set sizes, we need to run the localizer. Then we also have some auxiliary outputs, I guess you could say. These are things like lane lines, the lead car, that's just the car in front of you, detecting any lane changes or turns that might happen during a segment. And these are things that tend to be a little bit less mission critical. Lane lines, for example, are only used for display purposes. We don't use them for any kind of control. They're just nice to show on the screen. Lead car, we currently use that in chill mode, but as experimental mode gets better, that's also likely to become a bit less important. And lane changes, same deal. As we move to the future and potentially start doing more work with navigation, lane changes may also become a bit less important. So these outputs are only used by the final driving model. The world model does not use any of these. It doesn't know about lane changes or lead cars or lane lines or any of that. And the final driving model is generally trained on a smaller data set because that model is smaller. For a couple of reasons, we need to run it on device, but also there's a lot of factors that govern the scaling for that model beyond just making it bigger. And so making the model bigger is not generally the way that we find is easiest to improve that model. So because of this, the auxiliary outputs, we run them on less data, and they're a bit less important for us in autonomy. And so I won't focus quite as much on these outputs for the rest of the talk. So now we have our data set ready to go. It's all processed, and we have to actually serve it to the trainers. So what does that look like then? Well, so we've got all this data stored in mini key value. We actually have a couple of mini key value instances. You can kind of see the computers involved over on the right side here. We've got mini key value raw in red. This is the cluster that stores all of the raw data. That's the videos and the logs. And then we have the processed data stored in mini key value SSD, which is called that for historical reasons. That's over on the left side, and that's about 300 terabytes. So mini key value raw is about 3 petabytes. A mini key value SSD is about 1/10 of that and about half the bandwidth. So when we need to serve the data, this would be like a PyTorch dataset class that you're writing. We need to load the data out from mini key value. For the processed outputs, these are basically just stored as NumPy, like MPY or MPZ files. So either like a compressed zip or just dumped as raw NumPy, as raw bytes. Then the logs, if we need those, we can spin through those just using the log reader from OpenPilot, the same tools that are publicly available. And then we got the videos, which we need to decode. So we've sort of been talking around this up till this point, but the videos are H.265 files, they're HEVC, and we need to extract frames from these videos in order to train on them. So we can't do this in advance. When we decode the video, we're decompressing the frames about 100x. So on disk, the video file might be something like 70, 80 megabytes, but when we decompress it, it's going to be like 8 gigabytes. So we can't do this ahead of time. We need to do it on the fly. We just don't have enough storage space. So we need to decompress. We need it to be fast, or it'll be the bottleneck for all of this stuff. And we need to do it for a bunch of different things. We need to do it every time we train, and we also require the video frames for a bunch of the processing stages that we'll talk about in a sec. So how are we going to decode these frames then? Well, when I joined Comma back in 2020, we were using good old FFmpeg on CPU, and on a machine with like 24 cores, we were getting something like 400 frames a second of decode, which is pretty good. You're running lots of these in parallel, and that was enough performance for the time. But as our models get faster, we get more trainers, and we need more decode. That was no longer enough. So now we would like to move the decode off the CPU onto the GPU. Around 2022, we started getting computers in our data center with GPUs in them, and GPUs have dedicated decode hardware that can decode at like 1,000 to 2,000 frames per second on like a normal, consumer GPU. And so we would like to do this. The problem at the time was that we just didn't have enough memory to both run the models and do the decode on the GPU at the same time. So we got these really tiny little like consumer GPUs. These are like, I think these are like $100 a piece at the time, maybe less. And they have almost the same decode performance as the larger GPUs that we train the models on. So we just stuck a bunch of these in all our machines and used these for decode. And that got us like, again, 2,500-ish FPS per machine. But the problem with these little GPUs is like they take up a whole PCIe slot, and eventually you just want all of your your slots in the machine to be for GPUs that are actually running the model, because that's kind of the primary workload. So eventually we want to kind of stop using these and just run the decode right on the GPU next to the model. So thanks to some slightly better memory management, we can just run everything on the same GPU, and now on a server with 8 GPUs in it, we might get decode on the order of like 15,000 frames per second. So that's not too bad. We've improved quite a bit. So, all right, that's pretty much everything that goes into creating a data set. And with the rest of the time that I have, I want to talk a bit about a case study of how our infrastructure has changed over time and how it's improved. I remember when I first joined Comma, as kind of a joke, I stuck a sign on the door of the research team that said Department of Magic. And I thought that was pretty funny at the time. But really, the research team is not the Department of Magic. It's the Department of Tools and Infrastructure. And everything we do is really focused on writing better tools and infrastructure. Because as a team of like 7 people on autonomy, like the only way that we can continue to improve these models and ship a better driving experience to all of you is to make the tools and infrastructure better and keep them simple. So this is going to be a bit of a case study of what that looks like in practice and how our stack has evolved over time. So I talked a bit about the localizer that we need to run. This computes the vehicle trajectory across a segment, and again, we use this for everything. But we need to run a couple of things first before we can run the localizer. So this is what our localizer pipeline looked like when I joined in 2020. Specifically, the things that are most important are that we need to run orb features and we need to run a segnet. So what are those? Why do we need them? Well, again, the localizer is this Kalman filter. We're taking in GPS, gyro accelerometer, but those sensors on their own are not enough to give us the kind of accuracy we need for the vehicle trajectory. We also need information from the camera stream. So one easy way to get information from the camera stream is to use something like orbs. Orbs are a classical CV technique where you find key points in a frame. Those are things like corners or edges or points that are easy to recognize. And you track how those key points move between one frame and the next. And this kind of tells you how the camera is moving with respect to the scene. So we can do this, and you can see this in this middle picture here. We're generating all of these red tracks that show how the key points are moving as we're moving through the scene. But the problem here is that we want to know, again, how we're moving with respect to the static background. And there's also all these other moving objects in this scene, like cars that are passing us. We've got a car in front of us, and there will be key points on these moving objects. And those key points really mess up our estimation. So we want to get rid of those. We want to filter those out. And the easiest way to do that is with a segnet. We have a semantic segmentation model that we trained using the comma pencil dataset. This tells us like which pixels are part of our car, which ones are part of the road, and which ones are part of other cars, etc. So we can use this to figure out which pixels are part of moving objects on the road and remove any tracks that get matched to those objects. So all of that is kind of a lot. So we can see kind of all of what's involved there. This was the state of the localizer stack in 2020. And then in 2021, we launched the Comma 3, which now has 2 forward-facing cameras instead of 1. And so that means that we need to run the orb features and the segnet on 2 video streams instead of 1. And that means everything is twice as slow. So in 2021, it's, again, a little hard to see, but it took 85 minutes to run 1 minute of driving data through the pipeline. Now that's pretty horrible. Like if we do the math on that to figure out like how long it's going to take us, we had about 1,500 compute cores at the time. That number is for a single compute core. But even so, to run 1 million segments through the localizer would take 40 days. Now, not only is that completely out of the question, but it also means we can't run any more than 1 million segments. Like if we wanted to run 5 million segments, that would take months. So this isn't going to work. We need to speed this up. So what can we do? Well, the first thing we need to deal with is the SegNet. The SegNet on its own is taking 60 minutes. And a large part of that is because it was running on CPU at the time, like just using Onyx runtime. And so, like I said, around 2022, we started getting servers in our data center that had GPUs in them. And so first order of business was we need to run the SegNet on the GPU. So step one was just move the decode over. We already talked about that. Then we want to run the SegNet on the GPU as well. Onyx runtime has a GPU backend for NVIDIA cards that works great. But then we were running in a fairly memory-constrained environment at the time, and so we could only have a couple of model runners active at any given point. So that still wasn't great. So then we switched to Triton Inference Server, where we can batch up a whole bunch of requests, send them to a server that's got a couple model runners in it, and get the requests back and write them out to disk. And this way we can have a lot more going on in parallel, and we get better performance. And then lastly, we can quantize the FE16. This one's a no-brainer. Like we were running in float 32. By using half precision, we can almost double our inference speed. So with all of that considered, we can go from about 60 minutes down to 4 minutes for the SegNet. So that's a huge improvement already. And with that change, we're now down to 29 minutes to process 1 minute of driving data, which, again, that's a lot better, but it's still not good enough. We still need to improve things. So next up is the orb features. The orb features are taking 17 minutes now. So that's now about half of the total time to process a segment. So we need to deal with the orb features somehow. So the orb features have a few problems beyond just the fact that they're slow. They're running on CPU. We can see from the video here that there's a lot of incorrect matches. So this is cases where like a key point in one part of the image is incorrectly being matched to a key point somewhere else entirely. And this gives us all these outliers, all this garbage that we need to filter out somehow. So partly because of that, we need to generate a lot of tracks. So this image right here, I think we have maybe like 600 tracks per frame. And then they're tracked over multiple frames. So you'd be like several thousand tracks at any point in time. And partly because of that, the localizer is way slower than it would be otherwise, because now this Kalman filter has a few thousand additional inputs, and that just slows everything way down. So not only is the orb features like really slow, but it's also making everything else slow. And not only that, but the SegNet is only used in the localizer stack to filter out moving objects. So what this means is if we could somehow delete the orb features, we would get rid of the SegNet, we'd get rid of the orbs, which are the slowest stage right now, and the localizer would be way faster. And now the problem is we can't delete the orb features. We need some kind of visual odometry because otherwise the localizer just won't be accurate enough. But what if we could replace the orb features with like an open source visual odometry model? Over the last 5 years, there's been a bunch of really good ones. Models like Lofter, Flowformer, Tapier, just to name a few. There's been a ton. And these models look great on paper. Like the demo videos are super compelling. You can see the points being tracked over time. The problem is when we take these models and we run them on our data, it's not very easy to see with these lighting conditions, but Lofter is like completely garbage in these low light conditions. Flowformer is like slightly better, but when you look at the tracks that are being output, they're still basically unusable. And the problem is these models just struggle in a lot of real-world conditions that we see in our data set. And you can kind of understand why when you look at the data sets that these models are trained on. Like the largest data sets for these models are like all synthetic. They're all generated with like a traditional graphics engine, like Unity or Unreal or something like that. Kubrick is one such data set that's quite large from Google. My personal favorite is Flying Chairs. I don't know if you can see it from there, but you can probably guess from the name what's in it. So those aren't great. And then even the data sets that are based on real data, like ScanNet and Kitty is actually driving data. So that should be perfect, but it's all during the daytime. And it's also a fairly small data set. I believe it just contains like a few dozen hours of driving max. Might be even smaller than that. It's been a while since I looked at it. So these data sets are just not enough. And these models, because of that, really struggle in situations where we need them to work well. So if we're going to make this work, we're going to need to train our own model. And you know, that sounds great, but where are we going to get the data? Like, we just looked at these data sets, and if we just train a model on those data sets, we're going to run into the same problem as all these other models. So we need a data set somehow. Where are we going to get it from? Well, the idea that we had was, what if we just train it to predict the orb features? Like, the orb features have all these problems, but most of these problems are actually fixed if you just have a model predicting the orb features instead of using the raw ones. And you'll see what I mean here. So basically, the setup that we want to do is we'll input like a pair of images that are just two adjacent frames from the video. And we'll ask the model, we're just showing a little patch of the image here, we're going to ask the model to predict whether or not there's a key point on each pixel. And then if there is a key point, we'll ask it to predict how that key point moved between the two images. So we're asking it how this point in the image moved to the next frame. And then using a loss function like Gaussian NLL or Laplacian NLL or something like that, we can also recover an uncertainty. So the model can tell us directly how confident it is about its motion prediction. And that's great because the localizer takes uncertainties for each of its inputs. And so we can feed those confidence outputs directly into the localizer and improve the localizer pretty substantially this way. So putting it all together, this is our neural orbs model. And we can see that right away, there's way fewer of these garbage features. There's fewer features overall because we just take the very highest confidence ones. So that means we're putting fewer of these features into the localizer. And the model runs about 4x faster than the old orb feature stage. So we've improved this a bunch. We get rid of the segnet. We'll use the segnet to train this model and remove all the orb features on moving objects. But then once we have that, we can throw away the segnet, and we no longer need it for the localizer stack. And best of all, this change makes the localizer about 5x faster, which is crazy. Like this improves the entire pipeline just from this one change. So we can see this was the state of the localizer stack in 2024. We got rid of all of these parts that were here before. The localizer is down to 1 minute and 20 seconds. Neural orbs takes like 3 minutes and 20 seconds, and the total time is down to just over 5 minutes. We can clean things up a little bit further even. We have this log processing stage, which was just reading in the logs and writing out a bunch of intermediate outputs to disk. That's kind of silly. We can just spin through the logs as we need them, so we'll get rid of that. We've got frame index and frame times, which is just reading some metadata from the video streams. We can combine those into a single stage that just does all of the metadata that we need from the video and saves that. So putting all of that together, this is where we're at in 2025. We have one stage to get the frame metadata, one to get the visual odometry, and one to run the localizer. And the whole thing is done in 4 minutes and 50 seconds. So that's a big improvement. We're booking right along, and the total data center throughput across all of our servers now is just shy of 2,000 segments per minute. So what that means is we can now process about 1 million segments in 8.5 hours, which is great. Remember, we were at 40 days before to do 1 million segments. We're down to 8.5 hours now, which I think is like 110x improvement. So about 17x comes from all of the changes that we just discussed. And then the remaining 6x comes from just getting more servers over time and growing our data center. But of course, we're still not done. We can still make this faster, and we can have even bigger data sets. So there's at least another easy 2x speed up on the table. We can do the decoding inside the Triton server, because at this point, creating and destroying the decoder objects actually takes a pretty significant amount of time. So just by keeping the decoders around for longer, we can make it faster. We can use a faster runtime. Like Onyx runtime GPU is not as fast as it could be. Torch compile is like almost 2x faster if memory serves. We can quantize to in date. That's another free speed up as long as we don't lose any accuracy. And then finally, we could potentially combine the neural orbs and localizer stages into one, since the localizer is the only thing in our stack that really requires these visual odometry outputs. So we could save writing them out to disk and reading them back in, and that saves probably another 10%. So if all of that sounds interesting to you, I'm repeating what's been said earlier, but Comma is hiring. If this part of the work sounds like fun, come work with us. Do the hiring challenge and help us build a 10 million mile data set to get the next scale up for our models. And that's all I got for you. Thank you.
Thank you so much. All right, we have time for a few questions for Mitchell. Any questions?
Great talk. How does the left side driving data affect the training?
So we explicitly detect left side driving data just based on geography, and then we can use that to have a model that predicts which side you're on, just to validate those. It doesn't affect things too much because in all cases, like the localizer that you're running is the same. So the model may need to know which side of the road you're supposed to be driving on, but all of the stages up till then are completely agnostic.
Hi there, another question.
Okay, so you send back like a really short like log for all the road segments, but do you like on that look for key features like hard braking, hard steering, stuff like that? Be like, hey, we probably want to get those road segments back.
Yes. So the uploading, we have some of that information in the queue logs that we can scan through if we want to. Currently, we don't prioritize uploads that have like hard braking or hard acceleration. Although we've talked about doing this, this may be something we do in the future. But we have quite a bit of that data in our full data set, and so we can choose if we want to train on more of that data or to train the model to predict that kind of thing. And so that we do a little bit of.
All right, we can maybe take one more question.
Yeah, it's a great talk. One question is, previous talk I talked a little bit about the change in the dramatic change recently in better engagement, higher percentage. Does that fundamentally change how you decide to choose segments that you want to keep?
Right now it doesn't, because the differences are small. Like we're seeing maybe a 5% increase in engage time, but potentially yes. If we're at the point aspirationally in the future where like 90% of all of our drives are engaged, at that point, we might want to start to pull more specifically from data where the human is driving, just for that reason.
All right, guys, Mitchell will also be available in the Q&A if you have any more burning questions about his talk, but we are going to keep it moving. Next up, we have Robbe. So thank you, Mitchell.
I'm good, thank you. Perfect. Great. Good afternoon, everybody. Sure, you've all seen my my title on the the itinerary for today. It's actually not the full title. Obviously, after the launch, everybody knows what it's going to be about. Comma 4. Concept of shelves. It's quite interesting. You don't really see any other companies talking about this, but I think it's very important to share like what happened during like the process of getting into the device that we have now. I would like to see more companies do something like this. So 2 years ago, I also did a talk also about hardware, about manufacturing in our office. To recap that a little bit, because it's still quite interesting. I talked about like this general like flow of like how a product like comes to be and it gets into your hands, where we start from like a general like vibe of what the concept should be. We go into like first design stages, we prototype it, test to see what's broken with it, then moves to production once like the design is finalized, gets to the consumers, and then we do the repair stuff. So what I talked about last time was like, okay, so we get the PCBs in, we have like our own manufacturing line. It's actually a picture I took yesterday. So all the 3 axes that you guys have received are all built on this line you see over here. But we've recently been setting up the second line, which should be even faster. So hopefully the 4 axes will run off the line as quickly as possible. So you deposit solid paste, you put on the components, you make sure that everything looks correct, and then it goes into the assembly room where all the components are mounted onto the board, and then it goes into the testing rack that Adeeb and other people have talked about before. Okay, so that's a quick recap. Let's go back to this. So last time I really talked about like the second half. So now let's focus on the first half. We really start to dive into like how do we get from the concept into like the production design that you guys saw today. It always starts with a code name, which we call Misi, and some wildly optimistic thoughts. I don't know if you can read this, but it's January 14, 2023. George posted, okay, let's start with something called the comma mini. So it's supposed to be small. I think we achieved that. It's going to launch at CES 2024. I don't know if you checked your calendar lately, but almost achieved it. And really the concept back then was like build like the absolute bare minimum thing that we could buy, that we could build. That still gives you like 80% of the value of the main like 3X that we had back then. And we figured it would look somewhat like this. Like it would look like a stock Alcas camera, but maybe have it be like passively cooled. It wouldn't have a display because like we need to display like a stock Alcas systems don't have this. We wouldn't store any training data. We wouldn't upload it back, so it didn't need any LTE, so we could drop that. We thought like, oh, well, like Toyota back then was like half of the fleet, so maybe we just only support Toyota. We put like the Toyota connector on there. We increased the narrow road camera field of view to make sure that like you didn't need like a special mount for like the cars that have like the tilted windshield, and really like minimize all the production steps. Like if you think about it, it's like this is all it really needs to be, right? Like it's one like die-cast metal piece. You place on one PCB there. You have like the other PCB with the cameras on there. That's all you really need. And I don't know if you like if you go to this link, this is some other company designed this, and it looks so uncannily like the thing we came up with back then. It's crazy. But then we thought about it more, and like, well, having no display, I mean, that's really annoying, right? Like, how do you set it up? Like, how do you get this thing? You take it out of the box, you put it in your car. Like, you have to like connect it to Wi-Fi. Like, you can't input anything. There's no buttons. Like, you have to like make a good app. You have to like, support Android, support iOS. We're historically not very good at any of this. So we thought like, okay, let's just put a display on there. And from our experiences, like getting a custom OLED made, like in the shape that you want, that's basically impossible. Like if you're like a Samsung and you want to build like a Galaxy Watch, all the stuff's very easy, right? Like you have like, you buy like 1 million of them, you spend like a few $1 million, everything works. That's just not really the scale we're at yet. On the other hand, LCDs, they're a little easier to like customize, but we've tried this before, but like in the 3X stages, like prototyping stages. This is actually a picture of that I pulled from our Slack, where you can see like, okay, we put this thing in an oven for a few hours. These LCD panels are really not made to like withstand like higher temperatures you would see on a car dashboard. And so this is also not really an option. But fortunately, we're looking around the markets, and we finally found a company that like makes like a very nice, tiny, like little AMOLED display. It's like almost the right form factor, right? Like you can imagine, like this is like this height. It kind of like matches the driver camera. The width is roughly like what we would expect for the device we wanted to build. Like this is great. And the thing is, you don't even have like, you don't want it to be square, right? Like that doesn't really fit in any device. But if you can just replace the front glass, which is a lot easier to customize, you can actually make something that looks pretty nice. And so that's the thought that we went on a little further. Contrast isn't great. But I really had this concept of this thing, like maybe we can make it look like a Mac Mini, like with like nice rounded corners, you have like a nice rounded display. And it actually kind of looks like the comma 4 we ended up building. And thinking about it a little more, it's like, okay, like if we already added back the display, why don't we just make it better than a 3X? If you just add back LTE, which can't be that hard, we add back OBDC, so we support all the cars. Like, there's really no drawback in having this device versus a comma 3X. And instead of calling it a comma MISI, let's just skip that, comma 4. So just build a new flagship, that's great. You don't have to support like 2 different product lines. This is gonna be amazing. So once you have this concept, I mean, that's all still in like magic land. Like everything looks great on a computer screen. Like obviously it doesn't drive your car. So you want to get something driving as soon as possible. That also means that you have like a product you can hand off to like, for example, the openpilot team, so they can start working on like the UI. Like, how does this thing look like in a car? Can I design like an interface that like works with this? Probably, possibly, like very well. And you can also like test out different refactors you want to do in the electronics. And so this is something that we really thought about, and we really tried to optimize like the first prototype to be driving as soon as possible. And most of the important things, like one of the most important things to get something driving as soon as possible is you really have to select like which processes you're going to use. Like you don't want to do anything fancy that would take like months of lead time from like different companies or something that like only one company in the whole world can do. You really want to stick to like the basics, like 3D printing for the case. Or if you want to do a metal case, you just have it CNC machined. Like that stuff is all super easy, and you can get it done in like hours or days. The electronics, that's a little less easy than the mechanical parts to speed up, because like, if you want to put something like a Snapdragon 845 onto a PCB, you really can't do that on like your standard like JLC level 4-layer PCB. Which they produce in like a week, but you really have to step up to like an 8-layer board which has like vias that don't run all the way through the board, but like go from like, for example, like layer 3 to layer 4. And these things like, they take weeks and weeks to produce. It's not even just production time. Like these things, they actually take 6 to 7 weeks to produce, but they also take like 3 to 4 weeks to even just like design and route out. Like you don't want to do like 50 revisions doing this, because you'll just be stuck for years. And then for the other parts, like if it's not broken, like just don't fix it. Like just take parts that already work. Like from, for example, the 3X, we already had a heatsink that worked, and just like stick it on there. Like this is also the board that we designed for the 3X, which has the 845 already on it. So we figured like, oh, let's just reuse this module, get it on the first prototypes, and it'll be driving like immediately. And that's exactly what we did. So from the time we started the design, we had PCBs ordered in 9 days, and then after 13 days after that, we had the first thing booting. And so that means that we could hand it off and get like all the development teams start working on software, firmware, that kind of stuff. And only 3 days after that, we got the first one driving in a car. Now, I do say driving. It did drive, but the screen is still black. It's like, obviously, like prototypes make mistakes. The screen didn't come up. Like every time we plugged in a screen, we see like a puff of smoke and be like, oh, something's not right. So the connector was mirrored. I mean, it happens. You only make this mistake once, right? Well, you just design a small PCB. You don't want to respin that rigid flex board because it also takes like 2 weeks. You just make like one simple 2-layer PCB. You get that in like a few days. The display is up. Everybody's happy. So that's kind of what this board looked like. I mean, it worked. I posted it to Slack, and then in the same vein that Shane got the feedback from Adeeb saying like, oh, this should only be 10 lines. This feedback was immediately, that looks like way too much stuff. I kind of agree. Like, In the end product, you see now, like, at least 25% of the components that are on here are just removed, like refactored out completely. Like we got the STM to do like the audio codec stuff. We replaced the beeper with like just driving the beeper signal through the speakers. All the stuff that just you don't need. And you just reduce complexity massively this way. Okay, so we had the SOM prototype driving. I mean, that's obviously not something you can just refine on and ship. So we really had to think about, like, okay, what is this device going to look like in the end? And the main driving factor for that is, like, what is the case going to look like? Like, you can't design like this complex PCB and change the shape because all the components move and you have to move all the traces. That just, every time you do like an outline change, that takes like weeks to materialize. So we thought about it a little bit, and I like my Mac Mini design. There were other people in the company that didn't quite agree, and one morning I woke up and I got like this image. I don't know if you can see it very well, but it's just like Play-Doh mashed together into like a potato chip shape. And they were like, yeah, it needs to look organic. Like, oh, okay. So I came up with something that looked like this. I got really into like the fusion design tools to like make organic shapes and stuff. It's really nice. Igor, our mechanical designer, did not agree. So we completely threw that out of the window. And also, like, if you try to fit any components in this, like the curves just don't really work. Like anything you want to put in there is square, it just doesn't fit. And so like, we botched it out a little bit, and like you could kind of like start to lay out components. Like we thought, like, okay, like this is going to be like a nice die-cast aluminum case. It's going to be passively cooled. But like in some cases, you might want like a little bit of like active cooling. So we fit in like this blower fan to like get some air moving through the case. We laid out all the ports that we needed. We laid out the camera bar, the LTE module, the speaker, all that stuff. It kind of fit. And so after a few more iterations and design, we came up with this, which is the Rev A case. As you can see, like it's still like it's supposed to be made out of metal. It's still die-cast to like get the passive cooling working. You had like this big surface that would like the 845 would heat sink into, distribute out over the whole surface, and then would just like mostly cool itself passively and be quiet. We kind of proved this out as well. It's like I posted this on Slack a little after that, and I like made like a very simple mock-up that we could simulate, where we dump in like the 6 watts or whatever the 845 outputs. And then so like, okay, if you have like 25 C air and move up roughly 1.2 meters per second over the surface from like natural convection and like car, like air currents moving in a car, this should just work. It turns out like both of these assumptions are completely wrong. There's no convection in a car. The forced cooling never hits the windshield. It's never 25 C. The air next to the windshield is so hot. This was completely off. But anyway, we didn't know that at the time, so we started laying out the Rev A. We put this nice big hole in the PCB where like the blower fan could sit on the other side. It could suck in air and then exit it through the top. That seemed like a good thing to do. We like had some trouble like laying out all the components on the board, but like it all kind of fit. We got it to work. We put that into like a flow simulation. Like, okay, it pulls air from the back. You can see like it moves like under the PCB, so it moves over the aluminum surface to cool. It pulls it up through the blower and shoots it out to the front. And like, that might work. So we routed it out, we sent it out, and that was our Rev A of the MISI. Of course, as I talked about, this is already like the high complexity PCB, like a high density interconnect PCB, so it would take like 6 to 7 weeks to produce. And we didn't really want to wait on those 7 weeks before we could start stuff like mechanical design. So what we did is actually we just took the top and the bottom layers of the PCB, and we just sent it out as a 2-layer PCB. So it looks and functions exactly the same mechanically, but there's no traces in there. Like, it doesn't do anything. But it's still very useful, because mechanically it's completely equivalent. And you can get this in a week. We didn't make one mistake though. Usually the stuff that we intend to work, we make black, because that looks the nicest in the case. We figure like, if we want it to be mechanically equivalent, we'll also make this black. Turns out you just can't tell it apart from like a real PCB anymore. So I predicted back then, like how long is it going to take before we're just going to waste like half a day trying to figure out why this thing doesn't boot. And it didn't take very long. Okay, so once you got the real MISI Rev A PCBs in, It only took a few days. We got it to boot, so there was no like fundamental big issues, except like the cameras didn't work and the display was still black. We did it again. This time it was like just 180 degrees. So oh well. After fixing that though, just a few days later, we have the first actual drive of a MISI in a car. MISI Rev A, August 22nd, 2024. Okay, it's almost up and running. Like, it kind of drives. Like, we're nearly there. It'll ship in like 2 months. It doesn't. Of course, Rev A, you make all these like tiny mistakes. We track this in GitHub. We have just make like a big list of all the things we want to improve for Rev B. There's nothing too spectacular in there. Like looking at the thermals of that first drive, which you could have seen, like this was like the sun was already setting, it wasn't very hot out, it was like the car was like nicely cooled and AC'd. The thermals of the CPU, they just kept rising through the whole drive. Like it just didn't really perform passively like we thought it would. And so we thought like, okay, let's dive into the first principles, right? Like you have this 845 processor that we get from Qualcomm. That's soldered to a PCB, and then because it's usually used in a phone, they're very like space and power efficient to put the RAM like right on top of the chip. So it's actually like a chip you solder on top of another chip, which is great in phones where you have like very bursty loads. You don't really care about thermals all that much. But like with sustained loads of OpenPilot, this really limits like the thermal interface between like the die that actually produces most of the heat and like the heat sink you want to put on top of it. With 3X, we didn't optimize this all that much. Like what you basically have is just to put the heatsink on the top. It just mostly flows out of the top, and it's like mostly fine. But then we also figured out like this PCB is actually like 8 layers of copper in there. There's a lot of interconnects, so it's actually like thermally decently conductive. So what if you just also cool it from the bottom? Turns out that Qualcomm actually publishes pretty good high fidelity like thermal models of their chips. They can just simulate this. And turns out like you could get at least a third of the heat through the PCB out of the bottom. So that's already like an easy like 33% improvement that you just get for free if you design this in. We also validated this. So this is what we call the shot glass test. We just got a copper shot glass, filled it with water. And then if you run a constant load on the CPU, you can just like measure the difference between the CPU cores and the water temperature. If you diff those, you just get a flat line, and it gives you the exact temperature difference from this actual CPU die that you're trying to cool and the outside environment. And that's the best you can do in this setup. And it's like, it's still not really good enough. Like, is there anything else we can do? Like, you can see this like big air gap here, right? Like it's in between the balls, it's on the top of the processors, and like air, it's not very conductive. Everybody knows this. So what happens if you just add some epoxy in there that's like somewhat thermally conductive? It just fills all these gaps in, and it really improves thermals. Like this change alone, like improved thermals by at least like 1 C per watt, which is pretty massive in the things we try to optimize. And as an added bonus, because it's epoxy, it also like mechanically bonds the chips to the PCB, and that greatly improves reliability. So this is kind of what it looks like. So this is not a chip you're looking at. This was a chip. It's underfilled, and then you just mechanically like break it off, and you can see like the epoxy filled like all the empty space next to the pins. Another issue we found on the early MISIs is it's a metal case. If metal is at like 50 or 60 C, if you touch it, it's not good. It burns your fingers. The device is still running fine thermally, but like it doesn't really feel like a high quality product, and like it's just not something we wanted to ship. We tried to improve it. I made like this cyber MISI design, which I thought looked kind of cool. Like, the team wasn't very convinced either. But if anybody like wants to make this, I'll buy one. So we still have the metal case back there. And like this is also validated in the plots where like we didn't realize this, but a lot of the heat input actually doesn't come from the electronics inside, but it comes from just the sun like shining down onto the device. Like especially if you drive around in California or like the lower states in the US, you could see like one of these is case temperature. That's case temperature. It just keeps rising and rising and rising. It doesn't dissipate into the air. The case just gets way too hot. It's just not very good. We simulated this. So we made like a small little fake windshield with a device on it. We had like an IR heater that like we got to somewhat match the sun output, and we couldn't really get the metal case to work. So let's just cut our losses, let's just redesign it completely. And instead of dumping all the heat into the case, we know we can extract like 66% of the heat out of the top of the chip, which we could then put in like a nice heat pipe with like a fin stack that we would see in like a laptop. We simulated this, that does seem to kind of work. So we got that made. And we stuck with this design like all the way from Rev C to Rev F. It caused so much problems. So one of the issues you have is that you really need the surface contact between this plate and the 845 to be as flat as possible. So we designed this to be on spring screws. But you can see in that picture, like spring screws are way too big, and nobody really makes the smaller ones that we needed. So then we got custom screws made. Okay, the custom screws, that looks a lot better. But then like the fan standoffs, like do you really want to put like all the screws in, and like it has like little like capped on labels on there that get everywhere in production. So we designed custom standoffs for the fan. We figured out like, oh, we need to optimize the intake pads. So then we added like a big hole in the front of the case. We put like an extra fan on there, and it just turned into this whole big mess. We even came up with this monstrosity at some point because we figured out that like one of the fin stacks just wasn't quite long enough to like be super efficient. So we like doubled the fin stack up. We added backside cooling. We added a fin stack in there. It just didn't really, like we could kind of get it to work somewhat on a 3x level in this form factor. But also right around this time, we figured out that the GPS performance wasn't actually quite what we hoped for. Like if you look on this graph, like the bottom line, that's the horizontal accuracy that a 3x would get on a route. And the one on top of there, that's one of the early production, early prototype Mises that we built. And it's just a lot worse. So that turned into a whole thing as well. One of the most annoying things is that the 845, because it's like, it has so many sub-blocks and it runs at so many different frequencies and PLLs, that it outputs harmonics basically like in the whole broadband spectrum around GNSS. So you really need to shield it. Like on the 3X, it's like nice, it has like its own shield, it's like covered by the heatsink, like that kind of works. But for this, I mean, we designed in a shield. That helped a little bit. Turns out like the heat pipe, because it's not mechanically connected, because it's on spring screws, it's not grounded enough, so we like tried grounding that. That kind of helped. We covered up the whole thing to like cover any holes. That kind of helped a little bit. Then we had to add like shield, like a foil under the holes. Another small improvement. We had to add like a bottom side shield. It just turned into this whole thing. At some point, we even got like production versions of like the shields that we would like get the machines to solder onto the boards. Because they're like in awkward shape, they like would bend and like warp in production, and then sometimes like not all the edges would get soldered, so that also like became somewhat flaky. So we ditched that and we went to like a full like unibody copper thing that sat on top of that, like sacrificing some of the thermal performance for RF. And still, you would get like plots like these that didn't quite match what a 3 or a 3X could do. Another issue for GPS performance that we had was that some of the signals that are just like happening in the device, like driving the display or like driving the cameras, they're at certain frequencies that are like, if you multiply them by an integer amount, you would get harmonics that are right in the center of GPS frequencies. And GPS is an extremely low amplitude signal. So it gets drowned out by basically anything that's even close to it. You can see this on these plots. Like Maxime wrote this very nice piece of software that would like turn off the screen, turn the screen back on, turn the cameras on, turn the screen back off. And so like from this graph, you could see like, okay, the screen has a big effect, the cameras have some effect. And some of these you could just fix with software. Like we just looked into like the display code, and we could change like the frequencies the display was running at. We changed like drive strengths of certain like regulators and the 845 firmware. Like it turned into this whole hassle to get something to like barely work. Another thing limiting GPS was just that the antenna was on like the edge of the board. And the antennas, like these patch antennas, are not designed to do that. Like they're designed to be in like a perfect vacuum with like a nice 10 by 10 centimeter ground plane that's like very nicely centered, which is just not possible in the form factor that we were building. This is another RF plot. This is because the antenna's on the edge. Like You want this blue trace, which is what you measure. You want that to be in the middle to like be more efficient. Won't bore you with all the details, but that took a whole bunch of like optimization as well. But that then changes like the resonance frequency of the GPS, so then you have to go to like brute force all these values. This literally took months to get something that's like barely on the level of a 3x. But in the end, we kind of got there, like on RevF, C, D, E, F. We got to like something that somewhat matches a comma 3. But it's okay, it's maybe barely shippable. But if you just zoom out a little bit, we had this RevF that like barely worked thermally. We had barely working in a GPS. The case was still metal. It would get like uncomfortably hot. The fan had to run now because we didn't passively cool most of the chip anymore, which is kind of whiny. The shielding is like, there's a lot of custom components to like barely make it work. And we just came up with just, we'll do one more redesign and completely solve all the issues like just fundamentally. And that's how RevH came to be. And that's remarkably close to what we are actually shipping now in RevI. So it's, as you can see, it's like a complete redesign again. Like the 845 moved back to the bottom side of the board. We ditched the big fan hole for the blower, which allowed like a lot more space to lay out the components all very nicely. This also added the space to like add this exposed ground path, so you can have like a shield that fits nicely on top of it. The shield could also be like the heatsink, we figured out. And then from the backside cooling, it turns out that you can just have a copper plate here, and that's high conductivity enough to like just conduct that through the posts back into the bottom heatsink. And this just turned out beautifully. Even the GPS is like somewhat more central into the board, and that just fixed so many things. So this is you've already seen this, but this is the heatsink design we came up with. This is also the integrated shield, and it just is great. After that, we still did a whole bunch of experimentations on the input design, like the airflow input design. A lot of these had trade-offs between like noise production and thermal performance and looks. So we literally built like hundreds of these. The team also optimized the thermal design on the heatsink side. So it turns out if you add like a nice little cover over the heatsink to not recirculate air, and also to cover the sides of the fins, you would get both better thermal performance and lower noise profile, or at least like shift the frequencies away from the noise profile so you barely can't hear it anymore. And that was a massive improvement as well. Even more intake designs we tried before finally ending up with what we're shipping. And like thermally, this is what we ended up with, which is honestly quite incredible. Like if you look at this graph, like the blue line, that's the comma 3x. So it's running a constant like 6-watt load. And then we just sweep the fan power, wait until it settles, and you just see whatever the CPU temperature ends up in. That's, the 3x, it works pretty well, but it's thermally not the best thing in the world. So in RevF, like the final design that we had, like if you run the fan like at 60, 70%, you could somewhat get close. It's probably good enough for what we wanted to do. And then if you go back to like this abomination, like the heat sinks on the back and like the extra fin lengths and stuff, you could get it to be somewhat better than a 3x. That's the green line. And then the RevH design, that's in like a league of its own. Like even at like 30% fan, it just like blows the 3x out of the water. And this obviously also translates into driving performance. Like this is just a log app from like a route that we drove on the RevH. Like loaded while driving, like regular openpilot load, the CPU barely like dips above 50C, which is quite incredible. Because it's also under the 75C that we try to control the temperature at, the fan was basically not running at all. And then for GPS performance, that doesn't look any different than a 3 or a 3X. So we also completely solved that. Of course, like you can't do all the experimentation in-house, like all the test setups you build, like you're only testing like one device, you test it for like one time. But if you wanted to get some data on like what this thing would perform like in the field, like what are the 1% failures like, then you really need to like just get so many driving hours on this thing. And we had this nice group of people that we trusted to not leak the device, that we sent some devices to. They got like the unbox experience, they got to test the UI, provided a whole bunch of feedback. They racked up tons of miles on this device. which really makes us confident that it's a very solid design. Other than that, we have testing infrastructure from the other teams as well. So I already showed you this. This is like a testing dashboard that Maxime from the openpilot team built, which is very valuable. It just shows like every MISI drive of every day. And you just look at like all the sensors that we have in the device, like see if there's anything wrong that you don't expect. This slide's somewhat outdated apparently, but that's like the amount of segments that we got driven around RevH. And then we also had like the green check mark every day from the autonomy team, which basically meant that, okay, all the data, all the logs that we gathered from the device were actually trainable, which also is a very strict check to make sure that all the sensors and the cameras and stuff looked good. After you've done all of that, you're still not done. You still need to send it off to certification. So they put in like this big anechoic chamber. You run your standard openpilot loop, and then they just measure like whatever RF frequencies come out of it. The limit is red line. This stuff, that's all noise. That's all like the cabling and the power supplies and stuff, so you don't really look at that. But like, look at how flat this line is. Like, this is basically just background radiation. Like, the shielding we did on this thing is just incredible. Like, I haven't seen any other device that looks like this. We also went to Shenzhen. I think Adeeb already showed some of these pictures. This is invaluable feedback. Like, this so so valuable that you can see like how the processes are being done, so you can like incorporate it into like the next revisions to like make sure that it's super easy to produce. You don't get any defects in between batches and stuff like this. Like in the right, there's like the general flow of how they produce like a MISI heatsink or comma 4 heatsink, where you start with like extrusion, they mill that in a few steps. It's just so valuable to know how all these things do. That's not only the device performance that improved quite a lot, it's the complexity of these things. It's just so much reduced from the 3X. Like, I went through like the list that we have, and like the unique BOM items, like the bill of materials on this thing, that's almost dropped in half from the 3X. The amount of process steps that we do in-house, like the assembly steps, like focusing lenses, sticking on tapes, like plugging in cables and that stuff, that's literally halved. And the amount of custom parts, where we actually design it instead of just buying it off the shelf from different vendors, has more than halved. So this is quite an incredible achievement, I think. If you don't believe it, then it's way easier to build. I mean, we have a booth over there. Just go up to it, take a look at the components, put one together yourself. You don't need any training. You can literally do it in a few minutes. So I think that concludes most of what I wanted to talk about. I think we finally got to a design that's worthy enough to be called the comma 4. That was it.
Thank you, Robbe. We have a couple minutes for questions. Any questions for Robbe?
Do you guys do any formal vibration testing, or is it just relying on the ones in the field is working?
We mostly rely on the field for that, yeah. We've thought about like making like a vibration setup, but we haven't just gone around to it to figure that out.
You know, just like you have the SMT line in-house, and that really helps with iteration speed, would you ever consider bringing like the machining in-house or molding, injection molding in-house?
We'd absolutely love to. Like, if we could get CNC parts like by the end of the afternoon, that would be amazing. Okay. The office that we have now is just not quite set up for it yet. Like, we would need like a decently sized like actual factory building for this, but hopefully in the future, yeah.
I try to fit as much in our office as we can, but sometimes it's a stretch.
How do you find your simulation tool relative to the testing that you're doing? Is there any opportunity that you get to improve the simulation tool that you're using?
I already had this conviction, but I'm getting more and more convinced that like most of the simulations we do are just not very useful. Like, like you've seen this, right? Like we've simulated so many things that you just, even if you like get like one very small detail wrong, the conclusions that you derive from this they're just not useful. Like, just spend like the 2 days, build the thing in-house and just test it.
Is moving to Raylib and CPU rendering going to make a measurable difference to your kind of steady state CPU load / temperature?
Hopefully. But I think the problem is like every time the openpilot team makes any improvements on this, it's just all eaten up by autonomy again. So you just run bigger models.
All right. Thank you, Robbe. You have to stay on stage, though, I'm afraid. All right. I would love to invite the whole team up to the stage for a Q&A. Yeah. You can sit.
I'll do some yoga.
All right. Do we have some questions in the audience? No, you've already gotten all your questions out?
I don't even know who I'm directing this to. I'll pick Adeeb. Crystal ball time. When Best Buy?
I think we gotta, let's see how it sells on the website. The Best Buy is, I don't know if we want to sell to the Best Buy person. The thing about the Best Buy stuff, the MISI, we like to say the M in MISI stood for mother, in that it's ready for your mom. And it's not that we want to actually sell it to your mom. It's a way about thinking in the limit. Another thing I talked to the hardware team about is the $99 MISI. It's like if we had to have the cost of this thing, you're like, okay, I'm paying $4 for the cable, $12 for the box, and then you start adding stuff up, and then you're like, wait, this is a pretty significant percentage of my thing. So it's a way about thinking in the limit. We'll see if Best Buy is that relevant. I think we're still a bit ways from there, but it's the first product. You know, we had a non-dev kit, we had a product, we had a bunch of dev kits. Maybe 6X. We'll see how this one sells.
Okay, we've got one back here.
Hey everyone, I just want to say first of all, amazing work with Comma, and to you guys, to the people in the past. I had a question for the ML team, I guess, is in the diffusion space, one of the questions I had is when you generate the videos, are you generating them 2 individual videos and then combining them, or are they one world space model that you're generating together? Because the fact that they're both consistent really was sick, so I was just curious how that works.
No, we generate them at once. Our compressor takes in both frames and compresses both of them in one latent vector. So the world model generates both frames at the same time. That's why they're so consistent. And there was a question about adding more cameras, in which case we will just add them to the compressor, and they will all be compressed in one latent space, and they all get generated at the same time. That's how you get consistency in the dynamics and consistency in the scene. Yep. So all at once.
More questions?
Ask us anything. We like talking about this stuff.
Version 1.0?
1.0?
Yeah. Why it's 0, of course.
Yeah, we used to have all these kind of goals for this stuff. We kind of simplified it. We just shipped 0.10. 0.10 was defined by the what we call the Tomb Raider architecture, which used some of the new simulator architecture. We'll ship 0.11, which will be the full, if anybody's driven the watermelon models, that's the full world model ones. And then 1.0 will be when N10 long is in chill mode. Yeah.
I was just curious, how have you kept the team so small over 10 years and still with great output?
Refactoring. So we have a few teams. We can go team by team. I can talk about hardware and production and openpilot, and then maybe Harald can talk about autonomy. Production, I'll show you. We refactor the product. We refactor the product. We refactor the space. We designed them together. The factory is the product. The hardware team has grown a little bit with this product. It really didn't get out the door until we grew the team a little bit. The fact that it's so quiet was one of the big contributions from our new members. Beautiful design was Nick. And then the software team hasn't grown as much, but that's we'd like it to grow a little bit. We'd like to ship a beautiful mobile app. I'd love to ship fast boot times. I'd love to ship a new updater. I'd love to ship tons of software stuff. But we don't have to grow that much. We really just focus on the openpilot you get should be like some second order effect of the kind of infrastructure that we set up. So we spend a lot of time on that, and it's about being really focused. You might see us like recoil a bit when somebody asks cameras or carports or this kind of stuff. This is part of it, yeah. It's this focus.
Yeah, I think the general answer is just managing complexity and staying focused. I think one thing that I really like is something George brought up a lot, is that the management boundaries in your company are generally reflected in the code base API boundaries. And so it's really important to refactor the team to make sure that the API boundaries in the code also make sense. And I think one example of this is that we used to have somewhat distinct boundaries between controls and the machine learning policy, but these things are very intertwined, and having those things be two separate teams and having essentially both a people and a code boundary there made that there was a lot of inefficiency. Both teams often just blamed each other on, oh, this is a controls problem, this is a model problem, but I mean, it's really intertwined. It's usually a combination of those things. So then refactoring that into this all being one joint problem, just controlling the car, I think reduces a lot of the code complexity and then also allows people to make better improvements without bloating the software and creating more overhead. And I mean, my talk was kind of about exactly this problem, is how are we able to develop quickly, how are we able to ship improvements quickly, and making sure that all of the infrastructure and stuff is in place there. And it's basically the things I talked about in my talk, is right, you have really good tests, really good infrastructure, and you keep it all simple enough that everyone kind of has oversight. This entire thing is managed by, including the data center, all the tools, everything is managed by 5, 6 people. So I think that keeps it simple.
I forgot something big, actually. George will. Oh, sorry. I just want to shout out our community. Obviously, we have tons of contributors on GitHub. It's open source. You see a bunch of them over there. There's a bunch more in the crowd, and there's way more on GitHub online. So big shout out to the contributors.
So, I mean, comma has a mission of solving self-driving cars and delivering shippable intermediaries. And you have to ask the question for a lot of these large companies what their mission really is. And a lot of these companies' mission is to pump their share price. And investors haven't quite caught on yet. But one way you can make your company look big and important is by hiring lots and lots and lots of people, right? Look at these. We have 1,000 people. You good? we have 1,000 people. Wow, that's a legitimate team. And until people with money just completely stop funding this kind of stuff, you're going to see it. But the reason we're small is because our incentive is to solve a problem. The reason they're big is because their incentive is to raise their share price. And investors see big company, big share price. Oh, yes.
Got a question over here.
For the C4 and the 2-year warranty, do you still get that with Prime Lite, or do you get it with the full version of Prime?
Full Prime, $24 a month.
Other questions?
We'll clarify on the website this week.
Is there a reason the video segments are 1 minute, or did that just kind of, how do you guys end up at 1 minute segments?
I don't know. Do you know? Anybody know? George?
It's a good length,
Yeah.
It's a good length. What's the history behind the 1 minute segment?
I mean, we had some choices. We thought about 53 seconds, but we thought 60 would kind of just be better.
6, 7.
With all these forks and variants, have you guys been thinking more about third-party APIs or SDKs and making it easier to develop on or pull data out of?
Oh, we are.
Yeah, do you want to talk about it? Yeah, so I mean, we have the best one. All the code's open source. You can mess around with it. As far as what happens on the back end, this is also pretty transparent as far as if you want to interface with our app and stuff, if you're making some kind of openpilot-like software. It's pretty clear how our software works if you just mimic it. And then as far as making forks trainable and stuff like this, we're starting to move in this direction. I think it's playing out such that openpilot is we know openpilot's pretty bare bones. We want to just sell you a thing. If you go to our website, you find your car, you find the Honda Civic, you click add, and you get it. We want you to set up in 5 minutes, and you don't really have to think about it. This is all the experience we all drive with. And then, you have Sunny Pilot, you got Frog Pilot, you got Star Pilot, you got Blue Pilot who do the Fords. This is like all the Linux distros. And some people, they hear open source and they think hacky. But I mean, Linux is everywhere. And openpilot will be the Linux.
Got one back here.
Are you guys planning on keeping 2 modes for the foreseeable future? Like, why not just 1 mode or 3? Like chill versus
We don't want to, but
I mean, the reason there's experimental mode is because if we made it the default, people would be upset. We want that to be the default mode, but it's just not good enough yet. So, I mean, that's what we're working towards, is making that good enough to be the default.
All right, one more question over here.
So I'm not sure if you already covered this, but is the external GPU going to be usable properly on the C3X, or is there something specifically on MISI that requires it? Just making sure.
So it does work. The MISI has one thing that's very specific, comma 4. The comma 4 has one thing that's specific. We improved it, so I don't know how many of you know this, but USB and GPS don't like each other. And the thing is, we need GPS to train. You saw Mitchell's talk, you saw how the localization stack works. So we didn't know this until we did the comma 4. And so we made some improvements in that regard. So that's the one big difference. But for the user, we might not be able to train on your segments, but as far as we know, there's no differences right now. Yeah.
GPS doesn't work on the 3-axis. You got a GPU. It works on the 4.
Which at runtime is no longer required. When the 3X launched, it was required at runtime to drive. We've removed this. Refactor.
All right, we might have time for one more question.
So I was wondering how the comma prime works in terms of like a cellular plan. Do I have to kind of use my own eSIM or physical SIM in order to kind of get the benefits of it, or do you supply? Because I remember at some point it came with cellular from comma, I believe.
Yeah, so since we introduced comma prime, we would ship like a T-Mobile or an AT&T SIM. It changed over the years. And the problem with those SIMs, those are just normal SIMs, like pre-eSIMs. And as soon as you cancel those, just because this is how the carriers operate, you can't reactivate them, and we'd have to ship you a new SIM. So the eSIM just simplifies that. It's still a very managed experience, and there's a lot of subtleties to eSIMs, unfortunately, but the eSIM that's in the comma 4 is the same type of eSIM that's in your iPhone. So if you want to take your comma 4 and you want to install your own eSIM, we don't have a convenient interface for that yet, but the hardware totally supports it. And right now what the software supports is setting up our managed experience. So comma prime is a totally managed experience. Then we offer Prime Lite, mostly for international people. And if you want to install your own SIM, that kind of stuff, you're totally able to. But the comma 4 vibe is, it just works.
So for international, I just basically have to have my own cellular.
Yeah.
Can we fix that? Especially Canada.
Yeah.
Yeah.
We'll work on it.
All right. The team will be around. Oh, so sorry. The team will be around for more questions out in the space. They love talking about things, so feel free if you have any unanswered questions, find them, talk to them. We have one more talk, which is going to be over here by the Porsche by one of our star contributors, Jason Young. If you were at Comic-Con 2 years ago, he gave a talk, How to Port a Car. This is How to Port a Car V2. So he is going to go live, so we're going to need about 5 minutes to transition our camera over there. But we invite you to go see his talk. It's starting in approximately 5 minutes. After that, there will be pizza. The bar is still open. And if you have not picked up your merch yet, please remember to do so before you leave tonight. I want to give a big thank you to the whole team. They have worked so hard to bring you this beautiful comma 4, and we're so excited to share it with you today. Big shout out to the people that aren't on stage, also our production team, our fulfillment team. They are all here and they work behind the scenes to build these beautiful devices and get them shipped out to all of you. So thank you so much for being here. We're so excited.
Oh,
I just want to give a live update to my talk, Maxime and I's talk. We briefly talked about PyTest in the beginning, using that for our test suite. And my point was that you shouldn't always rely on libraries because they take out the complexity for you. And just today, 8 hours ago, PyTest pushed an update that broke OpenDBC tests, so I had to fix that just now. So, yeah, we should write our own PyTest.
All right. I'm Jason, and sometimes
I have the antenna on this side.
Okay. Check. There we go. Hello, everyone. I'm Jason. Sometimes I work on carports. Usually I do it with people watching, but I'll see what I can do. I have one slide, and then we're going to get down to business. We're going to talk about the minimum you need to do to get your openpilot environment set up and get your nice new comma 4 connected to your car. We're going to talk about a demo carport that I put together to try and make this a little bit easier. We're going to talk about kind of the processes I use in Cabana to turn that big scary wall of numbers into something usable, and some of the OpenDBC tests. That's my slide. And we're going to get down to business. For those of you that haven't installed OpenPilot on your laptop before, more than just like installing on your comma 4, you're also going to install it on a development environment on your PC. You can use Ubuntu, you can use WSL, anything. You'll run this on your PC. I'm not going to do it right now because it takes 5 or 10 minutes to run, and you're all staring at me expecting something more interesting than watching a compile run. So I have OpenPilot Master checked out. And within that, we have OpenDBC, and we have, well, Shane was talking about that PyTest thing earlier. We were trying to fix that real quick. We're going to check out the demo port, and the reason we want that, I'll show you here. Sorry, I had everything open, and then we were trying to fix that PyTest thing. So we have a development template carport that it's not merged into mainstream OpenPilot yet. It's kind of an experiment. I'd like to do this a different way, but we're going to try this for now. It puts in all basic infrastructure so that you can get down to mic off. There we go. The interesting part is our use of the all output safety mode, and particularly this mode, because with that little parameter on there, it switches OpenPilot into a mode where we're transparently forwarding. We open a relay and we start recording which traffic comes from which side of the bus. That's already running on the comma bar. And if we start the car, and we do it with the key in, pilot is started up. OpenPilot is started up and has started recording data. And if there's a signal that we want to find in the car, this is a good time to trigger it. Like, let's say I want to find the turn signals. I'll hit the left turn signal, let it go for a minute, and hit the right turn signal, let it go for a minute, and shut off the car. The way that I do this is always based on uploaded logs. You can go to Comma Shop and you can buy a Red Panda, and you can actually do this live just with your laptop. But my method is just to always let the device upload logs. Let's see if my device is online. It is. And it has just recorded a route. No, that's not it. Come on. It hasn't uploaded yet, but fortunately, I have prepared extensively for stuff going wrong. So we have a series of tests here, and I've put together a document that shows some tests you can go through to produce all the signals that OpenPilot is looking for. Wheel speeds, the accelerator, the brake, et cetera, et cetera. So we'll look first at the drive stationary test 1. We're going to grab that route ID and pull it up in Cabana. And this is going to be a bit of an eye chart. Let me, oh, you know what I need to do is start screen recording. There we go. So this is going to be a bit of an eye chart, and nothing really useful or sensible is happening here. We just have bits that are changing, and we're not sure why. But as there are some general rules here we can use to figure out what's going on. The reason we're using this demo carport is because the comma 4 has multiple CAN buses connected to it, and we can choose which one we're looking at and just show the messages that we care about. And that's going to narrow it down a lot. And then we can filter by frequency, or rather sort by frequency. And from here, there's some general rules. The most important CAN messages, safety-related stuff, wheel speeds, steering angle, et cetera, they're going to be in higher frequency messages, generally 100 hertz, sometimes 50. They're also going to be on lower numbered CAN IDs, just due to the way the CAN protocol works. Those end up being higher priority if the bus is busy. The lower frequency stuff and the higher CAN arbitration IDs Those are all convenient stuff, blinkers, seat belts, stuff like that. You don't need you don't need to know if your turn signal's on 100 times a second, but you do need to know wheel speeds. So you can see Cabana here highlighting just the bits that are changing, and the ones that aren't changing are being left alone. There's a lot of activity here. My process is to go through and kind of cut through all the noise, get the noisiest stuff figured out first. And the noisiest stuff is going to be the checksums and CRCs. Every message, or most of the messages you find on CAN bus are going to have a counter and a checksum associated with them. We happen to know the counters on this car are usually located in bits 8 through 11, yeah. And then the checksum is that first 8 bits. The checksum will appear random, but it will cyclically repeat if the rest of the message is the same. But the checksum will just keep rolling it over and over and over. So the first order of business is to identify all of those, because Cabana has a feature where those stop being highlighted if they've been identified. So we can cross off all the checksums and CRCs. Now, I could make you wait and while I go through and mark all the checksum signals and all the CRC signals, but through the magic of having done this yesterday, we can skip to the point where all the checksums and counters have been identified. And as you can see, lots less activity here. So now we're hopefully able to better see what's going on. I'm going to go back to our document on what I did in that drive. So we're looking for the doors. We're probably going to look for the accelerator and the brake first. The accelerator is nice and easy. It's a little further into the route, which is only a couple minutes long. And let's see what we got going here. Don't know what this is, but don't be afraid of marking stuff off just to see what's in there, see how Cabana graphs it for you. Any activity you see could be interesting. Something interesting going on here. No, that's not it. That's not it. If you need any evidence that I have not, in fact, memorized all the CAN IDs, this is it. Okay, so here's something promising. So I've highlighted these 8 bits here, or I've made them part of a signal, and you can see a weird pattern here. It goes up and it cuts off. You'll see this when you're reverse engineering. What happens is I marked off these 8, and it ends up overflowing into the next one, and that's kind of a good indicator that the signal's a little wider than you initially thought. Or actually, maybe it starts a little earlier. A little more? There we go. So we've got 3 things going on there. I'm not sure if that was the accelerator or the brake. I think this is the brake, because for the accelerator, we went to the floor 3 times, 100% each time. For the brake, I didn't have the engine running, so this is like a hydraulic brake pressure, and with the engine not running, you get like that NHTSA mandated vacuum boost left over for the first couple times you press the brake, and then there's a little loose. So this is going to be like a brake pressure. So we'll mark that off. And then I believe I did the accelerator before this. So we're looking for accelerator activity. somewhere before. Da, da, da. Don't know what's going on there. Okay. I just wasn't in the right place. It was right before the break. There we go. There's our accelerator. I pressed it 3 times, went to the floor, and it went to a full 8-bit width each time. Well, just slightly less. It went to 250. This happens to be a percentage, so if we scale it by 0.4, that'll bring it down to a percentage. 0% when released, 100% when not. So now we've got our accelerator, we've got our brake. And now things are starting to get a lot less noisy. What else did we have in here? We had the doors. So the doors we'll be looking for somewhere down here. We'll be looking for them in these lower frequency messages, and they'll just be little one-offs that you're going to have to hunt for and see if anything interesting happens. Okay, so right there, I have to know when I walked past the camera, that was, I opened driver, passenger, rear left, rear right. That's me walking from the driver to the passenger. So I'm pretty sure this one was the driver's door. I got out, shut it, and then I should see a bit flip for the passenger. And then we saw some more while I was typing. And that'll be the rear left. And this will be the all right. So we know this one's going to be like from a BCM or something. I think in the demo carport, I think I called this door states. I can't recall. Let's take a look. We've got a named message here now, door states, and we can save this DBC. OpenPilot. We're not scrolling. And we're going to save it over the demo DBC. Yes. So now we've got a DBC entry. Now we can teach OpenPilot to read it. Once PyCharm starts back up. Let's go to another signal while it's thinking. Did we get everything out of this route already? We got the doors. I'm going to skip the seatbelt for now. We'll come back to something more interesting. Let's see if we can find the gear shift position. This same route, obviously we start in park, but after I got back into the car, I went to neutral, or rather reverse, neutral, drive, and back again. So I know that this was, where did we put the brake pressure? So we know it's right after this brake pressure, right? Yeah, So we know it's somewhere in like this area. So we're going to zoom in the timeline and play it and see what pops up. I think we got something happening here. Yes. Okay. So these 4 bits here are giving us some interesting activity. They are the same for the whole drive until I'm messing with the gear shift. So it starts at a 5, 6, 7, 8, and then back to 5. So we now know this is a gear position. And we'll go ahead and call this message transmission. And we'll do something extra for this signal because we know what certain values mean. We know that 5 is park. We know that 6 is reverse. We know that 7 is neutral, and we know that 8 is drive. Now this is super basic. I think the thing's got like a sport gear, it has manumatic. There will be more states in here, but this'll do for a demo. All right, let me check how we're doing on time. So going through this whole process for all the signals will not fit in the time slot that I have. Going through an entire carport, and I've done it quite a few times, is probably a long weekend, but we can skip through here and look for some interesting signals like, you know what, let's actually skip to the fun signal. Let's skip to the one that actually controls steering, just to make sure we fit that in. This is a route from a community Macan owner who gave us a stock lane keeping assist route because this particular Macan doesn't actually have the factory feature for lane guidance. The car's capable of it. We turn it on. OpenPilot can use it, but I couldn't get a stock route from it. So we'll come in here and launch Cabana on that route. And because he was in dash cam mode without that special switch to actually open the relay, we don't have all the traffic is present on both buses 0 and 2. So I'm going to cheat here a little bit because I happen to know it's in this message. Let's load. Let's load our demo DVC. And we're going to call this one HCA01 because that's what it's called. We'll mark off the checksum. We'll mark off the counter. And you'll see nothing else is really happening here yet. What we're going to do is skip till it gets out to like a main road. And oh, we got some activity now. So as soon as he went out to a road, he bounced it off lane lines a couple times for us, and we're getting some obvious activity here. Yeah, so these are force inputs from the lane keeping assist system. We're seeing that that jagged edge there again that kind of indicates I didn't make the signal wide enough. So I don't recall the exact width, but it's definitely more. Let's call it 12. See if it. Oh, it was just the Indianness was wrong. Let's do this. There we go. So this is the factory lane keeping assist system. When you see him get close to a road edge, it's applying torque, force to the steering wheel to counter that. The Volkswagen family cars, this one is secretly an Audi Q5 under the hood. It shares a platform. The Volkswagen family cars, for steering angles, pretty much any angle, they don't use a signed value for whatever reason for direction. It's an absolute value, and they send a separate direction signal. So we'll call it LKA torque sine and LKA. And there's usually going to be a bit somewhere that's just turned on whenever it's active. In the interests of time, I'll tell you I happen to know it's over there, or at least I believe it is. Make sure I got the values right. Yeah, so on this car, it is a 3-bit field, values from 0 to 8. If we look in the beginning of the drive, there'll be an init value. Yeah, it'll init at 0, it'll go to 3 when it's ready, and it'll go to 5 when it's actually intervening. So as you go through and come up with all of these values, we can take them and plug them into the demo car port, into car state. We put in here, and this is just a test to see how it goes for speeding up car ports. These are all the signals that we need to populate. And did we find accelerator position? I believe we did. Maybe I didn't save it. I hope I saved it. Let's do transmission instead. So as we find these values, we can come in here and uncomment the places where we read those signals. Now that we've got a gear shift position, every time car state runs, openpilot will now know we're in drive, we're in reverse. Like openpilot will refuse to engage if you're in park. If you're in reverse, it puts up the reverse display on your screen so you don't look at it like it's a backup camera, et cetera, et cetera. So the process you go through every time is you've got to find the wheel speeds, you got to find brake pressed, gas pressed, steering angles, cruise activation, blinkers, et cetera, et cetera. For purposes of the live stream, I have a really limited time slot. For purposes of nerding out in a group of friends, I'll do this all night if you want to see more afterwards, but I'm sure Julie's going to give me the hook eventually here, and people would probably like to eat. Oh, people are already eating. Good. I'm not holding anyone up. So, questions, anyone? Go ahead.
What do you type into this demo script or this default?
What do I type into it?
Like the values that you found, how do you add them in?
So what's happening is when we save this DBC, it goes into car. Oops, I clicked too many times. DBC. This file right here. So we have a transmission message with a checksum, a counter, and a gear position. And down lower in the file, you'll see the value table for gear position. And then openpilot, when it starts up, the demo car port will read the demo DBC for this car, and that way when the car state is running, we're referencing that DBC for these signals. So that tells it what message to read, and then this shifter values map that we read up here is what goes down to the bottom of the file and reads that value table, 5, 6, 7, 8. These names are made up. I made them up just for the demo car port. You can call them whatever. The intent was to kind of be able to skip all this stuff and get straight to the fun part of finding order in the chaos of this giant wall of numbers. So we can find signals in here all day if you want. But again, I have limited time on the stream. I want to be respectful of everyone else's time. So if you have more questions or you want to see more, I'm happy to. Yes, sir.
So with the newer cars, what happens is like if you try to like plug in to like OBD2 port and like you try to tap into CAN, you don't see anything.
That's correct.
Is the red panda capable of like seeing it?
So the question is, why don't you see anything from the OBD port that uses CAN? It's a good question. And the answer is there's something like, there is not one CAN bus in this car. There's something like 8. And one of them, so there's a central CAN gateway, which has 6 CAN buses. One of them connects to just the OBD port. There's another one for infotainment, convenience, powertrain, chassis, and extended. And extended is where all the cool ADAS stuff is. That's the bus that we split. That's where the radar is, that's where the camera is, and that's where the like the blind spot radars are. And then there's 2 more at least. There's a fusion bus between the blind spot radars, and there's a fusion bus between the camera and the radar. Neither of those connect to the gateway directly, but the answer to why you don't see everything is because there's 8 CAN buses, and the gateway filters out everything that isn't diagnostic relevant. It doesn't repeat all the other internal stuff on that port. Other questions?
So for the torque steering, you selected absolute values. Will it be same for all cars of the same model?
So of all the cars in the same model, yes, generally of the same platform. Volkswagen and other manufacturers as well, really good at recycling stuff from the parts bin. It tends to all work the same way. Other Volkswagen cars that use, say, the MQB platform, and there's 20 or 30 of those, it's all the exact same openpilot code that supports it. There's 3 or 4 different VW platforms. They all tend to work very similarly. Other manufacturers, I think all the Honda cars work almost the same way, including like going all the way back from the mid 2010s to the most current CAN FD stuff. They use the same messages, same signals for the most part.
So does it make sense to start with Q5 and then build on that?
Like the other, like the Audi Q5 that this is based on. So it can. You can just start wherever you want. They're very, very, very similar, like 98th percentile similarity. This is just the car that was in front of us that was the most interesting. We thought it'd be cool to play with at Comic-Con. And we'll come and layer Q5 on top of this. Mm-hmm. Anything else?
Is it right to assume that all information is open in the sense that it's not encrypted, or is there any?
So the question is this information open and not encrypted? Yeah, the information is there in the open. It is not secured per se, other than it is undocumented. You get to figure it out, but we have great tools for figuring that out now. Even the checksum and the algorithm for that varies, isn't really intended as like anti-tampering. It's more intended to protect against bit flips as it transits like a CAN gateway. There's CAN network level checksums, and then the payload checksum is intended to protect it end to end. You will hear people talk about like Toyota TSK. You're seeing some cars now, not all, but some implement actual cryptographic signatures on the messages. You'll see that some Toyota messages will have a very random looking signal that's like 16 or 24 bits wide. The fun police have come for you there. It is specifically designed to stop man-in-the-middle attacks, which you might consider that to be what openpilot is doing, depending on your point of view. There's none of that here. It is showing up a little in the field. It's not hit everyone yet. We're seeing plenty of 2025 and 2026 cars come out that have none of this. So it's not been like oh my gosh, I can't get a car without this anymore. Some manufacturers, Toyota's all in on it, it seems, but I don't think anyone, maybe some new Ford, new GM. I think those are the big ones that I can think of at the moment. But haven't seen it on Hyundai, haven't seen it on VW yet, but we think it's coming. Haven't seen it on Honda, haven't seen it Mazda, Subaru. Mm-hmm. More questions? Great question. Question is, what's the minimum set of signals? And I tried to put together a little bit of information about that. So you need to fill in brake, gas, the cruise state. You really should have like door open and seat belt. And you'd have to have that before upstream, but like if you didn't look at it right away, if you're just developing on your own, things would be fine. Gear shifter, I would go for it right away just because it's easy to find and nice to have, but like you can hard code the carport to drive while you're in development if you have to. You'll need the blinkers in order to do lane changes. Standstill you can do on your own. You'll have to know your steering angle. Steering torque you'll need for lane changes and for the safety model to work right. And you need to know how fast the car is going. Things you'll need to send. You'll need to send whatever the control message is for your car. It can be based on torque. It can be or angle or curvature. And you'll have to figure that out during the process of reverse engineering. All right. Anything else? Well, this is my carporting talk. Thanks for coming.